Welcome to the history of mathematics, the queen of the sciences. My name is David Brassu. I'm a mathematician and a teacher, and I have a real passion for the history of mathematics because mathematics is really about ideas. And I think one of the most effective ways of understanding these ideas is to look at how they have developed. Where did they come from? What were people trying to do as they looked at these ideas? How did the ideas arise from many different civilizations and cultures? How did they interact? What were the difficulties that people encountered in developing them? And how do they play out in our world today? I'm also interested in the history of mathematics because I'm interested in it as a teacher. As I try to explain these ideas to my students, I want to look back and be able to motivate the ideas by showing them where they came from, but also, and sometimes even more important, to look back and see where the difficulties have been. Where did people have trouble in coming up with a particular idea? What were the ideas that came naturally, that were easy to find? What were the ideas that were very difficult and took a long time to develop? Those places where the mathematicians and scientists had difficulty with the mathematics, I can expect are going to be places where my own students are going to have difficulty. And it greatly encourages them if I can say, look, this great mathematician, Augustin-Louis Cauchy, the greatest French mathematician of the 1820s, was struggling with this idea. If you're struggling with it too, that's just to be expected. I also enjoy the history of mathematics just because it's full of great stories. We're going to be looking at a lot of interesting people. We're going to be studying people like Leonhard Euler, probably the greatest mathematician who ever lived, who would continue to be incredibly productive even after he was completely blind. We'll look at people who died extremely young. The young Évariste Galois, who would solve one of the most fundamental problems in mathematics at the age of 17 and die before his 21st birthday. We're going to look at the self-taught mathematician Srinivasa Ramanujan. And we're going to see how, despite the obstacles of growing up in southern India without access to much of the mathematics of Western Europe at the time, he was able to get his hand on mathematics textbooks and learn from those and become one of the greatest mathematicians of the 20th century. But before I get into the history of mathematics, I want to back up and look at the topic of this particular lecture, which is, what is mathematics? To me, the essence of mathematics is the abstraction of pattern. What mathematicians do is to look at the world around us and see the patterns that are out there and then abstract those patterns in order to be able to work with them and manipulate them, and use them then to tell us more about this world that we see around us. Some of the simple examples of this abstraction of pattern come from numbers, they come from geometry, and most people, when they think of mathematics, they think of number, and to some extent that is appropriate. I hope by the end of these lectures you'll have a much richer sense of the kinds of patterns that mathematicians work with. But the beginning of understanding these patterns really is with number. So we look initially at number simply as a qualifier. We have 5 people. We have 5 loaves of bread. We are looking at 5 stars in the sky. And from that, we abstract the number 5. And that's very useful as we begin to combine objects. If I have 5 people in a room and 3 more people come in, I now have 8 people. If I have 5 loaves of bread and add to those 3 more loaves of bread, I now have 8 loaves of bread. And the fact that we've got, in essence, a 5 and a 3 that combine to become an 8 is something that goes beyond the people or the loaves of bread. It's a mathematical abstraction. And once we take those patterns and begin to abstract them, we can begin to play with them. The same thing happens in geometry. And the basic geometric objects are things like lines and circles, and they're really expressing spatial relationships. So we look at 5 stars in the sky and we see that they seem to be in a certain pattern that we describe as a circle. Or we might look at a ring of stones on the ground and we describe that as a circle. Or we might simply have 3 points that we're interested in. There's the tree over there and the house that's here and myself standing somewhere between them, and I consider those 3 points and I begin to think of them as a triangle. And so we get this geometry that comes out of abstracting these patterns. And one of the interesting questions that comes up as you begin to think about these abstractions that mathematicians are working with is, what is the reality behind them? Is 5 something that actually exists? Is a circle, a pure Platonic circle, something that really exists? And of course, I use the adjective Platonic because this gets back to Plato's view that in fact these ideal abstractions really do exist, that there is a reality beyond ourselves that we are tapping into as we make these abstractions. And this gets to a more fundamental question that is often debated by mathematicians and philosophers of mathematics and philosophers of science, and that is whether mathematics is discovered or whether mathematics is created. Are we simply revealing something that is out there as we put together mathematics, or are we creating something? I actually come down between those people who believe that mathematics is discovered and mathematics is created. I am at heart a Platonist. I do believe that there is an ideal world out there that we are trying to understand, that we are trying to tap into. And as we develop these abstractions of patterns that mathematicians work with, we're really trying to explain a deeper reality that is out there. But it is also a very subtle reality. And most mathematicians, most scientists realize that we can never really describe what's out there. What we are doing with mathematics is creating a language, a set of symbols that enables us to work with some aspect of that deeper reality that is out there. But in most cases, we cannot claim that we really fully understand that, we really fully comprehend it. And that's one of the things that makes mathematics so exciting, because as we abstract these patterns, we begin to try to look beyond what we've been working with. What a mathematician does is to take an abstraction of a pattern that she or he sees over here and another pattern that's observed someplace else, and you look for points of similarity between these 2 patterns. And as you overlay the patterns, as you begin to look for these points of similarity, you see that they suggest ways in which the pattern might extend. And so you begin to explore that. Is this really going on? And this is what makes mathematics so very exciting, is this kind of exploration, knowing that there is a world out there that we understand very imperfectly, and we're exploring it in the mathematics, taking what we know, trying to find ways of combining what we know in order to be able to go further into the unknown and to understand that. Now, the patterns of mathematics come from many different sources, and I'll talk about many of these sources through this series of lectures. One of the most important sources comes to us out of commerce and civil administration. And this certainly is where we get basic arithmetic. This is where we get our fundamental operations of addition, subtraction, multiplication, and division, and also simple fractions as well as the whole numbers or integers. And we can see ways in which fractions come up quite naturally. If I have 5 loaves of bread and I want to share them among 3 people, then each person is going to get a loaf of bread and something left over. And to be quite precise, each person, if they are shared equally, will get 1 2/3 loaves of bread. So fractions come in fairly naturally. Commerce and civil administration also give rise to rates. What's the rate at which someone can accomplish a certain job? You want to know how long it will take to build a wall or dig a canal. And so you need to know the rate at which people are working. You want to know what the yield is on a given plot of land, and so you want to know how much barley is produced on each acre. Commerce and civil administration will also be the origins of much of the work in algebra. We're going to see how algebra comes out of these problems in arithmetic, but also how algebra comes out of problems in geometry. And this will be one of the threads in some of the early lectures. Another source of the patterns of mathematics comes from problems of navigation and problems of surveying. So we're trying to do land measurements. And this gives rise to geometry, which literally comes from the words geo, earth, and metry or metric measurement. So we are measuring the earth. And geometry then arises from these problems of trying to determine distances, trying to determine areas, trying to determine volumes. As I said, we'll be using geometry to motivate much of what goes on in algebra. And we'll also be using geometry to motivate much of the number theory that I'll be talking about. Number theory is really about understanding the structure of the integers. If I've got an integer like 20, how can I represent it? Can I write it as the sum of 2 squares? How can I decompose 20 into a product of primes? These kinds of questions are the questions that we're going to see addressed as we look at number theory. A third source of the patterns of mathematics comes to us from astronomy or astrology. And in the ancient world, there really is no clear distinction between astronomy and astrology. And in fact, right up well into the 17th century, people would not make a distinction between these two. You studied the heavens in order to try to understand what was likely to happen on Earth, but you really were doing astronomy, but it was done for astrological purposes. And we're going to see how some of the greatest astronomers also were astrologers, in particular people like Johann Kepler at the very early years of the 1600s, whose work in both astronomy and astrology would lay the foundations for much of the work that would be done in developing the calculus. This distinction between, or lack of distinction between astronomers and astrologers also carries over into mathematicians. And in fact, if you look at the ancient world, or even the medieval world, or even the Renaissance world, the words mathematician, astronomer, and astrologer were used interchangeably. And one of the stories that I like very much is of the Emperor Tiberius, who, it is recorded, banished all mathematicians from the city of Rome. Now, he was not banishing the accountants. He was banishing the astrologers. The astrologers were predicting his downfall, problems for his empire. He didn't like that fact, and so he was banning the astrologers. But to Tiberius, and for many hundreds of years after Tiberius, astronomy, astrology, and mathematics were all bound up in the same package. And largely that's because some of the most important advances in mathematics came directly to us out of astronomy. Because we're trying to understand the patterns of the world around us, and most of the world around us is too messy to be able to pick out these patterns. What we need to do is to take a look at a place where the patterns are much simpler. And astronomy would turn out to be one of those places. By looking at the heavens, we saw these patterns in a much purer form. But it's not just astronomy. We're going to continue that into a general viewpoint of the physical phenomena of the world and how we've pulled patterns from them. We will also be looking at optics, and eventually we're going to be looking at electricity and magnetism, and even the study of subatomic particles, and see how mathematics was influenced and how mathematics often was created from trying to explain these physical phenomena of the world around us. Yet another source of mathematical patterns that will be very important is art and architecture. Especially as we get into the later lectures, we're going to see how the ideas of symmetry would come to play an absolutely fundamental role in the mathematics that would be developed in the 19th and the 20th centuries. And that's one of the reasons why I'm standing in front of a picture of the Lion Court at Alhambra in Granada, because that particular palace is a wonderful example of symmetry in art. And it's actually through the symmetry at Alhambra that many mathematicians have come to a realization of the kinds of patterns that they then could apply to other problems, both in geometry and also in algebra. I want to say a little bit more about number and distance. We've talked about number as abstraction from actual units. So we're counting the number of people or the number of loaves of bread. And sometime in far antiquity, somebody decided to take this idea of number and apply it to distance. And you run into a problem there when you try to apply number to distance, because the difficulty is there is no natural unit when you're looking at distances. If I want to know how far is it from here to there, well, today I might measure that off in feet or meters or yards. But those are simply human constructs. What are we going to use as the unit to measure off distance? And even once we decide what the unit is going to be, there's no reason why the unit we've chosen is really going to be appropriate for the distance that I'm looking at. So if I've got my unit, say a stick, and I'm going to measure off the distance to some point, almost inevitably, as I get close to that point, I see that the distance that's left is less than the length of my stick. But I'm not able to take a whole number of sticks and measure that distance. One way of solving this problem of this little piece that's left over is to take my stick and mark it off into smaller intervals. I might mark it off into tenths, or I might follow the Babylonians and mark it off into 60 small pieces. Or I might follow the Romans and mark it off into 12 small pieces. This is where we get our foot divided into 12 inches. And I'm now going to take these smaller pieces and try to measure off the remaining distance. But almost inevitably, the smaller pieces are not going to measure the remaining distance exactly. And so I'm going to need smaller units still. Take each of those inches, take each of those small pieces, and subdivide them. And as I do that, again, it won't exactly match. And eventually the scientists, or in the case of early mathematics, the bureaucrats, began to realize that in fact this was a process that would never end. And now the question is, does it make sense to talk about the distance between here to there as a number if we can never express that number exactly, if the best we can do is get these approximations using smaller and smaller units? This is a question that the Greek mathematicians would really wrestle with, but we're also going to see it in the Babylonian mathematics of 4,000 years ago. Trying to apply number to time introduces other problems that are going to be very important to our story, because unlike distance, where there is no natural unit, when I look at time, we've got too many units. We've got the day, we've got the lunar month, and we've got the solar year. And each of these units is incommensurable with the other. You cannot measure off a lunar month in a precise number of days. It's going to be a number of days plus a bit left over. And you cannot measure off a solar year in an exact number of lunar months or an exact number of days. Whichever of these two units you use, there's going to be a little bit left over. And as you subdivide these units, there's always going to be a little bit left over. But even more importantly, what's happening is we've got different units traveling in different cycles. And this would present fascinating problems for mathematicians to wrestle with, is how to figure out when all of these cycles would line up. a very important question in astronomy and astrology, as people look not just at the cycles of the day, the month, and the year, but also the period that it would take Mars to circle the Earth, or the time it would take Venus to circle the Earth, or the time it would take Saturn to circle the Earth, and then trying to find out when different planets would actually be in alignment in the future. As we explore this question of the nature of mathematics, it's going to be very useful to refer to two papers that I'd like to talk about now, the first of which was written by the physicist Eugene Wigner, who taught at Princeton University, and he published the paper in 1960. It's called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. And one of the things that Wigner observed as a physicist was that physicists look at the world around them and they try to understand the patterns that they see, and then they turn to mathematics. And they ask, are there similar kinds of patterns that the mathematicians have been working with? Can I take this pattern in mathematics and apply it to the physical phenomena? And Wigner remarked that, amazingly, most of the time when physicists see a pattern in the natural world and they pick up a pattern from mathematics, that pattern in mathematics actually fits what's going on in the natural world with amazing accuracy. And not just amazing accuracy, it also often has excess content. It is possible to take that mathematical model and see beyond what we were trying to explain. So not only does the mathematical model enable us to do the predictions of what we already saw, it suggests a deeper reality that is out there. I will return to this theme periodically as I talk about the work of Newton, and also especially in the second to last lecture, when I'm going to show how mathematics really does represent the ultimate physical reality, showing us things that we never would have expected without the mathematical models. And Wigner asks the question, why is mathematics so good at this? He defines mathematics as the science of skillful operations with concepts and rules invented just for this purpose. Now that suggests that there's an arbitrary nature to mathematics that I don't quite buy. I do not believe that mathematicians just sit at their desks and try to think up interesting patterns that they can play around with. As I said, mathematicians really get their ideas for the patterns that they will study by looking at the world around them. And so, in some respects, we should not be surprised that if we look at the world around us and we extract a pattern and then we try to apply this pattern to the world around us, it often will fit. But what is surprising is that the patterns that are pulled out of one area, so, for example, we're going to see how astronomical phenomena gave rise to the trigonometric functions. We can then take those trigonometric functions and apply them to something that seems to be totally unrelated to the heavens, namely a vibrating string, and see that exactly these trigonometric functions that came out of our study of astronomy are going to be applicable to problems in mechanics, problems of vibrating strings, and actually eventually applicable to problems like heat flow and electricity and magnetism. There was a second article that I want to talk about. This is really a response to Wigner's article. It was written by Richard Hamming in 1980, and it's called simply The Unreasonable Effectiveness of Mathematics. Richard Hamming was a very prominent applied mathematician. He worked at Bell Labs, and he did a lot of work in signal processing. And he was also interested in this question of why mathematics seems to be so useful, so effective. And he did raise that point that I did, that after all, mathematics is extracted from the world around us, so we shouldn't be too surprised that it's applicable when we try to apply it back to the world. He was actually less surprised, though, that it could be applied to other areas than I am. But I want to raise Hamming's article because he does a nice job of clarifying what mathematics is. He describes the four faces of mathematics. And the first two I've already talked about. The first face of mathematics is number. The second face of mathematics is geometry. The third face of mathematics is close reasoning. And this is extremely important because, as I said, as we're looking at mathematics, we're taking these patterns, we're overlaying patterns, and very often we're extracting patterns from the overlay of patterns. And as we build these abstractions of the patterns that we saw, they create new patterns and we abstract from them. And mathematicians are often working with abstractions of abstractions of abstractions of abstractions. And to keep track of what's going on and to really have a reliance on the results that you get, to have some confidence that you really have found something that really is there, that really will be useful, you need tools in order to keep track of these abstractions of abstractions and how they work together, and what are the legitimate conclusions that can be drawn and what are not the legitimate conclusions. Now, one of the ways of doing this is through formal logic, the logic that was developed in Greece, that comes to us from the Greek mathematical tradition. But I like the fact that Hamming uses the words close reasoning rather than logic, because I think the picture is much broader than just the kind of formal logic that we know from Euclid's Elements, the Euclidean geometry. As we look at many different cultures, many civilizations, and the way that they have developed mathematics, we're going to see that they came up with different ways of maintaining this close reasoning. It did not have to be the kind of formal logic developed in Greece. And the fourth of the faces that Hamming talks about is artistic taste, and I really like this, because there is something about mathematics that is very aesthetically appealing. And as we're looking for these patterns, there almost inevitably has to be an aesthetic appeal if we're on the right track. When we see the kinds of symmetries that we want, when we see these kinds of patterns coming together and just clicking perfectly, perhaps in an unexpected way, but in a very satisfying way, that's what tells us that we are working with real mathematics and with important mathematics. And it's very difficult to define this aha moment when things come together, but it's incredibly exciting when it does. And there is this real feeling of the need for artistic taste and the artistic appreciation that comes from it. I believe that mathematics is far less arbitrary than Wigner talked about it. I believe that it's much more surprising than Hamming claimed it was. And I hope to be able to communicate that to you in this series of lectures. My lectures are going to cover 4,000 years of the history of mathematics. And there's no way I can do this in any kind of detail. I want to bring you right up to the 21st century. I want to share with you some of the exciting things that mathematicians are doing today. And so I'm going to have to treat much of this history of mathematics in a very superficial way, but I hope to be able to communicate some of the really big ideas. In looking at how to structure these 4,000 years going all the way back to the ancient Babylonians and Egyptians, I decided that the real pivot point occurs in the 17th century. And that's when we get 5 different threads coming together. And the threads are algebra and geometry and astronomy and mechanics, the way that physical systems interact with each other. And then the last of these is going to be the mathematics of motion. And we're going to see how different ancient civilizations developed these threads until by around the year 1600 they come together. We're going to see these threads coming out of the ancient Mesopotamians, the Egyptians, the Greeks. We're going to go to South Asia and see how the Indian mathematicians of the first millennium AD developed the ideas. We're going to turn to China and see how these ideas were further developed there, how the Islamic world took all of the different threads of mathematics that had been developed up until that time and really pushed them much, much further and laid the foundation on which Western Europe would be able to pick up these threads and continue to develop them, until by 1600 they were ready to be woven together. And I'm actually going to spend 5 entire lectures just on the 17th century because this is such an exciting time. As these mathematical ideas came to maturity and people began to see how they could interact, how you could weave them together. And the great master of weaving these threads together was Isaac Newton. He saw how to combine them in new and very important ways. And Newton's mathematical principles of natural philosophy, not truly a work of mathematics, it's really a work of physics or of science. It is explaining celestial mechanics. But in it, he shows how all of the mathematics that had been developed up to that point could be brought together and united into very exciting new mathematical ideas. And then beyond the 17th century, I will follow the development of mathematics, treating it very superficially now, just touching on a few of the points that I find most interesting, some of the people that I enjoy talking about the most. So the mathematics after the 17th century is going to be extremely personal. I'm going to share with you my own enthusiasms, my own excitements, and hopefully bring you up to the point where you have some idea of why it is so exciting to be a mathematician today. In this lecture, we're going to go back to the earliest recorded mathematics, going back almost 4,000 years to both ancient Mesopotamia and ancient Egypt. In both of these civilizations, at about the same time, we get the development of quite sophisticated mathematical texts. And we're going to be looking at these texts for the origins of the ideas of algebra and also the origins of the idea of approximating values. For Mesopotamia, we're looking at what's known as the Old Babylonian period, roughly about 2000 BC to around 1600 BC. In Egypt, we're looking at the early Middle Kingdom, also over approximately the same period. What was happening in both of these civilizations, both Mesopotamia in what today is modern Iraq, and also in Egypt along the Nile River Valley, is that both of these were getting very sophisticated civilizations that had highly developed systems of commerce. They were doing a lot of construction. They needed to train a large corps of civil servants, of bureaucrats, of people who could oversee taxation, who could oversee the building projects that were coming about at that time. And these were people who needed to be trained in basic mathematical techniques. And the mathematics that we have from this period are the textbooks that would have been used in order to train these people. So it's not mathematics the way we might like to see it, which is, where did they get these ideas? How did they develop these ideas? What we get are problem books, sets of problems, together with worked out solutions. These are problems that students would have worked on and tried to emulate. Now, the problem books that we have that come to us from Egypt are really quite limited. There really are only 2 of these books, but they're both quite complete, and especially one of them. We've got the Rhind Papyrus that was probably written around the 17th century BC. The name of the scribe who wrote it was Ames, and we do know that, in fact, that this was developed from or copied from a slightly earlier manuscript believed to have been written about 200 years earlier. It's quite complete. The actual papyrus roll that exists is about 13 inches high and about 18 feet long. There is one other important source for Egyptian mathematics from this period, and that's the Moscow Mathematical Papyrus that was probably written in the 19th to the 18th century BC. That exists today in the Pushkin State Museum, but unfortunately we only have a small piece of that papyrus. Only the top edge still exists. It's about the top 3 inches of it. but the whole papyrus is about 15 feet long. So we've basically got these two problem books that lay out the kinds of problems that civil servants in ancient Egypt were expected to be able to do. And what is very interesting is the way that the ancient Egyptians represented number. The way we represent number today is really quite sophisticated. What we do with number is we have 10 symbols, the 10 digits, 0 through 9. And if we want to represent a number that is larger than 9, we start reusing these digits, but we put them in places that carry this extra value. So, for example, the two digits 1 and 3 can be combined to 13, or we can also combine the two digits 1 and 3 into 31. And the 3 has a very different meaning depending on whether it's 1-3 or whether it's 3-1. In the latter case, 3-1, that digit 3 represents 30. It's 3 tens. And so we take these 10 digits and we put them in different positions in order to indicate how many tens we have, or how many hundreds we have, or how many thousands we have. The system that was used in ancient Egypt is a much simpler system, and it's based on the idea, first of all, starting out by representing a number by strokes, which is certainly the very oldest way of representing a number. So 1 is a single stroke, and 2 would be 2 strokes, and 3 would be 3 strokes, and 4 would be 4 strokes. We still see some echoes of this in our modern way of representing numbers, because the digit 2, for example, is really based on 2 horizontal strokes with a curve connecting them. And the number 3 is really based on 3 horizontal strokes with curves connecting them. Now, it becomes very cumbersome if you want to represent every number by strokes. And so what the Egyptians devised was a system by which, once they got up to 10 of these strokes, they would replace 10 strokes with a single symbol, what we call a yoke. So a yoke was a single symbol that would represent 10. Once you got up to 10 of these symbols for 10, then you would replace them by a single symbol referred to as a rope. And so it's simply a spiraling symbol. That meant you've got 100. So if you wanted to represent 317, for example, you would have 3 of the rope symbols, 1 of the yoke symbols, and 7 of the stroke symbols. And if you wanted 10 of the ropes, then that was represented by a lotus symbol that represented 1,000, and so on. This was continued up into 10,000 and 100,000. In addition to that, the Egyptians were able to work with simple fractions. What they did was to think of the reciprocals of the integers. And so if you wanted to represent 1/2, you would simply take 2 strokes and draw an oval over the top of them. And so that represented the reciprocal of 2, or 1/2. 1/3 would be 3 strokes with an oval over the top of it. Now you've got a problem here in that how do you represent a number like 3/4? Well, what the Egyptians would do is represent 3/4 as a half, so 2 with an oval over it, plus 1/4, so that would be 4 with another oval over that. And that really was sufficient for the kinds of uses of fractions that you get in ancient Egypt. The kinds of problems that they would work with, one of the examples from the Rhind Papyrus is that you've got a scoop and you've got a certain volume of wheat, a hekat, and the problem that was posed was it takes 3 1/3 scoops in order to equal 1 hekat. What is the size of a single scoop? And so this is one of the problems that these people who were training to be civil servants would practice. The ancient Egyptians were quite good in their work with geometry. They were able to find a lot of formulas for areas, for volumes. They knew the Pythagorean theorem. In the next lecture, I'm going to talk about Pythagoras. He lived in the 6th century BC. So the Pythagorean theorem is definitely much, much older than Pythagoras himself. In fact, it's clear that even by the year 2000 BC in Mesopotamia and in Egypt, people were very conversant with the Pythagorean theorem. They were using it in many different contexts, and so it must be much, much older than 2000 BC. And the Pythagorean theorem, the way to think about it is the way that really has been thought about throughout most of the history of mathematics. The Pythagorean theorem is really a theorem about areas. You take a right-angled triangle and you construct a square on each of the three sides. So you take the bottom side and construct a square on that. You take one of the other sides and construct a square on that, and you take the third side and you construct a square on that. And what the Pythagorean theorem says is that the areas of the two smaller squares, when added together, give you precisely the area of the large square. Now, today we know the Pythagorean theorem as the square of the length of one of the legs plus the square of the length of another leg is equal to the square of the length of the hypotenuse. But what's really going on there, when we use the word square, it should be taken literally. And that's the way people have thought about this theorem right up until very recent centuries, is a theorem about areas. Another of the problems that the Egyptians solved was that of finding the area of a circle. And the problem of finding areas of things that are not square regions or rectangular regions was always simplified into the problem of finding the side of a square whose area is equal to the given area. So this is a problem that would be stated not just by the Egyptians and the Babylonians, but also by Greeks and also by medieval and Renaissance mathematicians. The problem of squaring a circle. You've got a circle of a certain diameter, and you want to find the side of a square that has the same area as that circle. And one of the amazing results that the ancient Egyptians actually were able to come up with is the way to find the side of that square is to take the diameter of the circle and take 8/9 of that diameter. So you construct a square whose side is 8/9 of the original diameter, and that actually gives you an extremely close approximation to the actual area of the circle, an approximation that is off by less than 1 part in 100, certainly accurate enough for the kind of work that these Egyptian scribes needed to be able to do. Now, the situation in the ancient Babylonian kingdom in Mesopotamia was quite different from what was going on in Egypt at that time. As I said, from Egypt, we've basically got two sources. From Mesopotamia, we've got literally thousands of sources, but they are not complete texts. They are tiny fragments of texts. Because in Mesopotamia, rather than writing on papyrus scrolls, what the scribes did was to record information on clay tablets. So they would take a clay tablet and they would take a reed stylus and they would stamp marks in the clay tablet. And the clay tablets generally were fairly small, and so very often a clay tablet would just contain a single problem with its solution, or perhaps it would be a table of values, but you would not be able to get a complete math text. But we have thousands of these clay tablets that have survived, and so we've got a very good idea of what was happening in Babylonian mathematics at this time. I want to focus on two of those tablets because they give a good indication of the kinds of mathematics that the Babylonians were able to do. The first of these is known as Plimpton 322. Today it resides at Columbia University, and it's about 3.5 inches high, about 5 inches long, and it's believed to have been created about 1800 BC. And this is a tablet that deals with the Pythagorean theorem, and in particular it is looking at cases of the Pythagorean theorem where you can take the three sides of the triangle to all be integers. These are called Pythagorean triples. So this is three integers, such as 3, 4, 5, where 3 squared, which is 9, plus 4 squared, which is 16, 9 and 16 is 25, and 25 is a perfect square. Another example of a Pythagorean triple is 5, 12, and 13. Another example is 8, 15, and 17. And sometime back in ancient prehistory, people began, after studying the Pythagorean theorem and realizing what was going on there, to look for triples of integers that had this property. Now, what's amazing about Plimpton 322 is that it does not just find triples like 3, 4, 5 and 5, 12, 13, but among the triples that are contained on Plimpton 322 are 119, 120, and 169. If you take 119 squared plus 120 squared, that is equal to 169 squared. And it's very unlikely that anybody could find this just by chance. And if you've got any question about what's going on here, some of the other triples that occur on Plimpton 322 are 3367 and 3456 and 4825. Another triple is 4601, if I square that. 4,800, square that and add it to the first square. I'm going to get a perfect square, exactly 6,649 squared. So there must be something going on behind this. Unfortunately, for Plimpton 322, all we have is this table of values. We have no idea how it was created. And there's some fascinating mathematical detective work trying to figure out what else we can pick up from what other things we see on Babylonian mathematics to figure out how they might have come up with these triples. But clearly they must have had a general procedure for coming up with them. Now, this is a good opportunity to also talk about the way in which the Babylonians represented numbers. They started out in the same way that the Egyptians had. So they had a particular symbol, a vertical wedge, that represented 1, and 2 of these would represent 2, and 3 of them would represent 3, until they got up to 10, and then they had a new symbol for 10, and that was simply a wedge put on its side. So a sideways wedge, a horizontal wedge represented 10, and then you built up from there. But rather than going all the way to 100, the Babylonians stopped at 60. We're not exactly sure why 60, but my guess is it has something to do with the fact both that there are approximately 360 days to a year, and also the fact that 60 is a number that is divisible by many nice small integers. But they worked with 60, and then instead of coming up with a new symbol for 60, what they did was to reuse the symbol for 1. In the same way that when I'm writing 31, I reuse that 3 symbol, but in the tens place. So the Babylonians, instead of having a base 10 system based on powers of 10 as our modern numbers are, they had a base 60 system based on powers of 60. So if they would put a 1 in the 60s place, and that would then indicate that they had 60, and they could build up 60s, and once they got up to 60 60s, they would start over again with their symbol for 1, that would go into the place of 60 60s, and 60 60s is 3,600. So they would have a units place, they would have a 60s place, and they would have a 3600s place, and they could continue that. So, for example, the number 4,601, there is one 3,600 inside of that. You take out 3,600, you're left with 1,001. There are 16 60s in that. You take out the 16 60s, which is 960, and you're left with 41. So they would represent this number, 4,601, by 3,600, 16 60s, and 41 ones. The next piece of Babylonian pottery. The next mathematics that I want to talk about is called YBC 7289. It's a rather unromantic name, but that happens to be its designation from the archaeological dig that it was discovered in. It exists today at Yale University. It probably dates from between 1800 and 1600. And what's going on this particular piece of mathematics is that the Babylonians are representing the square root of 2. We consider a square, and we look at the diagonal of the square, and the problem that they're really wrestling with is if I take the length of that square as my unit, how many times can I measure off the length of that square against the diagonal? Well, you try to measure off the length of the square against the diagonal, and you realize that it goes in once and it's not going to go in twice, so there's a piece left over. How big is that piece? And what they did then was to take their unit and break it down into 60 subunits, so 60ths of their basic unit. This idea of taking their units and breaking it down into 60ths, incidentally, is something that we still have with us today. The fact that we break an hour down into 60 minutes and a minute down into 60 seconds comes directly to us out of the Babylonian way of dealing with fractions. So the Babylonians would deal with 60ths, and if you take the piece on the diagonal that's left over, it's about 24 60ths. But not exactly. You can get 24 60ths, and then there's a little piece left over. And on this clay tablet, what the Babylonians did was take their 60ths of a unit and break it down into 60ths of 60ths. And they saw that there were about 51 of these 60ths of 60ths, but there was a little piece left over. And they then analyzed the little piece that was left over, and they found that there were about 10 60ths of 60ths of 60ths. Now, you're not going to be able to do that by actually measuring. In fact, you really can't get much beyond just 60ths of a unit. So there had to be some very sophisticated algebra that was sitting behind what the Babylonians were able to do in order to get this approximation to the square root of 2 so very accurately. The approximation that they came up with was that the square root of 2 is approximately 1 plus 24 60ths, plus 51 over 60 times 60, plus 10 over 60 times 60 times 60, which in our modern decimal representation is approximately 1.414213. This is incredible accuracy. The Babylonians were able to get the square root of 2 down to an accuracy of less than 1 part in a million. Now, not only did they deal with this question of how to find approximations, there also is a lot of algebra that is contained in the old Babylonian clay tablets. It's not algebra the way we think about algebra today. And in fact, one of the big themes that we'll be following through this series of lectures is how algebra actually did develop. But it's very instructive to look at the way that the Babylonians viewed algebraic problems, because that's the way the Greeks would look at it, it's the way that the Indians would look at it, it's the way that the Chinese would look at it. It really is not up until about the year 1000 AD that we begin to get algebraic notation and algebraic ideas that really are connected to our modern way of thinking about algebra. But the kinds of problems that the Babylonians looked at were very algebraic. And one of the problems that is contained on one of the Babylonian tablets is the following. You've got a square of unknown side, and we want to add to that the length of that square, and the value is 3/4. What is the length of the square? Now, today, the way we would set that up is with an algebraic equation. We would say x squared plus x equals 3/4, and we would solve it algebraically. But the algebraic notation did not exist at this time. What the Babylonians did was to think about this problem geometrically. You've got a square. You've got a certain length that is equal to that square. Let's create a second area to add to the square. We'll create a rectangle whose height is equal to the length of the square and whose width is 1 unit, so that the area of this rectangle is exactly equal to the length of the original square. So in our modern algebraic notation, if we think of the side of the square as being x by x, then our rectangle is x high and it's 1 unit wide. And the method of proof is exactly equivalent to the way we would solve this problem algebraically today. What the scribe is told to do is to take that rectangle and break it in half. So you get 2 rectangles, each of height this unknown quantity, and each of width exactly 1/2. We take one of those rectangles and we slide it underneath our square. So now I've got my square. I've got a rectangle over here of width 1/2 and height equal to the height of the square. I've got another rectangle underneath the square whose width is equal to the length of the square and whose height is equal to 1/2. And now we complete the square. And completing the square for the ancient Babylonians, for the Greeks, again, right up until relatively recently, is filling in the missing area on an actual geometric square. So we want to fill in that little missing piece that's down in the corner. And we know exactly how big that little piece is. It's exactly half a unit high and half a unit wide, and so its area is equal to 1/2 times 1/2, which is equal to 1/4. That tells us that if I add an area equal to 1/4 to my existing area, I'm going to get an exact square. An exact square, well, I knew that the area originally was 3/4. If I add an area of 1/4, that now gives me an area of 1, and so my entire square has area 1. Well, it's easy to determine what the side of that square is. It must be a square of side 1. But I know that the side is also equal to the unknown side of the original square plus 1/2. And that tells me that the original square must have been half a unit by half a unit. Now that's exactly what we do algebraically today. And this is one of the reasons in the first lecture why I talked about the power of looking at the history of mathematics, because teaching students how to solve a quadratic equation by completing the square suddenly makes a lot more sense if you're actually able to think about it geometrically and not think about completing the square as some abstract operation, but actually as taking a geometric square and filling in the missing piece. And once you understand what's going on geometrically here, you can then take that idea and see how to encode it in the algebraic notation. But it would take 3,000 years before these problems of solving quadratic equations got encoded in the kind of algebraic notation that we are familiar with today. I've been looking at Babylonian mathematics and Egyptian mathematics basically in the period 2000 to 1600. I've been looking at the kinds of texts that were being used to train the scribes, to train the civil administrators. You do not get a lot of mathematics. You get some mathematics after 1600 BC. But the sources are not nearly as rich as they had been before, and to some extent, much of the mathematics goes underground at this point. Much of the mathematics in Babylon and Egypt is taken over by the priestly castes, who are using mathematics for astronomical observations. I'm going to wait until Lecture 5 before I really begin to look at astronomy and its effect on mathematics in any detail. But one of the things that's important to remember is that the mathematical tradition continues both in Mesopotamia and Egypt. We have every reason to believe that it becomes much deeper and richer largely because we know that it has direct influence on what would come into being in the Greek world starting in about the year 600 BC. But it does become secret knowledge. This ability to understand what was going on in the heavens was understood as a way of predicting what was likely to happen on earth. After all, the position of the sun in the heavens certainly has great influence on what's going on the earth. And so very likely the position of the planets, the position of the moon, should also have an influence on what's going on. And this then would become secret knowledge. In Mesopotamia, these mathematicians, astronomers, astrologers would come to be called magi. And the magi who visit the infant Jesus in the Christmas story are mathematicians, Persian mathematicians from Mesopotamia, who have seen a star and have realized the astrological implications of the star that they saw and follow it. And so we get mathematicians appearing in the New Testament. In the next lecture, we're going to jump ahead 1,200 years to about 600 BC, and we're going to see how the Greek mathematicians of that time picked up the ideas that they inherited from Mesopotamia and from Egypt, and then developed that mathematics in very new and very important directions. In the last lecture, we looked at the early developments of mathematics in Mesopotamia and in Egypt. With this lecture, I'm beginning a series of 3 lectures that look at Greek mathematics. And the Greek world, the Hellenic and Hellenistic worlds would dominate mathematical development for basically 1,000 years, from about 600 BC until around 400 AD. I'm going to focus in this lecture on the first 300 years, from about 600 right up until around 300, and something very important happens around the year 300, and that is when Euclid of Alexandria writes his great books. He's best known for the Elements, which is often considered to be a work of geometry. It actually has much more than geometry. It really covers much of the mathematics that was known at that time. And between the Elements and the other books that Euclid wrote, they really cover everything that was known in the Greek world. And for that reason, nobody bothered to keep any of the earlier Greek texts in mathematics. Euclid was so successful in summarizing what everybody else had done that there was no point in keeping what anybody else had done. Incidentally, it's not clear how much of the mathematics in the writing of Euclid really was his own. There are some people who believe that he did not discover any mathematics by himself, that none of the theorems in Euclid's work really are original to him. There are other people who do argue that certain pieces of it he must have been the first to come up with. But what is significant about Euclid's Elements, written around 300 BC, is that they do summarize what was known before, and they set the foundation for everything that would come afterwards. The earliest of the Greek mathematicians that we know something about is Thales of Miletus. He was born in the late 7th century and then would go into the 6th century. Thales was interested in a number of problems related to finding distances between objects. We know that Thales studied with the Egyptian mathematicians, that he picked up much of their mathematics. He did learn astronomy from them, and it's been recorded that he predicted the eclipse that occurred in the year 585. It's also been recorded that he was able to calculate the height of the pyramids. He would have used similar triangles in some way. It's also been recorded by Plato that Thales came up with a way of determining the distance that a ship is offshore. If you've got 2 different points on the shoreline and you're able to observe the ship from both of these points, you can then do a geometric argument that enables you to determine the distance out to the ship. Plato also records one of the events that apparently happened to Thales, and it illustrates the concept of the absent-minded mathematician. Thales apparently one night was walking along studying the stars when he fell into a ditch, and a young servant girl who happened to be nearby pulled him out and asked him, "How is it possible for you to understand what is going on up in the sky if you do not even see what is at your feet?" Thales of Miletus sets an important example for Greek mathematics because of his fascination with the idea of distance, calculating the heights of the pyramids, figuring distances out to a far ship. You're using geometric ideas, and certainly the other kinds of ideas of mathematics will appear within the Greek tradition. There is a lot that is built on problems of commerce, problems of taxation, as well as astronomy. But it's these geometric problems that really will come to dominate Greek mathematics. And we're going to see that in a very large dependence on the idea of ratio and proportion. So ratio, taking the ratio of two integers, so one integer divided by another, and working with those ratios of numbers. Very often, instead of working with pure numbers, what the Greek mathematicians would do is to work with ratios. And we see this particularly strongly in the work of Pythagoras of Samos. Pythagoras was born sometime around 580 BC. Samos is just a stone's throw from Miletus, and it is believed that at the very least he probably met Thales. There is a tradition that he may actually have studied with Thales, but we do know that Pythagoras learned much of his mathematics by traveling to Egypt, and he actually was indoctrinated into many of the mystic practices of the Egyptian astrologer priests. He learned a lot of the Egyptian astrology or astronomy or mathematics at this time. He happened to be in Egypt at the time that Cambyses of Persia conquered Egypt, and Pythagoras was taken back to Babylon by Cambyses, and he took advantage of this. There was still a very strong mathematical tradition in Babylon at this time, and according to the tradition, Pythagoras learned a great deal of the Babylonian mathematics, the Babylonian astrology or astronomy at this time. After leaving Mesopotamia, after leaving Babylon, Pythagoras went to Italy, and there he founded his own school, what became known as the Pythagorean school, or sometimes the Pythagorean cult, because he really adopted many of the cult practices, both of the Egyptian and also of the Babylonian or Mesopotamian mathematicians. He set up a group that was very mystical, very secretive. We don't have many details of exactly what was going on in this group, but we do know, certainly according to tradition, that Pythagoras believed that mathematics lay at the core of all nature. The quote that Plato ascribes to him is that at its deepest level, reality is mathematical in nature. There certainly were cultish aspects of the Pythagoreans. They followed the Egyptian priests' practice of never eating beans, never wearing leather, but they also were clearly interested in developing the mathematics, and in particular developing mathematics built around ratio and proportion. And so music and the musical scale, which is very much built on ratios, is something that is generally attributed to the Pythagoreans. There are developments in architecture and the kind of proportions that you should have as you design buildings that is often attributed to the Pythagoreans. And of course, the Pythagorean theorem is often attributed to them. As we know, the Pythagorean theorem is much older than the Pythagoreans, but in fact, they appear to have been the first people to actually come up with a proof of the Pythagorean theorem. This is more than an observation. that the areas of those two squares on the legs is equal to, when you add those two areas, it's equal to the area of the square on the hypotenuse. That according to tradition, it's the Pythagoreans who actually came up with a proof of this fact. The Pythagoreans are also credited with coming up with the idea of an irrational number, that there are numbers that cannot be represented using fractions. They cannot be represented using a ratio of two integers. And the first example that we know of this case is the square root of 2. The square root of 2 is about 7/5, but it's not exactly 7/5. And in fact, you cannot find a fraction that's exactly equal to the square root of 2. We don't know when this was first proven. It is often attributed to Pythagoras himself. And one of the stories that is out there is Pythagoras discovered this fact, and there was a great feast among the Pythagoreans. Another one of the traditions is that it was one of Pythagoras' disciples who discovered this fact, and there was a great celebration that was experienced around this. And a third tradition is that it was one of Pythagoras' disciples who discovered that the square root of 2 was not a ratio, that it could not be represented as a ratio of two integers. And Pythagoras was so disappointed and upset at this revelation that he banished this disciple from among the Pythagoreans. The next mathematician I want to look at is Zeno of Elea. This is in what today is Italy. He's a 5th century mathematician, and he's best known for his paradoxes. He was interested in this whole question of what it means to consider all possible distances and assign a number to any possible distance. It's what today we refer to as the continuum. Does every single point between here and over there actually correspond to some number? If it does, then you start to get some paradoxes coming in. I want to focus on just one of them because it's going to be important later on when we get to calculus. And that is the problem if you consider an arrow in flight and you look at how fast it's traveling. That's its velocity. And you can determine the velocity by looking at how far it travels and how long it takes to get there. So the distance that it travels divided by the time that it takes to get there is its velocity. Well, if every single point between here and the end point of the arrow's trajectory is a number, we can think about what's happening to the arrow when it reaches a specific point. When it reaches a specific point in time or in distance, what's going on there? Can we assign a velocity? Well, it seems to Zeno that we can't possibly assign a velocity because if we're looking at the arrow at one instant, it doesn't travel any distance. And if it doesn't travel any distance, it can't possibly have a velocity. So at any instant in time, the arrow is not moving. But to get from here to there, we've got to pass over the continuum. We've got to pass over every single point. And at each point, the arrow is not moving. And if at each point the arrow is not moving, how does it succeed in getting from where I shoot it to where it lands? That's one of Zeno's paradoxes, and it would take a long time to really begin to grapple with this. Aristotle, in the 4th century BC, would be one of the people who attempted to work with Zeno's paradoxes by essentially banishing them. What Aristotle did was to separate mathematics into those numbers that are proportions and deciding that we could work with them, and then the continuum that also contains these strange numbers like the square root of 2 that cannot be represented by a ratio, and simply put them into a whole nother category. There are other separations that Aristotle makes that turn out to be very significant for the development of mathematics. And one of those is the difference between arithmos and logos. Arithmos is the origin of our word arithmetic, and so Aristotle is looking at basic arithmetical calculations, the kinds of calculations that would be used by people doing commerce or that would be used by the scribes and the civil servants. versus the kind of logical mathematical argument, the close reasoning that I talked about in the very first lecture, and that he referred to as logos. And logos is an interesting word. It literally means word. And in the ancient Greek world, this word logos carried many, many different meanings. And in fact, in the opening lines of St. John's Gospel, we have the word logos used, and arche ino logos. In the beginning was the word, but you could interpret that to refer to Aristotle's sense of logos. In the beginning was logical mathematical reasoning. I don't think that's quite what St. John had in mind when he wrote this, but it's interesting food for thought, and it certainly fits into much of the Greek tradition, and especially the tradition of the Pythagoreans. The next mathematician that I want to look at is Theaetetus of Athens, born around 417 BC, died around 369 BC. He was a friend of Plato. He was at the Academy in Athens. Theaetetus did a number of important things that would be reflected in the work of Euclid. In particular, Theaetetus is considered to have been the mathematician who finished the description of what today we call the Platonic solids. They are named for Plato, but they certainly do not come from Plato. So these are solids that have faces that are flat, and the faces are all regular polygons. So, for example, a cube is a simple example of a Platonic solid. So each of the sides of a square, each of the sides of a cube is a square, so a regular four-sided polygon. There are other examples of Platonic solids. There is the tetrahedron that has four sides. Each of the sides of a tetrahedron is an equilateral triangle. Another example is the octahedron that is made up of 8 triangles. And there is the dodecahedron that is made up of 12 pentagons. There is another Platonic solid. The tradition in Greek mathematics was that the Platonic solids came from the Pythagoreans, but almost certainly the last of these was not known to the Pythagoreans. Almost certainly it was originally discovered by Theaetetus, and that's the icosahedron. And this is a solid that is made up of 20 triangles. So the faces of this solid are made up of equilateral triangles. Something else that Theaetetus did was to work with the question of how do you recognize a rational number? One of the problems that we have when we're working with rational numbers is that you can have two very different appearances to the same rational number. Thus, 3/4 is the same as 6/8, which is the same as 12/16. Now, in those cases, it's easy to see that they are all the same fraction. But what if you've got a more complicated fraction like 119 divided by 91? What's the simplest way of expressing that? And it's not clear if this idea originally comes from Theaetetus, but he certainly exploited this. And this is the idea, if we're thinking about the fraction 119 divided by 91, to first look at what's the largest integer in that. The largest integer in that is 1. How much is left over? 28 over 91. Now, once you take out the largest integer, whatever is left over is going to have to be a number between 0 and 1. Let's take its reciprocal. Instead of 28 over 91, we look at 91 over 28 and find the largest integer in that. 28 goes into 91 3 times. What's left over is 7 over 28. Let's repeat that process and take the reciprocal of 7 over 28. That's 28 over 7, and 7 goes exactly into 28 4 times. If you start out with a rational number and you do this process, take out the largest integer, look at what's left, take its reciprocal, take out the largest integer, that's going to stop after a finite number of times, and you can now redo this process. The integers that we got were 1, 3, and 4, and we can back up. Start with 4, take its reciprocal and add 3 to that. That gives us 13/4. Take its reciprocal, 4/13, and add 1 to that. That gives us 17/13. And that gives us the original pair in their reduced form. 119 over 91 is equal to 17 over 13. This is what would come to be known as the Euclidean algorithm. And what Theaetetus realized was that he could prove that the square root of 2 was not equal to a rational number by showing, and this is a geometric argument that unfortunately I don't have time to go into, but he used a geometric argument in which he showed that if you take the side of a square plus its diagonal and ask how many times does the side of the square go into that, well, it goes in 2 with a little bit left over. And geometrically, Theaetetus was able to show that if you take that little bit that's left over and you look at its reciprocal, that's exactly the number of times that the side of a square goes into the side of the square plus its diagonal. So that if we're trying to take the side of a square plus its diagonal, 1 plus the square root of 2, that's equal to 2 plus a number whose reciprocal is what you started with. 2 plus 1 over, 2 plus 1 over, 2 plus 1 over, 2 plus 1 over, and so on. This continues forever. It never terminates. This cannot be a rational number. Incidentally, this gives you a very accurate way of approximating the square root of 2, is to work this process backwards. Start with 2, take its reciprocal and add 2. 2 plus a half is 5 halves. Take that reciprocal and add 2 to it. That gives you 12/5. Take its reciprocal, 5/12, and add 2 to that. That gives you 29/12. Take its reciprocal and add 2 to that. That gives you 70/29. Take its reciprocal and add 2 to that. You get 169 over 70. And I hope you see how you can continue this as long as you want and get as accurate as you want. But if I take 169 over 70, that accurately measures 1 plus the square root of 2 to an accuracy within 1 in 34,000. And you can quickly get whatever accuracy actually is needed. The next Greek mathematician I want to look at is Eudoxus of Cnidus, also someone who was at the Academy in Athens. He was born sometime between 395 and 390 BC. Eudoxus of Cnidus was interested in this question of how do you define an irrational number? If you've got a number like the square root of 2, we've seen how Theaetetus was able to take the problem of when are two rational numbers equivalent to each other and working out a procedure for deciding that. And what we're looking at here with Eudoxus of Cnidus is how do you decide if two irrational numbers are the same? And he came up with a brilliant idea that actually would be adopted in the 19th century of the modern era by Richard Dedekind, that we'll be talking about much later. The way to compare two irrational numbers and decide if they really are the same number is to look at the rational numbers that are larger than each of them. And if every rational number that's larger than this irrational is also larger than the other one, and if every irrational number that's smaller than this is also smaller than the other one, then the two irrational numbers have to be the same. This is an idea that Euclid would pick up, and he would use as an important foundational aspect for studying all numbers, whether they are rational numbers, in which case he would explain what we call the Euclidean algorithm for deciding when two rational numbers are the same, or for comparing the size of irrational numbers. Eudoxus of Cnidus is also important for his work on areas and volumes, and he is credited with being the first mathematician to really work out how to take this problem of finding the area of an irregular region, or taking the volume of something that's not just a rectangular solid, and approximating the area by chopping it up into little rectangles or little rectangular blocks. And so this is a method that would come to be known as the method of exhaustion. Euclid describes it in his writings, And in the next lecture, I'm going to talk about how Archimedes of Syracuse really refined this idea and turned it into a very powerful way of working with the problem of finding areas and volumes. Euclid of Alexandria is a shadowy figure. It's generally believed that he lived roughly from 325 to 265 BC. But the fact is, not only do we not know when he was born or when he died, we don't even have any definitive proof that he ever existed. There is no contemporary who wrote about him. There is a reference in one of the works of Archimedes, but a lot of the scholars believe that that was a later addition. We don't get the first biography of Euclid until 750 years after he lived. However, there is a body of mathematical work that was written around the year 300 BC that clearly was all written by the same person. It's in the same voice with the same kinds of ideas and the same logical development. Somebody must have done this writing, and we might as well believe that it is the person to whom it's attributed, this Euclid of Alexandria. Now, Alexandria is a city that had been founded after the death of Alexander. The first ruler of Egypt following the death of Alexander was Ptolemy I, and he built a center for scholars, what was known as the Musaeon. This was a temple to the Muses. It's the origin of our word today, museum. And the Musaeon was set up by Ptolemy I in the last years of the 4th century BC to be a center for scientific work, for scholarly work. And there was a group of mathematicians who were pulled together at the Musaeon, and Euclid almost certainly was the person who was leading this group. And his job was to take the mathematics that was around him and condense it, explain it. And while we're not sure how much of this mathematics was original to Euclid, what was very original to Euclid was the way in which he was able to explain the mathematics and put it on a very logical foundation. Euclid clearly made important choices about what needed to be defined and how it would be defined, what needed to be taken as a postulate or assumption or axiom, and how these then would be structured into proofs. Euclid was one of the greatest teachers to have ever existed. Euclid should be thought of as a great textbook writer. And that's really what's going on here. He is taking ideas, most of which existed in Greek mathematics before his time, and he is organizing them in an incredibly effective way. Euclid's Elements is still a textbook that is used today. It has gone through well over 1,000 editions in many, many translations. And it's made up of many books. It's usually, when you think of Euclid's Elements, you think of geometry, and the first 4 books of Euclid's Elements really are devoted to geometry. But there's much other mathematics that's going on here in addition to that. Books 5 and 6 deal with ratio and proportion. Those books are also looking at similarities in geometry. Books 7 through 9 look at number theory, and here is where Euclid explains this Euclidean algorithm that really comes to us from Theaetetus, or possibly even earlier than that. Euclid looks at sums of geometric progressions. This is where Euclid proves that there are infinitely many prime numbers. So a prime number is one that is only divisible by 1 and itself among the positive integers. And Euclid proves that, in fact, there are infinitely many such primes, 2, 3, 5, 7, 11, 17, and so on. Book 10 of the Elements looks at the meaning of irrational numbers. And here is where he picks up this idea of Eudoxus of Cnidus on how to define an irrational number. And Book 10 talks about how to compare various kinds of magnitudes. And chapters 11 through 13 look at solid geometry. He explains Eudoxus's method of exhaustion, how to find areas and volumes of irregular objects. He explains how to construct the Platonic solids. And he goes well beyond that. He doesn't just explain what the Platonic solids are. He actually proves that these are the only ways that you can construct a solid so that all of the faces look exactly the same, and that all of the faces are in fact regular polygons, but polygons in which all of the sides have exactly the same length. There's much else that Euclid wrote. He also wrote 2 other books on geometry. We still have some pieces of those, one called Data, one called On Divisions. He wrote one of the first books on optics, and in that book we find the very first recorded treatment of the question of perspective. Another one of Euclid's books is a book on astronomy called Phenomena. And there are several other books that people recorded that Euclid had written, but unfortunately which no longer exist. There is one book on surface loci, so this would be 2-dimensional curves. There's another book with an intriguing title, Porisms, and people are not quite sure what is meant by a porism, but from some of the examples that other people make of the kinds of results that Euclid stated in this book, these appear to be results that can easily be deduced from other theorems that he proved. Most of the porisms are geometric results that follow from the main theorems that Euclid proved in the Elements. There is also a book on conics. There is a book that's called the Book of Fallacies, and he had at least one book on music. For the next time, we're going to look at the following 700 years of Greek mathematics, from the time of Euclid right up until about 400 AD. We're going to focus in particular on Archimedes. We'll also be looking at Apollonius, Diophantus, and the first recorded woman in mathematics, Hypatia of Alexandria. In this lecture, we're going to be looking at Hellenistic mathematics. The last lecture ended with Euclid of Alexandria sometime early in the 3rd century BC. We're going to pick up there and continue right through until 400 AD. This lecture and the next lecture are going to be separated. In the next lecture, I want to put all of the work on astronomy. And so this lecture is going to focus on 700 years of Hellenistic mathematics, but without any mention of the astronomical work that would be done. As I mentioned in the last lecture, it was Ptolemy I who established the Museion in Alexandria, in what today is Egypt. And this would become a center for mathematical work actually for the next 700 years. Aside from Ujjain in India, there probably is no other place on Earth that has been a center of important mathematical activity for such a long stretch of time. Ptolemy's successor, Ptolemy II, would go on to build a great library that would be there to support the Museion. And his successor, Ptolemy III, then would make a point of really building that library up into the greatest repository of books anywhere in the world. And in fact, there are many stories of people being pressed into loaning copies of their manuscripts so that they could be recopied. Anyone who traveled to Alexandria and was taking a book, a scroll with them, was required to loan this scroll to the library. And sometimes, if it was a very valuable scroll, the scroll would not be returned to the person that it was taken from. Rather, they would have to leave with a copy of the book that they arrived with. We also know that Ptolemy III did get in contact with many of the other of the rulers of the Eastern Mediterranean and aggressively went after books from other sources. One of the first mathematicians to follow Euclid in the Museion was Eratosthenes, originally from Cyrene. Born around 276 BC, he would die around 194 BC. In addition to being a mathematician, he was the third librarian of the great library in Alexandria. And he did a number of very interesting mathematical accomplishments, one of which is to find a general method for finding all of the primes below a given number. So, for example, if you want a list of all of the primes less than 1,000,000, there are about 78,000 of them. There is an algorithm or procedure that Eratosthenes came up with called the sieve of Eratosthenes, which is a method of generating all of the primes. And even today with our powerful computers, the kind of procedure that these computers use in order to find all of the primes below a given number, such as the primes less than 1,000,000, rely on the idea behind Eratosthenes' sieve. Something else that Eratosthenes accomplished was to measure the circumference of the Earth. Now, it was known in ancient times that, in fact, the Earth is round. It's a common myth that people right up into the Middle Ages believed that the Earth was flat. In fact, they were quite aware of the fact that it was round. One of the arguments for knowing that it was round is the fact that as a ship sails out to sea, you see the bottom of the ship disappear first, and the mast is the last part of the ship to disappear because it's disappearing over the curve of the horizon. But there's an even more immediate way of seeing that the Earth must be round, and that's by looking at a lunar eclipse. A lunar eclipse happens when the Earth comes between the sun and the moon, and so the shadow of the Earth is projected onto the moon, and you only have to look at that shadow to see that it's round. The Earth has to be round. And if it is round, then the question comes up, how large is the Earth? And this is a question that Eratosthenes wrestled with, and he came up with a very ingenious way of figuring it out. It's known that the sun is so far away from the Earth that the rays of the sun hit the Earth essentially as parallel lines. And so what you can do is find a place where the sun is directly overhead at a certain time of year, and then find another place a certain distance north of that, and figure out the angle that the sun's ray makes at that northernmost point, at that more northern point, and compare that angle to figure out that distance, what angle of the total circumference of the Earth is being measured here, and use that to extrapolate the circumference of the Earth. Eratosthenes actually did this. What he did was to dig wells, one in southern Egypt and another one near Alexandria. He chose a time when the sun was directly above the well in southern Egypt and looked at the shadow, the angle that the sun made with the well near Alexandria. He was very lucky in being able to accurately measure the distance between the two wells and came up with a measurement of the circumference of the Earth that essentially is right on. He came up with something between 24 and 25,000 miles, or the equivalent in the units of that time, of something between 24 and 25,000 miles, which is what the circumference of the Earth actually is. One of the problems, of course, is that there were lots of people who were estimating the circumference of the Earth at this time. Eratosthenes' estimate was one of many estimates that were out there, and an independent observer didn't have any good way of knowing which one was correct. It wouldn't be known until much later that, in fact, Eratosthenes had been correct. I want to spend most of my time in this lecture at looking at one of the friends and colleagues and contemporaries of Eratosthenes. This is Archimedes of Syracuse, certainly the greatest of all of the mathematicians of the Greek world. He was born around 287 BC, died in 212. He was noted as an engineer. He is credited with inventing the hydraulic screw. We know that he went to Egypt, that he did spend some time in Alexandria, and the tradition there is that he invented the hydraulic screw. So this is a screw mechanism that can be used to lift water, and he invented it for use in Egypt. He probably did not invent the block and tackle, but he certainly understood the principles behind the block and tackle and was very instrumental in developing this idea. he also discovered the power of levers. And he is famous for his quote, "Give me a place to stand and I will move the earth." If you've got a fulcrum point and you've got a long enough lever, somebody who is as puny as a mere human being actually is capable of moving an object as large as the earth through the mechanical advantage of using a lever. Archimedes also turned his attention to vehicles, to machines of war, catapults in particular. Burning mirrors are something that he is credited with inventing. Certainly Archimedes was very much involved with optics, with the properties of mirrors. The tradition is that in 214, when Marcellus, the Roman general, was attacking Syracuse, one of the defenses of the city that Archimedes came up with was to line up soldiers with polished mirrors that he would focus on the ships and set them ablaze. Almost certainly this didn't happen, and an interesting item of debate today is whether this is even possible. Some people argue that it is not possible. Others argue that if he got things just right, there are ways in which he might have been able to succeed. But one of the important points is that Archimedes was well known to the Romans as somebody who was extremely inventive. And it is said that the Roman soldiers were so terrified of these engines of war that Archimedes was inventing that all the defenders of Syracuse had to do was to drape a little piece of rope over the parapet, and the Roman soldiers would assume that Archimedes was about to unleash some terrible new weapon and they would flee in terror. The Romans would eventually conquer Syracuse in 212. And it was again the Roman general Marcellus who was leading the Romans when they did conquer Syracuse. Marcellus was well aware of Archimedes, and he greatly valued the contributions that Archimedes was making, even if he was working for the people in Syracuse who were his enemy. And the story is that Marcellus sent one of the soldiers to go and find Archimedes and bring him safely back to the Roman camp. And that the Roman soldier misunderstood the order, simply that he was supposed to bring Archimedes back. And the story is told that the soldier came to the house of Archimedes, general chaos going on in the streets around him as the soldiers were entering the city and pillaging and burning the city. And the soldier came up and he discovered Archimedes deep in a mathematical piece of work. Archimedes, and there is a mosaic that shows this, Archimedes was doing his calculations on a sandboard, which is probably the way he really was doing calculations at that time. So you wouldn't want to waste valuable papyrus or other writing surface in order to put something indelible if you were just doing mathematical calculations. So you would write them with your finger on a board that was covered with fine sand, and once you found your answer, then you could wipe it out and reuse the sandboard again. And so the soldier finds Archimedes deep in his mathematical calculations. He orders him to follow him. Archimedes says, "No, let me finish these calculations first." And the soldier, who believes that he must get Archimedes back without delay, kills him on the spot, rather unfortunately. And so that is the death of Archimedes. I've described Archimedes as a great engineer, and certainly that is where he made much of his reputation at the time. But he has also left a very important mathematical legacy. And in fact, we've got an indication that it was the mathematics that was most important to Archimedes, because Archimedes had asked that on his tomb there be erected a sphere contained within a cylinder. And this refers to Archimedes' calculation of the volume of a sphere, which he considered to be his greatest work. And in fact, we do have independent confirmation. Cicero visited Syracuse in the year 75 BC, and he found the cemetery where Archimedes was supposed to be buried, and in fact, he did find this tomb of a sphere inside a cylinder. The result that Archimedes found is not the usual way we have of stating the formula for the volume of a sphere. We remember that formula, if you've been taught it in grade school, as 4/3 pi r cubed. So 4/3 times pi times the cube of the radius. The way Archimedes stated this was that the volume of the sphere is 2/3 the volume of the cylinder. So if we put a sphere inside a cylinder so that the circumference of the sphere exactly matches up with the circumference of the cylinder, and the height of the sphere is equal to the height of the cylinder, it's easy to work out the volume of the cylinder. The volume of the cylinder is the area of the base, which is pi r squared, times the height of the cylinder, which is the diameter of the sphere, which is 2 times r. So you take the base, pi r squared, times 2r, and you get 2 pi r cubed for the volume of the cylinder. If the sphere is 2/3 the volume of the cylinder, then the sphere is 2/3 times 2 pi r cubed, which is 4/3 pi r cubed. But the way the ancients thought about the volume of the sphere is that it was 2/3 the volume of the cylinder. Archimedes worked this out. He worked it out using the method of Eudoxus of Cnidus, this method of exhaustion that Euclid had talked about, taking this volume and breaking it down into thin slices. You can find the volume of each of the thin slices and then approximate the volume of the entire sphere by adding up the volumes of the thin slices and seeing what that number approaches as you take progressively thinner slices of the sphere. This is the idea behind integral calculus. Integral calculus, really at its heart, has the problem of finding areas and volumes, and it works by precisely this kind of slicing mechanism that was first introduced by Eudoxus, later developed by Euclid, and really perfected by Archimedes. And it's not too much of a stretch to say that Archimedes understood integral calculus. Now, when we get to the 17th century, we will see that all of calculus involves much more than being able to find areas and volumes. But this basic idea is something that Archimedes really understood. Something else that he was able to do is to find a way of approximating pi essentially to arbitrarily high accuracy. So remember that pi is the number of times that the diameter of a circle is used to measure off the circumference of a circle. The diameter goes around the circumference 3 and a little bit, and the number of times the diameter goes around the circumference is this number we refer to as pi. Incidentally, the use of that particular letter, the Greek letter P, for perimetros is something that would be introduced in the 18th century of the modern era. Before then, people did not use this Greek letter pi to represent the ratio of the circumference to the diameter of a circle. But nevertheless, people were interested in this ratio. And Archimedes began by considering a hexagon, a 6-sided figure, that fits precisely into a circle. And if I've got a hexagon, a 6-sided figure, it's made up of 6 equilateral triangles. And that means that the circumference of the hexagon is 6 times the radius of the circle, or in other words, it is 3 times the diameter. If I start out with a 6-sided figure, a regular hexagon, in my circle, its circumference is going to be exactly 3. And what Archimedes succeeded in doing is figuring out if I've got a polygon that sits inside a circle, a regular polygon, all of the sides have the same length. He figured out how to take that polygon and double the number of sides and find the relationship between the new circumference and the old circumference. So once he knew that a hexagon inside this circle has a circumference of exactly 3, he was able to work out the circumference of a 12-sided regular polygon. And from there to 24 sides, and from there to 48 sides, and from there to 96 sides, and he was able to measure pi accurately to about 3 digits. About 3.14 comes out of recognizing that pi can be approximated with this 96-sided regular polygon. Archimedes could have gone further with that, but he chose to stop at that point. The next mathematician I want to talk about is Apollonius of Perga, born sometime around 260 BC. And the big contribution that I'm going to talk about today from Apollonius is his work on conic sections. As I mentioned in the last lecture, we know that Euclid wrote a book on conic sections, but we don't know what he said about them. And all of our evidence of what was developed in Hellenistic times about conic sections comes from Apollonius. Incidentally, we're going to encounter Apollonius again in the next lecture because he also has important contributions that he made to astronomy. But what he was looking at is conic sections. So these are curves that can be obtained by slicing a pair of cones. So I take a pair of cones that meet point to point, and I consider what happens as I slice through these cones. If I make a horizontal slice through one of the cones, I'm going to get a circle. If I tip that plane that slices through the cone slightly, it's going to elongate my circle, and I'm going to get an ellipse. So a circle that's simply elongated along the axis in the direction in which I'm slicing by this plane. As I move the plane up to an ever steeper angle, my ellipse gets longer and longer and longer, until finally I take a plane which is actually parallel to one of the sides of the cone, so that the plane comes in, hits the cone, and then never leaves. And what happens is that my ellipse stretches out so far, and then suddenly it opens up at one end, and I get a parabola. If I now continue tipping that slicing plane, if I tip it just a little bit more, it's now going to intersect the other cone. And as it intersects the other cone, I'm going to get two pieces. I'm going to get one piece on the bottom cone and another piece on the upper cone, and those two pieces together give us the curve that is called a hyperbola. And so we've got the circle, the ellipse, the parabola, the hyperbola. All of these basic curves are united in this idea of slicing cones. And what Apollonius of Perga is able to do is to explain properties of these conic sections, these various curves that are all related in this way, and find the things that are common among them. Apollonius's work on conic sections would eventually become an important part of analytic geometry, when geometry and algebra get merged in the 17th century. And today, when we study these conic sections, we usually think about them algebraically. It makes it much, much easier to understand conic sections if you think about them algebraically. Apollonius did not have this kind of algebraic representation at hand. He had to think of them purely geometrically, and it's incredible how much he was able to do. We know that Isaac Newton, as he was writing the mathematical principles of natural philosophy, explaining the motion of the planets around the sun, he needed to use conic sections because, as was discovered by Kepler, the planets move in conic sections. They move in ellipses or parabolas or hyperbolas. And we know that Newton directly drew on this work of Apollonius of Perga in order to do his work in the mathematical principles of natural philosophy in the late 17th century of the modern era. Another important mathematician of this time, now jumping ahead several hundred years because I'm going to jump over some important astronomers who will figure in the next lecture. The next mathematician I want to look at is Diophantus of Alexandria, born sometime around 200 AD, died about 284 AD, certainly a mathematician in Alexandria of the 3rd century AD. A number of important innovations that come to us from Diophantus. He is the first person known to use a single letter to stand in for an unknown quantity. So today in algebra we use x all the time, or t, or some other letter to represent the unknown. It was Diophantus of Alexandria who, so far as we know, was the first person to come up with this idea. That does not mean that he invented algebra. As we'll see, especially when we get to the lecture on Islamic mathematics, there is much more to algebra than just having a single letter that represents an unknown, or even working with things like quadratic polynomials, which we saw that the Babylonians were able to do. But Diophantus did help set the stage for the later development of algebra. He was very well known to the Islamic mathematicians. He is responsible for a very compact notation to represent quadratic polynomials. So polynomials that involve the unknown squared plus a linear term plus a constant. Also cubic polynomials Diophantus studied. So these are polynomials that go up to a cubed term, something raised to the third power. And Diophantus of Alexandria is best known for his book, Arithmetica, in which he studies problems where he is only looking for solutions that only involve integers, what today we call Diophantine equations in honor of Diophantus. And a classic example of this are the Pythagorean triples that I talked about in connection with Babylonian mathematics. So you've got an equation like x squared plus y squared equals z squared. You can let x and y be any positive numbers, and there will be a positive value for z. But the more interesting question is, can you find integers for x and y that lead to an integer value for z? So examples like 3, 4, 5, 5, 12, 13, and so on. And it was Diophantus who studied this question. And Diophantus is the first person who actually recorded a method for generating arbitrarily many of these, in fact, all of the possible Pythagorean triples. Now, going back to the Babylonian work from almost 2000 BC, we have seen that they were able to generate literally dozens of these Pythagorean triples. They probably knew the method that Diophantus explained in the 3rd century AD, but nobody actually wrote it down until we got to Diophantus. The last mathematician that I want to talk about is the first woman to appear in the history of mathematics, and that is Hypatia of Alexandria. She was born around 370 AD. We know quite precisely when she died. She died in 415 AD. She was not alone in being a woman who was doing mathematics. We do have accounts of the mathematical community surrounding the Musaeon at this time in Alexandria, toward the end of the 4th century AD. And we know that the Musaeon itself was made up of a group of scholars, and many people would come from around the Hellenistic world in order to study mathematics, study mechanics, study optics, study the other sciences there at the Musaeon with these great scholars. The great scholars, incidentally, so far as we know, were not paid, but they were fed. And that was good enough to get them all to come together. And we also know that the Musaeon had a number of lecture halls where the members of the Musaeon could lecture about their topic. So people would come, they would listen to these lectures, they probably would pay the scholars independently for further lessons. And there was a group of people who gathered around the Musaeon who would also offer private tutoring or other lessons in mathematics. And Hypatia was one of them. She was actually the daughter of a member of the Musaeon, Theon of Alexandria. She was quite accomplished. We know that while there is no original mathematics that is directly attributable to Hypatia, we know that she wrote commentaries on the work of Archimedes, the work of Ptolemy, the astronomer, who I'll be talking about in the next lecture. She wrote commentary on the work of Diophantus. And in fact, just recently we discovered a work that is believed to have come from Hypatia. In 1968, there was an Arabic translation of commentaries written on Diophantus's Arithmetica. And it is generally believed from looking at the contextual evidence that these commentaries that were rediscovered in 1968 probably were written by Hypatia. And so if there was no original mathematics, and sometimes that's hard to tell because the commentaries often would elaborate on the mathematical themes and develop them further. Certainly, she was someone who understood the classic texts so well that she could write commentaries that would be used for hundreds, in fact, well over 1,000 years later. It's under Hypatia that the Musaeon comes to an end, and we do not know the exact date or the exact circumstances, but the last references to the Musaeon occur in the late 4th century, and they probably coincide with an event that happened in 391 AD. That's the year in which the Roman Emperor Theodosius I, who was a Christian emperor, banned all of the pagan temples. He ordered all pagan temples to be closed throughout the Roman Empire. The Musaeon was a center for scholarship, but remember that it was founded as a temple to the Muses, and as such it fell under this ban of Theodosius I. And so almost certainly at this point, the Musaeon is suppressed, and the scholars who would have gathered in this temple to the Muses were disbanded. Hypatia continued to live in Alexandria and to work in Alexandria, but the coming of the Christians to Alexandria would really mark an end to this great period of mathematical achievement. 415 AD, there is a great political fight between two leaders. On the one hand, we have Orestes, who was the prefect of Alexandria, the emperor's right-hand man running Alexandria. And on the other side, we have Cyril, who was bishop of Alexandria, the leader of the Christians in Alexandria. And since the emperor himself was a Christian, to be the bishop of Alexandria was to have a great deal of power. And Cyril and Orestes were engaged in a battle to see who could really control the city of Alexandria, and with control of the city of Alexandria would really come control of Egypt. And we know that Hypatia was a strong supporter of Orestes against the Christian bishop Cyril. And in the year 415, she was walking through the city of Alexandria when a Christian mob spotted her and attacked her, and she was literally torn to pieces. And that marks the last of the great Hellenistic mathematicians, and really the end of the Hellenistic period in mathematics. We're going to be looking at the development of astronomy in the Hellenistic world, and then in the following lecture we're going to move to India, South Asia, and we're going to see how they were able to pick up the Hellenistic tradition and further develop it. This is the last of our lectures on Greek mathematics, and in this lecture I'm finally going to start talking about astronomy. As I said, astronomy has been one of the dominant moving forces behind the development of mathematics. And in this lecture, we're going to look at how astronomy led to the development of trigonometry. Now, most people think of trigonometry as something that's used for land measurement, and certainly today it is used in surveying. But that's not where we get trigonometry. Trigonometry actually comes to us from astronomy, from problems in astronomy that I'm going to talk about in this lecture. And its application to problems of surveying actually didn't come about until quite recently. The earliest actual reference that we have to the use of trigonometry for the purposes of surveying is a book written in 1595 AD. For most of the history of the development of trigonometry, it came from astronomy, and it was being used exclusively in order to study astronomical phenomena. We also think of trigonometry as being defined in terms of the ratio of the sides of a right-angled triangle. Again, that's not the way trigonometry has been thought of. That's not the way people have thought of the trigonometric functions, the sine, the cosine, and the tangent function throughout most of the history of mathematics. we're going to see that those functions come out of the problem of trying to determine the length of a chord of a circle, finding the distance, the straight line distance between 2 points on a circle. And this idea of defining the trigonometric functions in terms of ratios of sides of a right-angled triangle only comes about in the 18th century. Trigonometry is extremely important, not just for the trigonometric functions and the role that they're going to play in mathematics in many different ways. That turns out to be one of those abstractions that is extremely important in many different contexts. But they also really begin to introduce the idea of function, and I'll talk more about this in this lecture and then again in the next lecture. This idea of having a process where you can take an input that can be any real number whatsoever, and you need to have a well-defined output no matter what input you put into this function. Well, I need to start by thinking about the solar system, and most of us have a picture of the solar system. There is a standard picture where you see a bunch of balls. There's a bright yellow ball in the center that represents the sun, and you've got a small blue ball, which is the Earth, and you've got a little red ball, which is Mars, and you've got all of these balls that are lying out there. And you see nice elliptical paths that are marked out, and the planets are going in these nice elliptical paths around the sun. And some people wonder, how could the ancients have been so confused that they didn't realize that the planets go around the sun? And of course, this traditional picture of the solar system that we have is something that nobody has ever seen. Nobody has ever actually put a satellite into that position and taken a picture of the solar system. And even if they did, that's not what they would have seen. The planets are much too small to show up as nice round balls. They simply would be dots of light. And planets don't leave vapor trails as they travel around the sun. You don't get these nice elliptical paths coming out. What the astronomers have seen is simply the night sky. And it's important to begin by thinking about what you can see in the night sky and how the astronomers began this process. The first thing that you observe by looking at the night sky is that the relative position of the stars is fixed. And this is why we create the constellations, why we're able to identify constellations, certain groupings of stars that always stay in the same relationship. But even though the relative position of the stars stays fixed, the stars themselves are moving in the sky throughout the night. And in fact, if you take a time-lapse photograph pointing toward the north, what you will see is that the stars are actually moving. You can see the tracks of these stars over time. The one star that stays fixed is the North Star or the polar star. That does not move. But all of the other stars are turning in a great sphere, a great celestial sphere around this North Star. One of the things that was observed in antiquity, far into prehistory, we have no idea when this first was observed, but the fact that the sun does not have a fixed position against this dome of the stars, that in fact the sun is constantly changing its position. And you can see that in that the first stars that you see on the horizon at sunset or the last stars that you see on the horizon at sunrise are going to be different constellations at different times of the year. And it was quickly realized that the position of the sun against the dome of the night sky is very important. Knowing where the sun is located tells you where you are in the process of a year. So it tells you when to expect the rains, when to expect spring to come. It tells you when to plant and when you should expect that the harvest is ready to be brought in. So the position of the sun against the heavenly dome is an extremely important thing to be aware of. And the actual path of the sun is what we call the ecliptic. And that comes from the means that people found, astronomers found, for determining where the sun is located. It's very difficult to see where the sun is against the stars because when the sun is out, it's so bright that you can't see the stars around it. But ancient astronomers figured out the path of the sun by using lunar eclipses. When the sun, the earth, and the moon are all lined up, the moon is exactly at the opposite point of the sky from where the sun is located. And so the moon, during a lunar eclipse, the moon is located where the sun will be exactly 6 months in the future. And by realizing this, then astronomers were able to gradually plot out the points where the sun would be at different times of the year. And once you begin to collect lunar eclipses over a period of 700 years, you get a very accurate track of where the sun is. And the position of the sun at different times in the year then tells you what to expect from the seasons. What we get are the signs of the zodiac, which are references to the constellations, which give a rough idea of where the sun is located. And there's a nice illustration of this in a frontispiece from Ptolemy's great work, the Almagest, that I'll talk about a little bit later in this lecture. And what you see in this frontispiece is what's called an armillary sphere. And so it is an object that shows the relative position of the sun and the various stars. The Earth is located in the center of the armillary sphere. You see the band of the ecliptic, that's the path that the sun moves along. And you also see the signs of the zodiac on this armillary sphere. Now, there are a number of problems that come up with the ideal situation for what's happening with the motion of the sun and what's happening with the stars. One of the things that was observed fairly early on is that in addition to the fixed stars, there are stars that move. In Greek, they became known as the wanderers or planetes, from which we get our word planet. So the planets are the stars that move, and it was observed that these stars that move also follow the ecliptic. And to the ancient astronomers or astrologers or mathematicians, again, those three terms really are synonymous. They observed that these points of light followed the same path as the sun. And if the position of the sun was so important for what's happening on Earth, then the position of these smaller lights must also be important for what's going on the Earth. Now, they're much smaller than the sun, and so one would expect their influence to be much more subtle. But nevertheless, they should have an important influence, and this is why astronomers, astrologers started tracking the position of the planets to figure out what's going on. Now, this was Aristotle's view of an Earth-centered universe with a great sphere of the stars, the sun, and the planets traveling on this path of the ecliptic. But it ran into some problems, and one of the first of these to be observed was the problem of retrograde motion. The fact that the planets do not keep moving along this great curve of the ecliptic. Every once in a while, they will slow down and back up. And this was a problem that Aristotle put out to the scientists of that time, the mathematicians and astronomers of that time, to explain what's going on. If in fact we have circular motion going out in the heavens, why do the planets occasionally stop, back up, then stop again and start going in the original direction? We understand this phenomenon today because we realize that a planet such as Mars is circling the sun, not the Earth, and the Earth is also circling the sun, and the Earth is closer to the sun, and so it takes less time for the Earth to go around the sun. And what happens is, every once in a while, the Earth is going to lap Mars. So when the Earth comes closest to Mars, it's actually going to pass it, and it's going to look like Mars is backing up. But then once the Earth is far enough along, it will again look like Mars has begun moving in its normal direction around, in this case, around the sun, or what it looks like from the Earth that Mars is going around the Earth. This problem of trying to explain retrograde motion, this backing up motion of the planets, something that Aristotle posed, and as the first person to come up with a solution was Aristarchus of Samos. He was born sometime around 310, and Aristarchus suggested that maybe retrograde motion is coming from the fact that Mars does not go around the Earth. Maybe Mars and the Earth both go around the sun. He actually came up with the correct solution. But of course, nobody believed him because his solution was totally preposterous. There's no possible way that the Earth could actually be circling the sun. We would have to be traveling at incredible speeds. In fact, the speed of the Earth around the sun is about 67,000 miles an hour. How could we possibly be traveling around the sun at that kind of a speed and not be aware of it? So people began to look for other solutions. And the person who eventually would come up with a solution to retrograde motion that would generally be adopted was Apollonius of Perga. This is the same Apollonius that we met in the last lecture, famous for his work on conics. And he's the one who suggested that what's really going on is that as Mars circles the Earth, Mars itself is actually located on a little circle whose center circles the Earth. So what happens is that we have Mars, which is going around and around a little circle, and the center of this little circle is going around the Earth. And so what's actually happening is that Mars executes a kind of looping motion as it travels around this little circle called an epicycle, so an outer circle. It goes around this little circle, the epicycle, as the center of the epicycle goes around the Earth. And this preserved one of the foundational Aristotelian viewpoints about the nature of the heavens, which was that everything that goes on in the heavens must be built out of circles. Now, there are other problems with trying to explain what goes on in the heavens. And another one of the problems that actually was observed by Aristotle and finally solved by Hipparchus of Rhodes, who lived sometime in the 2nd century BC, was the problem that if you look at the length of the seasons, they are not of equal length. So the ancient astronomers knew where the sun was located at the summer solstice, and they knew where the sun was located at the winter solstice, and these 2 points are exactly opposite along this great circle of the ecliptic. You then look at right angles from the line that connects the summer solstice to the winter solstice, and that gives you the vernal equinox or the spring equinox and the autumnal equinox. And the seasons are marked by the time from the winter solstice to the spring equinox. That gives you winter. Spring equinox to summer solstice gives you spring. Summer solstice to autumnal equinox gives you summer, and so on. And one would expect, if the sun were just traveling in a nice big circle with the Earth at the center, that each of the seasons would be the same length. But they're not. Now, it may not seem this way, but actually winter is the shortest season and summer is the longest. And the difference between the two is not subtle. Winter is about 89 days long from the winter solstice to the spring equinox. Summer is more than 4 days longer. It's 93 and about 5/8 of a day. So it's more than 4 days longer from the summer solstice to the autumnal equinox. And it was Hipparchus of Rhodes who came up with the idea of how to explain this. It could be explained if, rather than putting the Earth at the center of the universe, you had the Earth slightly off-center. So if the Earth is slightly off-center, if it's closer to where the sun would be in winter, then you're going to get a smaller arc that the sun has to travel during winter, and you're going to get a longer arc that the sun has to travel during summer. Now, of course, this immediately begins to upset the Aristotelian worldview because it moves the Earth off the center of the universe, but that seems to be the way to do it. And Hipparchus was looking at this problem and trying to figure out how off-center the Earth had to be. And that's where we get to the problem of calculating the length of a chord. In order to do this, Hipparchus essentially invented trigonometry, What he did was to invent a way of determining the length of the chord that connects 2 points on the arc of a circle. So this would become the basic problem of trigonometry. You've got an arc of a circle, and you want to figure out the length of the straight line that connects the 2 points at the end of that arc. Now, first of all, you've got to decide how you're going to measure that arc of circle, and we measure it in degrees, and this has been inherited from the Babylonians, who measured the arc of a circle in degrees. And this is something else that people very often do not understand. Today, we use degrees to measure how much something has turned. We say that something has turned 90 degrees, that means it's made a quarter turn. That is very recent. That's an 18th century interpretation of degrees. Up until the 18th century, degrees were a measure of arc length. They were a measure of how far you had traveled around the outer edge of a circle. And the Babylonians divided the circle into 360 degrees, almost certainly because that's approximately the number of days that it takes the sun to travel completely around the earth, or the earth to travel around the sun. Interestingly, the Chinese divided a circle into 365¼ degrees. And this is nice in one respect because it means that the sun moves exactly 1 degree every day. But working with a circle of 365¼ degrees is very difficult to do. And so the Babylonians made a compromise. They picked an easier number to work with, 360. What that means, though, is that the sun does not move exactly 1 degree across the ecliptic every day. It moves a little bit less than 1 degree every day. These degrees of arc length then would be subdivided according to the Babylonian system into 60ths of a degree, which we call a minute. And the word minute actually comes from Latin. It means a small part, pars minuta. And so we take the word minuta and it became in English minute. And then you divide the minute up into 60 seconds of arc, so a 60th of a 60th of a degree. And this is called in English today a second. And this comes from the phrase the second small part, pars minuta secunda. And so secunda, the second small part, became our second. So we're measuring the arc length in degrees, minutes, seconds. And given any particular arc length, we want to find the length of the chord that connects the 2 endpoints of that arc. Now, that's going to depend on the value of the radius. So as I make the radius larger, the chord length is going to change. So the chord length is always described in terms of the radius. If I take an arc of 90 degrees, that's a quarter of a circle, and if I know the radius, it's simply the length of a diagonal, and so the chord of 90 degrees of arc is going to be the radius multiplied by square root of 2. If I take a chord that corresponds to an arc of 60 degrees, well, I simply get an equilateral triangle formed by the 2 radial lines that go out to the circumference, and so the chord of 60 degrees is exactly 1 radius. And the Greeks were also able to figure out the exact value of a chord of 72 degrees. That turns out to be the square root of the quantity 5 minus the square root of 5, all divided by 2. Now, I've said that this problem of finding chord lengths is where we get trigonometry, and in fact, trigonometry does correspond to these chords. If we think about taking an arc and then taking the chord that connects the 2 endpoints of the arc, and the terminology here is the terminology of bows and arrows, so an arc or a bow, we've got the chord or string that connects the 2 endpoints of that arc, and we consider the line from the center of the circle out to the midpoint of our arc. And that was referred to as the arrow. It looks very much like an arrow. We can now connect the radial lines that go from the center of the circle down to the bottom of the arc and the center of the circle up to the top of the arc. And it really does look like a bow and arrow at this point. And if you consider not the full chord length, but only half of the chord length, so you consider the chord that goes from where it attaches to the arc at the top down to the arrow, what you have there is precisely the sign. Now, the Greeks did not work with the sign. The Greeks worked with what today we would think of as twice the sign, the chord. And this idea of working with half of that quantity, working with the sign, is something that would come out of India. And I will talk about that in the next lecture, how Indian astronomers picked up the ideas of Hipparchus and the other Greek astronomers, and then developed them into the kind of trigonometry that we understand today. Instead of working with a full chord, they worked with a half chord, what they called the sign. And then you also get the other trigonometric functions, the cosine. The tangent itself actually would be invented by Islamic astronomers. In the time that remains, I want to talk about the greatest astronomer of the Hellenistic period and also one of the greatest mathematicians of this period, and that is Ptolemy of Alexandria. We've run across a number of Ptolemies before, Ptolemy the first, second, and third, who were rulers in Alexandria, rulers of Egypt. This is a scientist who happened to share the same name. He lived during the 2nd century AD, and he took the ideas of Hipparchus and he put them into an incredible work on astronomy, a work that runs to 13 books, a work that is so comprehensive, does such a great job of explaining astronomical phenomena, that just as when Euclid's Elements came out, people threw away any mathematical works they had from before Euclid, the same is true with Ptolemy. When Ptolemy's astronomical work came out, everybody threw away any other astronomical texts that were out there. And so none of the texts from before Ptolemy actually exist. All we have are a few references to what was contained in them, and it's Ptolemy's own references to Hipparchus that tell us what Hipparchus had been doing. This great work of Ptolemy was known as the Mathematikis Syntaxis, the mathematical collection, and it would come to be known as the Great Collection, the Megisti Syntaxis, and the Islamic astronomers would then translate this into Arabic, and they would come to know it simply as the Great Work, Al-Magisti, taken from Megisti Syntaxis, the Al-Magisti. When this then was translated from the Arabic into Latin for European astronomers and European scientists, they took the Arabic term, the Al-Magisti, and they called the work the Almagest. And so that's the term by which it is commonly known today. And one of the great results that Ptolemy was able to do in this book, there's a lot of astronomy in it, there's a lot of mathematics in it, but I want to focus on one part, which is Ptolemy's efforts to construct a table of values where you could put in the arc length that you were interested in and then read off what the chord length would need to be. As I said, he started with certain chord lengths that were fairly easy to determine. And of course, one of the things that you've got to decide as you come into this is what your radius is going to be. Now, the circumference of a circle is 360 degrees. And it's going to be easiest to work with chord lengths if we measure the chord length in the same units that we use to measure arc length. So we really want to measure the chord length in degrees. Well, if I've got a circle of circumference 360, that means that I'm going to need a radius which is 360 divided by 2 pi, which is a little bit more than 57 degrees. It's about 57 degrees, 17 minutes, 45 seconds. Well, that's very difficult to work with. So what Ptolemy and the other early astronomers usually did was to convert everything to minutes. So the total circumference of the circle would be 360 times 60, and then the radius in minutes is approximately 3,438. Now, what Ptolemy was able to do then was to take the values of chord length that he knew. He knew the chord length for 72 degrees. He knew the chord length for 60 degrees. He also was able to work out how the chord length of a given arc could be determined if you knew the chord lengths of two arcs that added up to that. Or equivalently, if you know the chord length of one arc and you know the chord length for a smaller arc, he found the formula for finding the chord length of the difference. This is equivalent to our modern formulas for finding the sine of a sum of angles or the sine of a difference of angles. And so using these, he was able to find an exact value for the chord length of 12 degrees. And then you can also use this formula if you know the chord length for a given arc. You can find the chord length for half of that arc. So once you know the chord length for 12 degrees, you can find the chord length for 6 degrees or 3 degrees or 3/2 of a degree or 3/4 of a degree. But that doesn't give you the chord length for 1 degree, and this is something that Ptolemy really wanted to work out to quite a bit of accuracy. And one of the advantages of using the same unit of measure to measure the arc length and the chord length is that as we take smaller and smaller arcs, the ratio between the chord length and the arc length should approach 1. And so for very, very small arcs, we can assume that they're approximately equal. And that means that the 3/4 degree arc divided by the chord of 3/4 should about equal the arc of 1 degree divided by the chord of 1 degree. And that tells me that the chord of 1 degree is very close to the reciprocal of 3/4, which is 4/3, times the chord of 3/4. He knew the exact value of the chord of 3/4. He could then use that in order to find a very, very close approximation to the chord of 1 degree. And once he had the chord of 1 degree, he could find the chord of 1/2 degree. And once he had the chord of 1/2 degree, and he had this formula, if you know the chord of one arc length and the chord of another arc length, you can add them together. So he was able to build up an entire table of chord lengths in intervals of 1/2 degree. And if you know the chord length for 1/2 degree, that corresponds to the sine of 1/4 of a degree. So effectively, what Ptolemy was able to construct was a table of values of the sine down to just 1/4 of a degree at a time. Now, Ptolemy was 2nd century AD. As I've said, Greek mathematics really ends about 400 AD. Fortunately, though, this was not the end of the developments in astronomy, because these astronomical works that came out of the Eastern Mediterranean would be imported into India, and the Indian astronomers would pick up this idea, carry it much further, and also bring in many new ideas in mathematics. And in particular, one of the things that we will see in the next lecture is how this work on trigonometry would lead to a general appreciation for polynomials. In the last lecture, we finished our study of Greek mathematics, and in this lecture, we move on to Indian mathematics. The origins of Indian mathematics are rather uncertain. The earliest records that we have actually come to us from the Vedas, the great epic poems that were written in the mid to late 2nd millennium BC. The mathematics that's contained in the Vedas is very sketchy, and often what is found there is more of a mnemonic device, and so it's open to a great deal of interpretation what exactly is being described in the Vedas. But there is a collection of works that really are appendices to the Vedas, what are known as the Sulba Sutras. written in the period roughly 800 BC to 200 BC. And these describe how rituals were to be performed, and they lay out the way in which altars were to be constructed, things such as this. And so there's a fair amount of mathematics that's contained in the Sulba Sutras. And so one of the problems that the Indian priests would face is one of, say, doubling the area of an altar. And in order to double the area, what you need to do is take the length and the width and multiply each of those by the square root of 2. So the Sulba Sutras explain how to find a good approximation to the square root of 2. They also explain how to compute volumes. If you want to double the volume of a given altar, you need to multiply each of the 3 dimensions by the cube root of 2. And so these also explain how to find good approximations to the cube root of 2. We do find references to the Pythagorean theorem here. We also find references to interesting counting problems, because one of the ways in which the Vedas and the Sulba Sutras and these other poetic forms was memorized was to recombine the syllables. And people were often interested in the number of ways that these could be recombined. And some of our earliest work on what we call combinatorics actually comes from these kinds of investigations. The earliest recorded writing that we have of Indian mathematics also makes it clear that they were using a very different system for recording numbers, a system that's much closer to the system that we use today. They had 9 symbols for the digits 1 through 9, and then they would combine these with special symbols for the powers of 10. So you had a symbol for 10, a symbol for 100, a symbol for 1,000, and so on, and you put these together. So if you wanted to represent a number like 327, you'd write the digit 3, the 100 symbol, the digit 2, the 10 symbol, and then the digit 7. It was not yet a full place value system in our modern sense, and one of the problems was that at this point, the Indian mathematicians did not have the digit 0. They did not have this placeholder, which enables us to tell the difference between 307 and 37, and so they used symbols for the power of 10 that was being recorded. This system, as we'll see in the next lecture, was also used by Chinese mathematicians. And one of the interesting questions out there is whether this system was originally created in India and then imported into China, or originally created in China and then imported into India, or perhaps created someplace else, such as Central Asia, and then imported into both of those countries, or maybe it just happened to come up independently. It was an idea that made good sense in both India and China. But at roughly the same time, we see a very similar system of writing the numbers. 0 itself would be invented sometime, well, nobody's really sure, sometime between 300 and about 600-700 AD. The earliest actual recording that we have of 0 being used as a placeholder in a number is actually in a Hindu temple in Cambodia that was constructed in the year 683 AD, and the year as recorded in the Hindu system was a number that actually used the digit 0. 0 had been used a bit earlier, not as a placeholder, but as a number that could be manipulated by the 7th century astronomer Brahmagupta. And this really is the first time that we have record of somebody working with a symbol that represents nothing, a symbol for 0. 0 now enters the numerical system. And Brahmagupta did explain what happens when you add a 0 to a number or subtract 0 from a number, or what happens if you multiply a number by 0, you still get 0. And he wrestled a bit with this whole issue of what happens when you divide a number by 0, and essentially sort of left that up in the air, what happens when you try to divide by 0. In today's lecture, I'm going to focus on 3 great Indian astronomers, Again, these were men who were best known for their contributions to astronomy, but they also did a great deal of work in mathematics generally, in algebra, in number theory, and other areas of mathematics. These are Aryabhata, born about 476, died sometime in the middle of the 6th century AD. Brahmagupta, that I have already mentioned, who lived in the 6th century. And then Bhaskara Acharya. Acharya is an honorific title. It means scholar, so this is really Bhaskara the scholar, who lived in the middle of the 12th century. As I said in the last lecture, the astronomical works that were developed in Alexandria and elsewhere in the Eastern Mediterranean would be taken up by the Indian astronomers, and this appears to have happened in the first several centuries AD, under the Kushan Empire. Now, the Kushan Empire was an empire that had come down out of Central Asia to take over northern India, and it had strong connections with an older Hellenistic empire, the Seleucids, who were based in Persia and also in Central Asia. And largely because of this, the Kushan Empire maintained strong connections with the Eastern Mediterranean. And we do know that they brought astronomical texts from Alexandria and elsewhere. Strangely, it seems that they never actually imported Ptolemy's Almagest. That appears to be one of the books that was not translated into Sanskrit. But many of the other astronomical works of that same period were brought into India and were translated into the Sanskrit. And fairly soon after receiving the Greek texts, the Indian astronomers began to build on those and further develop their idea of trigonometry. The first of the great Indian astronomical texts is the Surya Siddhanta. We don't know exactly when it was written, probably in the 4th or 5th century AD. It's possible it was written even earlier than that. But already here in this first Indian astronomical work that uses trigonometry, we see that the Greek chord has been replaced by the half chord, what would come in the West eventually to be called the sine. And there actually is an interesting story behind how we got this word sine. The Indian astronomers quite naturally called it a half chord. The word for chord is jia, and half is ardha, so this was an ardha jia, a half chord. Although eventually they dropped the adjective half, they just referred to it as a jia or jiva, and this meant, though, the half chord. And from jiva, the word was taken up by the Islamic astronomers, and they pronounced it as jiba, and they wrote it in Arabic, which only uses consonants, as JB. And when the first Western astronomers were trying to figure out what this function was that was being described, they looked at these Arabic letters JB, which of course did not represent any word in Arabic. Jiba is not an Arabic word, it's simply a transliteration of the Sanskrit word for this half chord. They looked at those letters JB, and the one Arabic word that they knew that used the letters JB was jaib, which means breast. And so they assumed that this was to be called a breast. Now, it's not quite clear how this happened, but perhaps out of excessive modesty, rather than calling it a breast, they decided to refer to the fold of a cloth that might cover a breast. And the fold of a cloth could be referred to as a sinus. And so this became a sinus in Latin, which in English eventually would become our sine. So we get sine out of a mistranslation of a transliteration of a Sanskrit word. The Indian astronomers also studied the cosine, which was the kotijia. And if you think about the bow and arrow, so we've got the arc of the bow, we've got the chord, and we've got the arrow. The shaft of the arrow, so that's the distance from the center of the circle to the chord, that is the cosine, or the kotijia. And the Indian astronomers also made great use of the ukra madhya. And that's the tip of the arrow. That's the little part of the arrow between the cord and the arc of the bow. This would come to be called in English the versed sign. We no longer work with the versed sign. The versed sign, after all, is just the radius minus the cosine, so there's no real need to come up with a separate term for this. But if you look in the 17th century, something like Newton's Principia, his mathematical principles of natural philosophy, he does a lot with the versed sign, and this is where it's coming from. It's an Indian invention, and it comes out of describing that arc, that tip of the arrow. I'd like to spend some time now looking at the trigonometric tables that people came up with, and particularly the work of Aryabhata. Aryabhata, as I said, was born 476. He was in the Gupta Empire. The Gupta Empire had begun around 320, would last until about 600 AD. Aryabhata lived in Kusumapura, which was the center for astronomical work, very near the capital of Pataliputra, which today is modern Putna in India. He also was working with a circle of radius 3,438. And he almost certainly was not aware of Ptolemy's Almagest, because, as I said, Ptolemy's Almagest was actually able to look at chord lengths for arcs all the way down to half a degree. And Aryabhata was working with chord lengths of 3 degrees 45 minutes. In other words, what he was doing was starting with a chord length for 60 degrees, and then from that you can get the chord length for 30, 15, 7.5, and then 3 3/4 just by taking half angles. So he had a much rougher table. But he did something that was extremely important. He was looking at the problem of interpolation. If you've got a table of values and you want to find some intermediate value, how do you go about doing that? Well, a natural way of doing this interpolation is that if you've got a value, say, that's halfway between the two given values, you just take the output that's halfway between the two outputs. And rather than looking at the actual trigonometric table that Aryabhata was looking at, I'm going to show you a somewhat simplified table that illustrates the point of what Aryabhata and the later Indian astronomers were able to do. So what I'm going to do, on one side, I've got inputs that are the digits 1, 2, 3, and 4. And then I've got outputs that are the digits 1, 3, 7, and 13. And the question then is, if I've got an input of 2.5, what should be my output? Well, 2.5 is halfway between 2 and 3, so that suggests that my output should be halfway between 3 and 7. And so we might take 5 as the logical output. And that's what's called a linear interpolation. We're just assuming that things work as if they're on a straight line. But in fact, if you look at these output values, 1, 3, 7, 13, you see that the output values are increasing. 1 to 3 is a difference of 2, 3 to 7 is a difference of 4, 7 to 13 is a difference of 6. These differences are themselves increasing. Aryabhata did not just look at the differences, he actually took a table of the second differences. And he used that to refine the way in which he was going to do this interpolation. What is happening in this table is that as we move further down the table, the increase gets bigger. And so the increase in the output going from 2 to 2.5 should not be as big as the increase in output as we go from 2.5 down to 3. We need a bigger increase in output. Now, the total increase in output from 2 to 3 has got to be 4. So the output increases from an output of 3 to an output of 7. But how do we then arrange this output in order to take into account the fact that the outputs are increasing at an increasing rate? And one of the things that you can do is to decide that from 1 to 1.5, we've got to have a certain increase in the output. From 1.5 to 2, we've got to have a greater increase in the output. And the increase in the output has to increase by the same amount each time. And so we can do this if from 1 to 1.5, we have an increase of 3/4. From 1.5 to 2, we have an increase of 5/4. From 2 to 2.5, we have an increase of 7/4. And then from 2.5 to 3, we have an increase of 9/4. Now our increases are going up by the same amount each time. 7/4 plus 9/4 gives us our 16/4, our total increase of 4 as we go from 2 to 3. And so that says that a better output for an input of 2.5 is 3 plus an increase of 7/4. So that gives us 4 3/4 as the desired output. And what is happening here is that you are beginning to get the idea of taking this table of values and doing what today is called a quadratic interpolation. So you're no longer using just a straight line to figure out what number should come out. You're using a much more sophisticated kind of technique for interpolation. And this idea of using a quadratic interpolation would be more fully developed by Brahmagupta. And Brahmagupta would actually show how to do an arbitrary quadratic interpolation for any kind of function that you might put in. So if you know the value of first differences and you know the values of the second differences, you can then use those in order to get a better idea of what the intermediate values in your table should be. Brahmagupta is an extremely important mathematician and astronomer. He taught at the great astronomical center of Ujjain, which is located on the western edge of Madhya Pradesh, near modern Rajasthan. Ujjain was founded around the 4th century BC, and it would exist until the 12th century AD. It would be an important mathematical center, and it would be so important as an astronomical center that it would mark 0 longitude, or what was the first meridian for Indian astronomers. Now, the first meridian in our modern world is the line of Greenwich, and that's chosen because of the Royal Astronomical Observatory in Greenwich. It's decided that that is 0 longitude, and you measure the longitudes east and west from Greenwich. In ancient Indian astronomy, that 0 mark of longitude was located going right through the center of Ujjain, the great astronomical center. As I mentioned before, Brahmagupta is the first person known to have used 0. He also is one of the first people known to have used negative numbers. Now, we will see in China that negative numbers came in much earlier, but only as intermediate steps. And Brahmagupta realized that you needed to be able to actually work with negative numbers and accept negative numbers as possible solutions. And so far as we know, he's the first person actually to accept negative numbers as solutions to mathematical problems. This interpolation formula, this quadratic interpolation, is often attributed to Newton, who would then go on and extend this to interpolation by polynomials of higher degree, cubic polynomials, 4th degree polynomials, and so on. Eventually, the Indian astronomers would realize how to do this, how to not just take first differences and second differences, but to work with third differences, fourth differences, as many as you needed in order to get a very accurate interpolation of the values. Brahmagupta also did work on Diophantine equations. So these are equations that were studied by Diophantus. And one of the examples of these that I gave earlier is the problem of Pythagorean triples. So 3, 4, 5, 3 squared plus 4 squared equals 5 squared. The kind of Diophantine equations that Brahmagupta studied, equations where we're only interested in integer solutions, are things like x squared minus 8y squared equals 1. If you find two integers that solve this, then the ratio of those integers gives you a very good approximation to the square root of 8, a good rational approximation. And he found a number of solutions to this. We don't know exactly the method that he used. All we know are the answers that he found. But for example, he showed that 3 squared minus 8 times 1 squared is equal to 1. And 17 squared minus 8 times 6 squared is equal to 1. And 3,363 squared minus 8 times 1,189 squared is equal to 1. Another one of the examples of the Diophantine equations that Brahmagupta studied are something squared minus 61 times something else squared is equal to 1. And here the answer gets much more complicated. One of the answers that Brahmagupta actually came up with to this is you take 1,766,319,049, you square it, you subtract 61 times 226,153,980, this quantity gets squared, and then that difference is actually equal to 1. This idea would further be developed by the last of the great Indian astronomers that I want to talk about, Bhaskara Acharya, born in 1114, died in 1185. He also was interested in this problem of finding polynomials that interpolate values in these tables of sines and cosines and versed sines. And he came up with something that would really anticipate developments in Western Europe that would come many, many hundreds of years later. And that is, in order to find a good polynomial to approximate the sine, he considered the rate at which the sine function is changing. What Bhaskara actually was looking at is the derivative of the sine function. And what he realized is that the rate at which the sine function changes is given by the cosine function. And the rate at which the cosine function changes is given by the negative of the sine function. And he saw how to use this fact in order to find what today we would call a Taylor polynomial, a quadratic polynomial that does a very good approximation to the sine function, very close to any value that you happen to know the exact value of the sine function for. So if you know the exact value of the sine, you know the exact value of the cosine, you can work out this quadratic approximation. And this really marks a new episode in the understanding of polynomials. Because up until now, polynomials had been thought of simply as things that are useful for solving problems that involve areas, then you use a quadratic polynomial, or problems involving volumes, then you're going to use a cubic polynomial. But now suddenly polynomials were being used for interpolation. They're being used to approximate the missing values in a table. And once you start doing that, there's no reason to stop at polynomials of degree 3. There's no reason to stop with volumes. The Greeks stopped with polynomials of degree 3 because it made no sense to talk about a 4-dimensional region. But if you're simply looking at the interpolation, suddenly it makes sense to go beyond degree 3 and consider a polynomial of degree 4, a polynomial of degree 5, a polynomial of degree 6. And we're not entirely sure where these different polynomials came from, but it seems that this was one of the important sources of the development of the idea of a polynomial of general degree. Also, the Diophantine equation that was studied by Brahmagupta, this general problem, you've got a perfect square, and you subtract some integer times another perfect square. I gave the examples where it's a perfect square minus 8 times another perfect square equals 1, or a perfect square minus 61 times another perfect square is equal to 1. That is known today as Pell's equation. And this is an equation that was not just studied by Bhaskara, Bhaskara actually was able to find a way of coming up with a solution to Pell's equation no matter what multiplier you were using. So you could use an 8, you could use a 61, you could use any number as long as it's not a perfect square. So you could take x squared minus 57y squared equals 1, or x squared minus 327y squared equals 1. And Bhaskara laid out a procedure that would enable you to find a pair of integers that would then satisfy that equation. Indian mathematics would continue after the fall of Ujjain. Ujjain disappears in 1235. This is when the Delhi Caliphate conquers Ujjain. The astronomical center is destroyed. At that time, at the time of the conquest, the astronomers in Ujjain are dispersed. Northern India ceases to be a center of important mathematical work. But the mathematical work of that time does move down into southern India, specifically southwestern India in Kerala. And we do have a series of important Indian astronomers doing work in mathematics down in Kerala, beginning with Madhava in the 14th into the early 15th century, Parameshvara, a late 14th century into the 15th century, Nilakantha, 15th into the early 16th century. And what these astronomer mathematicians were able to do is to take the general idea that Bhaskara had done of taking a trigonometric function, looking at its rate of change, and using the rate of change, and the rate of change of the rate of change, and the rate of change of the rate of change of the rate of change, to come up first, as Bhaskara did, with a quadratic polynomial that's a good approximation to the sine function, and then a cubic polynomial, and then a fourth-degree polynomial, and eventually they saw how to get a polynomial of arbitrary degree. So you can get a polynomial of as high degree as you want. The higher you take the degree, the closer the approximation is going to be. And it's not clear which of these astronomers actually was responsible for it. It's generally believed that this goes back all the way to Madhava. But at this time, what they did was not just figure out how to get polynomials of arbitrarily large degree, they then made the jump to a polynomial of infinite degree, what today we would call a power series. So this is an infinite collection of powers of your unknown, which can be brought as close as you wish to the actual value of the function. So it's a representation of the function as a sum of powers of the unknown. The powers go out toward infinity. You can get as close to the value as you want just by going far enough out. This is work that was probably done in the 14th century. This is work that would not be redone in Europe until the very end of the 17th century. Unfortunately, the work that was done in India was lost to the rest of the world. The astronomers who were working on power series in South India were not able to communicate their results to anyone else. And the fact is that their way of approximating the sign was almost too accurate. The problem was that you can only measure the difference between two lights in the sky to within maybe a couple minutes of arc. So being able to calculate values of the sine or the cosine or the tangent to this kind of accuracy was far more than what was needed. And at this point, nobody could figure out any other uses for the sine or the cosine. The only uses for these trigonometric functions at this time was in astronomy. And since no one could figure out these uses, eventually knowledge of these power series would be lost. And it was only in the 19th century, actually, when British archaeologists managed to come across some of these old documents from several hundred years earlier. Mathematicians then looking at them realized what actually had been accomplished. But it points out the importance of not just pulling ideas from the world around you. The ideas that you pull out of the world around you have got to be applicable to worthwhile problems in understanding the world. And once the mathematics becomes divorced from what is really needed, there is the danger that it's going to degenerate. In the next lecture, I'm going to move north from India into China, and we will see what was happening at this same time, the first millennium AD, roughly up to about 1300 AD in China. In this lecture, we're going to look at Chinese mathematics, taking it up roughly to about 1300 AD. In my very first lecture, I talked about different sources of mathematical ideas, one of which is civil administration, another is navigation and surveying, and the third is astronomy. And as I said, all of these come into play in all of the great mathematical cultures, but different ones come to the fore in different cultures. So, for example, for the Babylonians and the Egyptians, as we saw, the dominant mathematical theme was what was needed for civil administration. When we get to the Greeks, the dominant theme is navigation and surveying, and this would influence the Greek decision to put their emphasis on proportion and on geometry. As we saw in the last lecture with Indian mathematics, really the dominant source of mathematical work came from astronomy. It was really the astronomers who were making the progress in mathematics. As we now shift to China, we're going to see that we go back to a mathematics that primarily comes out of civil administration, very similar to the sources for the mathematics in Babylon and also in Egypt, although also here navigation, surveying, and astronomy will be very important sources for the mathematics that is created. Our recorded record of mathematics in China begins with the early part of the Han Dynasty, what is known as the Western Han Dynasty or former Han Dynasty, going from 206 BC to 25 AD. And what made this particular time particularly propitious for the development of mathematics connected with civil administration is that this is the first Confucian dynasty in Chinese history. So this is a dynasty that is really built around the idea of Confucian scholars, people who are drawn out of the general population and trained in the kind of mathematics and philosophy and jurisprudence that they would need in order to be civil administrators. And so an important role in the Western Han Dynasty was that of the teacher, that of the person who would train the future Confucian scholars. And these people needed textbooks. And the Chinese textbooks in many respects are similar to the kinds of textbooks that we saw in Babylon and in Egypt. These are problem books. These are books that set out lots of problems that a future scholar would need to be able to solve in various contexts, and then would work out the solutions. We have two manuscripts from this time. The first of these is the Chupei Suanjing, roughly translated as the mathematical classic of the Chu Nomen. And this was written possibly in the 1st century BC. It might go back even earlier than that. And this deals with problems of similar triangles, very much involved with questions of surveying. You find the Pythagorean theorem stated quite clearly in this particular work. There also are methods for calculating square roots. Another book that comes out of this same period is the Chucheng Suanshu, or Computational Prescriptions, in 9 chapters. And this does a lot of work with finding areas and volumes. Again, we find the Pythagorean theorem. We also find linear equations. So these now are systems of equations, situations in which you've got several things that are unknown, but you've got several relationships connecting them. Problems like this can be found in the ancient Babylonian mathematics, but we also see it reappearing here in the very earliest known Chinese mathematics. There are also general rules for calculating square roots and cube roots, and the kinds of problems that are dealt with in this particular book involve problems of surveying, problems of commerce, problems of tax collection. And they use the same system for representing numbers that was used in India. The largest number that is actually represented in this particular book is 1,644,866,437,500. So they clearly were comfortable with working with extremely large numbers. Even more important than that, the Chinese at this time, this is still about the 3rd or 2nd century BC, were not only using fractions, but they also were using decimal fractions. So they extended this idea of a decimal representation, not just units place, tens, hundreds, thousands, but also moving in the other direction and looking at tenths, hundredths, thousandths. And in this book, we do have decimal fractions expressed out to thousands. Also here, again, we're talking 2nd, 3rd century BC. The Chinese are using negative numbers. Now, as I said, it would be Brahmagupta who was the first person to really accept negative numbers as legitimate solutions to mathematical problems. The Chinese were not there yet. But they were the first people to use negative numbers as intermediate steps in some sort of a calculation that might need to be done. Buddhism is introduced generally into China around the 1st century AD, and sometime shortly after that we begin to get the Indian astronomical texts being brought up, texts written in Sanskrit and introduced into China. And there are references to Chinese monks who would make a pilgrimage to India and be asked to come back with the mathematical texts. And so there was some transfer of mathematical knowledge from India into China in this time. We know that the Chinese built their ideas of trigonometry and began to work with trigonometric functions based on what they had learned from the Indians. Although this is one of the few places where we actually are aware of how mathematics traveled from China to other places or from other places to China. There is very little other direct evidence of influence between China and the other civilizations that surrounded it. It would take a while for the Chinese to begin to use 0 as a placeholder. They did not start using it until many hundreds of years after the Indians had begun to use it. But around the year 1000 AD, the Chinese were using 0 as a placeholder, although well after that, many of the Chinese mathematicians would continue to use special symbols for 10, 100, 1,000, or tenths, hundredths, or thousandths. The first actual Chinese mathematician that we know by name was Lui Hui. He lived sometime late in the 3rd century AD, and he is best known for his work, the Haidao Suanjing, or the Sea Island Computational Canon. And this was really a work that was looking at questions of surveying. And the name of this particular work, Sea Island Computational Canon, comes from the very first problem that's explained in the book, and that is trying to determine the height of a mountain on an island. So you are not on that island, you're somewhere offshore, but you see that island and you want to determine the height of the mountain. And you cannot actually determine your distance from where you are to the base of the mountain. What you have to do is take several different observations from where you are on this opposite shore. And what Lui Hui does is to explain how to use the idea of similar triangles in order to work out what the height of this mountain is going to be. We also very significantly find in this particular work the very first Chinese proof of the Pythagorean theorem. Now, this is not the first known proof of the Pythagorean theorem. As I said, this was known earlier, probably sometime in Greece between the time of Pythagoras and the time of Euclid. But Lui Hui does work out an actual proof of the Pythagorean theorem. Very significantly, he also works out a general method for finding areas and volumes that is equivalent to the method that was developed by Eudoxus of Cnidus and then described by Euclid and used so effectively by Archimedes, this idea of method of exhaustion, and that is used by Lui Hui. Lui Hui also comes up with exactly the same idea for approximating pi that Archimedes had discovered. This idea of first finding the circumference of a regular hexagon that is inscribed inside a circle, and then doubling the number of sides. As I said, Archimedes stopped when he got to a regular polygon of 96 sides. Lui Hui took this a step further. He went all the way up to a regular polygon of 192 sides, and used that to come up with the approximation which he actually states that pi is approximately 3.14. And so he gives it as the decimal using tenths and using hundredths. And Lui Hui also does something else. Even though decimal fractions had been used earlier, it's not quite clear how much mathematicians of that time were aware that you could continue decimal expansions as far as you wish. And Lui Hui specifically states that decimals can be expanded to as many places as you might wish. If you've got any distance, you can always try to find an approximation to its value by taking progressively smaller units, so taking tenths of tenths of tenths as far out as might be needed. Now, I said that Lui Hui came up with a very accurate approximation to pi 3.14. As most Chinese school children know, the most accurate approximation to pi from this time comes from a mathematician who lived late in the 5th century, Zhu Chongqi, and he came up with a rational approximation to pi of 355 over 113. It's a remarkable accomplishment. We don't know exactly how he achieved it, but he might have been using the same idea that Lui Hui did of taking polygons with progressively more sides. 355 over 113 is accurate to within an error of less than 3 parts in 10 million. And this would be the most accurate approximation to pi that would be found for well over 1,000 years. It's also an easy number to remember, especially if you think of fractions the way the Chinese thought of fractions and the way they still do, which is that you give the denominator first and then state the numerator. I've always thought this makes a lot of sense because the denominator tells you what kind of thing you're talking about in the fraction, and the numerator then tells you how many of these you've got. And so if you take this fraction, 355 over 113, and instead describe it as denominator 113, numerator 355, you've got 113,355, and that's a very easy sequence of numbers to remember. And as I said, it gives an extremely accurate approximation to pi. There's another problem that the Chinese worked with at this time, and it's a problem that I've alluded to in thinking about how you apply numbers to time. One of the problems as you try to apply numbers to time is that you've got different units to work with. You've got the day, you've got the lunar month, you've got the solar year, and how do you decide when all of these are going to line up? Now, obviously, astronomers all the way back to the Egyptians and the Babylonians must have worked with this. But the first time we actually see a method of solving this problem, knowing when different cycles are going to line up, comes to us from the Chinese mathematicians. And the first time that we see this is in a work called Sun Si Xuanqing, or Sun Si's Computational Canon. We don't know exactly when it was written, sometime between 280 AD and 473 AD. But what it does is to provide a method for finding out when different cycles are going to line up. It's something that today we call the Chinese remainder theorem. And the actual example that is given in the Sun Si Xuanqing is the following. We consider a cycle of length 3, and we are 2 units into that cycle. We consider another cycle of length 5, and we know that we are 3 units into that cycle. And we consider a third cycle of length 7, and we know that we are 2 units into that cycle. Now, another way of thinking about this, and the problem is, how long ago were all of these cycles lined up? And the situation is exactly equivalent to, we want to find a number so that when we divide it by 3, we've got 2 left over. How long has it been going through cycles of 3 until we get 2 into a cycle of 3? Take this number, divide it by 5, and we want a remainder of 3. So again, how many times do you go through a cycle of 5 and then go 3 more into it? And we want a number which also divided by 7 leaves you with a remainder of 2. The answer to this is 23, that you have to back up 23 time units to get all of these lined up. 23 divided by 3 leaves 2. 23 divided by 5 leaves 3. 23 divided by 7 leaves 2. Now, in this work, the method for finding these solutions is not explained, but it does give an indication that this was being studied, and a little bit later I'll talk about one of the Chinese mathematicians who actually did find a method for proving it. The next significant mathematician to come along comes at the very beginning of the Tang Dynasty. The Tang Dynasty began in 618, it ended in 907. And one of the very important people at the beginning of the Tang Dynasty was Lei Chunfeng. He was the director of the Astronomical Observation Service, and of course, as the chief astronomer of the Tang Dynasty, he would also be the chief astrologer of the Tang Dynasty. And if you're setting up a new dynasty and you're deciding where to locate your capital and how to build your main buildings, you need to know what the astrological prognostications are. What is a good time at which to launch a particular endeavor? And so Lei Chunfeng became very important for his astronomical work. But even more important than that, he looked back at all of the mathematics that had been done in China up until that point. And he was given the task of trying to pull it all together. What had happened over the centuries is that many of these mathematical texts had been corrupted. They had been copied and recopied and recopied, and mistakes had crept in. And there were places where different versions contradicted each other. There were different methods in different books that contradicted each other. And so Lei Chunfeng took on the responsibility of taking all of the mathematics that was known in China at that time and pulling it together in what would come to be known as the 10 computational canons. This is a work that was done over the period 644 to 648 AD, and while it's called the 10 computational canons, in fact, they did pull on more than just 10 mathematical works. There were probably at least 12 or 13 different mathematical works that were combined into this. And not only did they take these works and correct the corruptions that had come into them, but they also provided extensive commentaries. And so, much in the same way that Euclid in 300 BC took all of Greek mathematics and re-established it, clarified it, and made a foundation on which further mathematicians could build, Lei Chunfeng did exactly the same thing for Chinese mathematics in the middle of the 7th century. From here, Chinese mathematicians would begin to work on problems of general polynomials. And it's not quite clear when they began to work with polynomials and exactly how the work that they did with polynomials related to the work that was being done on polynomials in India. In the next lecture, I'll also be looking at Islamic work in mathematics, and we're going to see polynomials coming in and playing a very important role there. And so we've got three great centers toward the end of the first millennium AD that are all working, getting to this idea of a polynomial of general degree. We would love to know how they interacted, if there was any kind of exchange. The fact that all three centers of civilization were working on similar kinds of problems at exactly the same time suggests that probably there was some kind of communication, although it probably was quite imperfect. One of the important Chinese mathematicians from slightly after the year 1000 was Jia Xian. Jia Xian was a court eunuch. He lived sometime in the middle of the 11th century. And Jia Xian is credited generally with being the first person to come across Pascal's triangle. Now, Pascal's triangle is a triangular arrangement of integers that has ones down the outside edge, and then the numbers inside are obtained by adding the numbers that are diagonally above it. So I've got 1 and then 2 ones, and the next row is 1, 2, 1, and the next row is 1, 3, 3, 1, and the next row is 1, 4, 6, 4, 1. This is named for Blaise Pascal because of the work that he did on this particular triangular arrangement of numbers in the 17th century. But in fact, even Blaise Pascal realized that it was much older than himself. His name was associated with it because of all the work that he would do on it. And the place that this comes from is the problem of expanding binomials. So I'm looking at a binomial, 1 plus x, so it's a two-term algebraic expression, and I want to begin to multiply it by itself. 1 plus x times itself is 1 plus 2x plus x squared. If I multiply that by 1 plus x, I get 1 plus 3x squared plus x cubed. And if I multiply that by itself, I get 1 plus 4x plus 6x squared plus 4x cubed plus x to the fourth. And if you look at those coefficients, those are exactly the numbers in Pascal's triangle. And so what Pascal's triangle does is it gives you an easy way of remembering or finding the coefficients as you take 1 plus x and take progressive powers of it. And the purpose of doing this, the reason that Jia Xian studied this particular triangular arrangement, the reason that he was looking at these binomial expansions, ways of getting the expanded polynomial out of 1 plus x raised to a power, is that this is a very powerful way of approximating the root of a polynomial, the place where a polynomial actually is equal to 0. And so we know that by the 11th century in China, these Chinese astronomers and mathematicians were interested in working with general polynomials and trying to find out those values at which the polynomial would equal 0. Now, for some polynomials, this happens at an exact integer or maybe a nice fraction. Most of the time, the location of this 0 is going to be some irrational number, some number that cannot be represented as a ratio of integers. And so the best you can do is to get a good decimal approximation to the number in question. And you can use Pascal's triangle, you can use these binomial expansions in order to get these roots to whatever accuracy you actually need. Now, this would be then developed by Li Qi. Li Qi, who lived 1192 to 1279, wrote a work that is known as the Zheyuan Haijing, which means mirror like the ocean, reflecting the heaven of calculations of circles. It's a bit of a flowery title. It's a book that was written in 1248, and it has a lot of mathematics in it. We find many geometric techniques, but he also specifically addresses this idea, the problem of finding roots of polynomials to arbitrarily high degree. And it's Li Qi who references Jie Xian and says that he got this idea, and in fact, by the time that Li Qi is writing, this method of using Pascal's triangle is called the old method. It was at least a couple of hundred years old at this time. But Li Qi, whose manuscript we do actually have copies of today, lays out in a great deal of detail how to find the roots of an arbitrary polynomial by using Pascal's triangle. Another one of the Chinese mathematicians who was also working at this time is Qinju Shao. He lived roughly 1202 to 1261. And one of the things that he did was to take the Chinese remainder theorem. So this is the problem of astronomical cycles, and you want to know when was the last time they all lined up. And if you know the last time they all lined up, that will enable you to determine the next time they will line up, and the time after that when they all line up. And so Qinju Shao, even though the Chinese remainder theorem had probably been solved earlier, he becomes the first person to actually explain how it works and show how to use it in any situation with any number of cycles of any length. And one of the examples that he gives is a number that is 32 units into a cycle of length 83. It is also 70 units into a cycle of 110, and it is 30 units into a cycle of 135. In other words, what we want is the smallest positive number, so that if we divide it by 83, the remainder is 32. If we divide it by 110, the remainder is 70. And if we divide it by 135, the remainder is 30. And I'll leave that out there as a problem for you to work on. I'll give you a hint. The number lies somewhere between 20,000 and 30,000. Chinese mathematics of this era would really come to its culmination in the late 13th century, under a time when Kublai Khan was the ruler of China. And one of the great works that was written at this time is the Siyuan Yujian, the trustworthy mirror of the four unknowns. Zhu Shijia was the author of this. It actually was written slightly after the time of Kublai Khan. It appeared in 1303, but it was built on a lot of work that had been done in China at the very end of the 13th century. And this is an incredible work for the sophistication with which Zhu Shijia was able to work with polynomials. I had mentioned when I talked about the Indian use of interpolating polynomials that a general formula for interpolating polynomials using not just first differences, second differences, but third differences, fourth differences, as far out as you might want to go. That's something that Isaac Newton discovered, and it's known as the Newton interpolation formula. But what we find here is the Newton interpolation formula in its full generality that clearly was known to the Chinese mathematicians at the end of the 13th century. Something else that Zhu Shijia was able to do at this time is to work with Pascal's triangle, this triangular arrangement of numbers, and find ways for combining these binomial coefficients. And so a result that would come later to be known as Vandermon's formula, and Vandermon was a European mathematician of the 18th century. Vandermon's formula was first discovered by Zhu Shijia. This is a formula for taking the sum of the binomial coefficients that come up on a particular diagonal, and then finding what they equal in terms of a binomial coefficient. The evidence is that Chinese mathematics begins to disappear after the 13th century, and that may well be due to the chaos created in China after the fall of Kublai Khan. China broke up into a lot of small warring states, and mathematics really stops being developed in China for quite a few hundred years. In the next lecture, we're going to switch to Islamic mathematics and the emergence of algebra. And one of the great questions that I would like you to keep in mind as we come into this next lecture is how much of the Islamic mathematics actually was drawing on what had been happening in China. We know that Islamic mathematics built heavily on what had been happening in India, but we're not sure how much Chinese mathematics influenced what would happen in the Islamic world. We've now looked at the development of mathematics in ancient Babylon, in ancient Egypt, also in the Greek world, in the Eastern Mediterranean, in India, and in China. And in this lecture, we're going to draw all of these different mathematical strands together in the Islamic world, what is usually referred to as Islamic mathematics. That does not mean specifically mathematics connected with the religion, but rather the mathematics that was encouraged by this entire Islamic culture in the Middle East. Some of the big ideas that we're going to look at are the creation of algebra, advances in number theory, and eventually we're going to come back to this Islamic period and look at Islamic art in a much later lecture. The Islamic period, of course, begins with the Prophet Muhammad. The Islamic calendar begins in 622 AD, when Muhammad flees Mecca to Medina. And I want to focus on the Abbasid Caliphate that began around 750 AD. A few years after the founding of this caliphate, the capital of the Islamic world was moved to Baghdad. And for the next several hundred years, Baghdad would be the cultural center of the Islamic world, and it would become a very important center for the development of science in general and mathematics specifically. The great Islamic leader who would sponsor a lot of this mathematical activity is Harun al-Rashid. He ruled from 786 until 809. And he decided that he wanted Baghdad to be this center of science and mathematics, and so he began collecting the great works and having them translated into Arabic. And we happen to know that the very first two works that he had translated were Euclid's Elements and Brahmagupta's astronomical work, the Brahmafutta Siddhanta. And so this shows immediately that Harun al-Rashid was drawing on all of the scientific accomplishments that were in existence, that were accessible at that time. Not just from Greece and the Hellenistic world, but also from India and South Asia, probably also to some extent from China, and then also drawing on the local tradition, that there had continued to be a strong astronomical, astrological, mathematical tradition in Mesopotamia. Baghdad is located in Mesopotamia, in what today is Iraq, and there still was a strong mathematical tradition that could be drawn on in this particular work. His successor, Abu Ja'far al-Mamun, who ruled from 813 to 833, would go a step beyond this, not just translating works into Arabic and building a great library, but also actually establishing the Bait al-Hikmah, or House of Wisdom. And so he set himself to do what Ptolemy I had done in Alexandria many centuries earlier, set up a center for scholarly work that was built around a library, where you would bring people together to look at what had been accomplished and create new insights. One of the first people who did this was Abu Ja'far al-Khwarizmi. We don't know the exact dates for al-Khwarizmi. He was probably born late in the 8th century and died sometime in the middle of the 9th century AD. And he wrote one of the most important books in the history of mathematics, the condensed book on the calculation of restoring and comparing, which sounds like a very strange title. This is actually considered to be the first book of algebra. And I've talked a bit about the development of the idea of algebra, how you can go back to ancient Babylon and find problems that today we think of as algebraic problems that were being done by the Babylonians, certainly problems that we would think of as algebraic problems being done by the Greek mathematicians. But algebra itself did not yet exist. And I talked about Diophantus and how he introduced the idea of a single letter as a variable and the idea of an actual notation for a quadratic polynomial or a cubic polynomial. But algebra, as it is now considered, did not yet exist. What al-Khwarizmi did was to consider the idea of an algebraic equation, and he's the person who comes up with this idea. The two words that he's using, restoring and comparing, the actual Arabic words are al-jabra and al-muqabala. And so this is restoring and comparing. He comes up with the idea of setting up an equation where you have two quantities that both involve your unknown. For example, you might have something like the unknown squared is equal to 10 times the unknown plus 22. So you've got an algebraic expression. And the problem then is to try to find a root or a place where this expression actually is equal, where you've got equality on both sides. And what al-Khwarizmi does is he explains how to keep the equation in balance by adding the same amount to both sides, or subtracting the same amount, or dividing both sides by the same amount. And so this is the process of comparing and restoring. And his word al-jabra is the origin of our word algebra. It's simply a transliteration of the Arabic word. His name, incidentally, al-Khwarizmi, is also the origin of our word algorithm, a word used in mathematics to mean a procedure that needs to be followed. And al-Khwarizmi laid out this idea of the procedure needed to be followed in order to keep the equations in balance. Now, al-Khwarizmi's algebra didn't look anything like our present algebra. He did not have the kind of algebraic notation that we use today. He did not use single letters to represent the unknowns. He would express those in terms of actual words, talking about the unknown and the square of the unknown. You didn't have an equal sign. That's something that would be invented in Western Europe in the 16th century. But you did have this idea of an algebraic equation. And that would be an important breakthrough moment that would really lead to a lot of the development of the idea of algebra. Al-Khwarizmi is also responsible for taking the idea of Hindu numerals. At this point, the Indians are using a full decimal system in the way that we use it today. They have the 10 digits, 0 through 9. They're using it in a place value system where you don't have to have a special symbol to denote what place you're in. You don't need tens, hundreds, thousands as symbols because you have the 0 as a placeholder. And it's al-Khwarizmi who realizes how useful this representation of numbers is. And it's al-Khwarizmi who is really responsible for spreading this idea of how to represent numbers across the Islamic world. Now, there are some problems that the Islamic algebraists and mathematicians still had to wrestle with. One of these was the question of whether or not to use negative numbers. And in fact, most of the Islamic mathematicians of this time refused to use negative numbers. In some respects, this goes back to Al-Khwarizmi. While he was willing to describe an algebraic equation, he still thought about its solution geometrically, in the same way the Babylonians did or the Greeks did. And if you're thinking about this algebraic equation geometrically, it doesn't make sense to talk about a negative length. And so negative numbers generally were avoided. Now that made life a lot harder when you were trying to describe how to solve a quadratic equation. So an equation that involved a quadratic polynomial, because if you've got something like x squared plus 10x is equal to 39, you can try to subtract the 39 from both sides, but you don't want to actually work with a negative 39. And more important than that, there are actually two solutions to this quadratic equation. There is 3, and the other solution is minus 13. And Al-Khwarizmi and the Islamic mathematicians of his time would only accept 3 as a legitimate solution to this particular quadratic equation. The next mathematician that I want to talk about is Thabit ibn Qurra. He also lived in Baghdad from about 836 AD to 901. He did important work in astronomy, geometry, mechanics, and he also worked in number theory. One of the interesting things that he did that I'd like to say a little bit about is his work on amicable numbers. Now, this is actually a problem that comes down to us from the Greek mathematicians. And what the Greek mathematicians would do is to take a number, look at its proper divisors, so the positive integers less than that number that divide evenly into, and add those up and see what number you get, and then repeat this process. So if I start with 12, its proper divisors are 1, 2, 3, 4, and 6. If I add those up, I get 16. If I now take the proper divisors of 16, those are 1, 2, 4, and 8. If I add those up, I get 15. If I now take the proper divisors of 15, they are 1, 3, and 5. If I add those up, I get 9. The proper divisors of 9 are 1 and 3. They add up to 4. The proper divisors of 4 are 1 and 2. They add up to 3. And 1 is the only proper divisor of 3. So this process started with 12, went up to 16, and eventually comes down to 1. Do we always come down to 1? No. And a simple example is the number 6. If I start with 6, and I add up its proper divisors 1, 2, and 3, I get back to 6. 6 is what the Greeks called a perfect number, because when you add up its proper divisors, you get back to the number itself. Now, another example of a perfect number is 28. Its proper divisors are 1, 2, 4, 7, and 14. Add those up, and I get 28 again. So one of the possibilities as you do this is you might come right back to the number that you started with. Something else can happen. If you start with the number 220 and add up its proper divisors, you get 284. If you take the number 284 and add up its proper divisors, you get 220. 220 turns into 284, 284 turns into 220. These are called, and they were called by the Greeks, amicable numbers, friendly numbers. The Greeks found this pair, 220 and 284. They also found another pair, 1184 and 1210. And it was Thabit ibn Qurra who went on and found the next pair, 17,296 and 18,416. That knowledge eventually would be lost to Western mathematicians. It would not be known to the people working in Europe centuries later. And in the 18th century, the great mathematician Leonhard Euler would re-find precisely this pair of amicable numbers that Thabit ibn Qurra had found and be very excited and quite pleased that he had been able to find this result that had in fact been found many hundreds of years earlier. The next mathematician I want to talk about is Abul Hasan al-Uqladisi. Again, we don't know exactly the years he lived, but he was sometime in the middle of the 10th century. We know that he lived in Damascus. And one of the books that he is best known for is the Kitab al-Fusal fi al-Hisab al-Hindi, or the Book of Chapters on Hindu Arithmetic. As I said, al-Khwarizmi was important for urging the adoption of the Hindu method of representing numbers. This particular book really shows how effectively this Hindu decimal system can be used in order to do calculations. And one of the things that we find in this book by al-Uqladisi is the first use outside of China of decimals to represent fractions. And there is a page from one of his books that I'm showing up now. If you go down to the 10th line of this page from al-Uqladisi's book, the stretches of Arabic writing that have a line over them represent numbers. And if you go down on this 10th line, you will see a number that has a hash mark over one of the digits. And that hash mark is used to mark where the units are. Now, of course, instead of reading the number from left to right, you read the number from right to left in the Arabic fashion. And so you read it from right to left. When you get to the hash mark, that designates that you're now in the ones place, and the next digit is representing tenths, and the digit after that is now representing hundredths. And it's al-Uqladisi who manages to convince the Islamic mathematicians to begin using this idea of decimal fractions. I would love to know whether they borrowed this idea from the Chinese, who had been using it for many hundreds of years up until now, or if this was an independent discovery of this powerful way of representing fractions. The next mathematician I want to talk about is Abu Bakr al-Karaji. Again, we don't have exact dates on him, but he was born sometime late in the 10th century and died sometime in the early 11th century, perhaps around 1030. He also would live in Baghdad. The book that he is best known for is Al-Fakhri, which means the marvelous. And one of the things that he does that will be extremely important as we look at the further development of mathematics is this idea of taking the unknown and raising it to an arbitrary power. So you can take the unknown and you can square it or cube it or take it to the 37th power. You can also take it to a power that is a negative number. So he talked about how to represent the reciprocal of the unknown by using a negative power. So x to the minus 2 is the same as 1 over x squared. So he was working with positive exponents, negative exponents, and he pointed out how useful these exponents are because of the way that they combine. If I have x raised to the 3rd power and I multiply that by x raised to the 5th power, I can combine those just by adding the exponents. That's going to give me x raised to the 8th power. And he states the general rule that the unknown raised to the mth power times the unknown raised to the nth power is equal to that unknown raised to the m plus nth power. And the same thing is happening if you take x to the m divided by x to the n. That's going to be x to the m minus n. This is also the mathematician who would be credited by Al-Samaval, a 12th century Islamic mathematician, with being the first Islamic mathematician to discover Pascal's triangle. Now, unfortunately, we do not have any independent evidence that this really was the first Islamic mathematician to discover Pascal's triangle. If he was, he lived before Jiaxian, and so that suggests that perhaps Pascal's triangle came up first in the Islamic world. We're uncertain about this. Whatever happened is that amazingly in the 11th century, Pascal's triangle appears both in China and also in the Islamic world. And it would be wonderful to know if there was some kind of communication between them. Did one of them discover Pascal's triangle and then share the information with the other? Or was it just that both of them were working with this problem of arbitrary polynomials? And inevitably, as you begin to work with polynomials of arbitrary degree, you begin to come across Pascal's triangle, this idea of these powers of the binomial 1 plus x. And what we find in the Islamic world, just as there was in China, Pascal's triangle comes up as a method for finding roots of arbitrary polynomials. One of the most interesting mathematicians from the Islamic world was Abu Ali al-Haytham, born in Basra sometime around 965 AD. Al-Haytham was an engineer, and he made his reputation in Basra in southern Iraq early in his career. And then sometime around the year 1000, he was enticed to come to Cairo. Now, Cairo had been founded as the capital of the Fatimid Caliphate in 969. And one of the first things that was constructed in this brand new city of Cairo was a mosque, the Al-Azhar Mosque. And one of the first things that was done at the Al-Azhar Mosque was to create a school of learning. And this would continue to be a continuously operating center of learning ever since its founding in 975. In 996, Al-Haytham would become the caliph. He was only 11 years old at the time, and he would become known as someone who was quite cruel, quite eccentric, but he also was someone who was very interested in developing the sciences, and so he went out and found good scientists to bring into Cairo to help build the scientific community in this city. And Al-Haytham was one of the people that he brought in. Now, Al-Haytham was initially brought in to be an engineer, and actually the job that he was given was to travel south along the Nile River and find a place to construct a dam so that they could control the flow of the Nile. Al-Haytham traveled upriver and discovered that the job was simply well beyond the engineering capabilities of that time. He never built the dam. And when he came back to Cairo, he became rather afraid of the caliph because of his tendency both to be capricious and also cruel. And so Al-Haytham feigned madness. He disappeared into his own house. But while he was doing that, he was developing his mathematics and his science. And one of the areas that he really worked on very extensively is optics. So understanding how mirrors operate, and especially mirrors of different shapes, spherical mirrors, scientific mirrors. He would actually publish 92 scientific works, many of which dealt with optics, many of which dealt with mathematics, other scientific topics. 55 of Al-Haytham's books still survive today. Among the mathematics that he did was to work with the Chinese remainder theorem. Again, it's not clear if he was drawing on the Chinese tradition or if he came up with it independently. He came up with something that would later be known as Wilson's theorem, and that's the observation that if you have a prime number like 7, and you take the product of all of the integers that are less than that prime, so you take the product of the integers from 1 up to 6, and then add 1 more to it, that number will always be divisible by that prime. So the product of the integers from 1 to 6 plus 1 is 721, and that's divisible by 7. 11 is a prime. The product of the integers 1 through 10 plus 1 gives you 3,628,801, and that number is exactly divisible by 11. Al-Haytham didn't just observe this, he actually was able to prove this particular result. He was using polynomials in their fully general sense, and he was able to take Archimedes' ideas for finding areas, finding volumes, using the method of exhaustion. And he really pushed these much further than anybody had been able to do before. One of the volume problems that Archimedes was able to solve is the problem of finding the volume of a paraboloid. So we consider a parabola, and we take the line of symmetry, and we then rotate this parabola around the line of symmetry, and that gives you a kind of bullet shape. And that bullet shape is what is called a paraboloid, and Archimedes had figured out how to find the volume of a paraboloid. The problem that Al-Haytham tackled was to take this same parabola and rotate it a different way. What he did was he just took half of the parabola, say we take the top half of the parabola, and then we take a vertical line that chops this arc of the parabola at some point, and we rotate that piece of the arc around the vertical line. What we get is a solid that looks very, very different from the paraboloid of Archimedes because it's a solid that comes to a point. And you can actually see this solid of Al-Haytham that is in the domes of many of the mosques. This would become a common motif for Islamic mosque art. And what Al-Haytham does is to work out the volume of this particular solid of revolution obtained by rotating a parabola, but in a very different way from the way in which Archimedes did it. He does this by slicing his particular solid of revolution in much the same way that Archimedes does. But the problem's much harder. What Archimedes was able to show is that in order to find the volume of the paraboloid, you really only need to be able to find the area of a triangle. And you can reduce one problem to the other problem. For Al-Haytham, trying to find the volume of his solid of revolution, what he needed to be able to do was to find a formula for adding up the fourth powers of all of the integers from 1 up to n. 1 to the fourth plus 2 to the fourth plus 3 to the fourth, all the way up to n to the fourth. Now, the sum of the integers from 1 to n, that particular formula had been known since far antiquity. In fact, that's so old, we have no idea where it first came from. It was certainly known to the earliest Greek mathematicians. It was known to the earliest Indian mathematicians of whom we have any record. That formula was well known. If you consider the sum of the squares, 1 squared plus 2 squared plus 3 squared up to n squared, that particular formula, it gives you a cubic polynomial in n, that also was known to Greek mathematicians. The sum of cubes, 1 cubed plus 2 cubed plus 3 cubed up to n cubed, that involves a fourth degree polynomial. We don't know when that was first discovered. It might have been discovered by the Greek mathematicians. It was certainly known to the Indian mathematicians by the middle of the first millennium AD. But Al-Haytham needs to go beyond this. He needs to add up fourth powers. And one of the things that he does is to find the fifth degree polynomial that gives you the sum of the fourth powers. And beyond that, he comes up with a general procedure that can be used to find the sum of fifth powers or sixth powers or any powers beyond that. I want to talk just briefly about a few of the other important mathematicians who would appear in the Islamic world after Al-Haytham. The first of these is Ibn Yahya al-Samaval, lived sometime in the middle of the 12th century in Baghdad. This was well after Baghdad's heyday. Baghdad was no longer the place to go for mathematical and scientific work. But nevertheless, al-Samaval did become a very important mathematician. He was actually trained as a medical doctor. He was Jewish, and he's one of the first Jewish mathematicians that we know of from history. Eventually, in middle age, he did convert to Islam. He worked with polynomials, and he really understood the full power of polynomials. And he is someone who is able to explain how to take a polynomial and divide it by another polynomial. It's something that today we call synthetic division. And just as if you take one number and divide it by another, you begin to get a decimal expansion that may keep on forever. There may be no end to the decimal expansion. Say if you're going to take a number like 3 and divide it by 17, the decimal expansion repeats, but it never ends. So I'll realize that if you take one polynomial and divide it by another, what you're going to get are negative powers of the unknown appearing. So you'll get a term in x to the minus 1 and a term in x to the minus 2. And he realized that these negative powers could well continue forever. He is also someone who did a lot of work with Pascal's triangle. It turns out that there's a very clever formula for finding the sum of second powers, third powers, fourth powers, whatever power you want to fix on, you can find a formula for the sum of those powers using Pascal's triangle, using the numbers in Pascal's triangle. And Al-Samawal, we believe, was the first person to discover this. One more mathematician I want to mention just very briefly is Omar al-Khayyami, 1048 to 1131, lived in Isfahan. The very famous Persian poet. What many people don't realize is that in addition to being a poet, he also was a very accomplished mathematician. And he was particularly interested in the problem of finding the exact value of the roots of a cubic polynomial. And he made progress on this. He was not able to finally solve this problem. It would actually take about 400 years before this problem would be solved. And it would be solved in Western Europe by Italian algebraists. This would be the first mathematical accomplishment of the European world, the Western European world, and that will be the topic of my next lecture. In the last lecture, we looked at the Islamic mathematicians. In this lecture, we're going to look at the Italian algebraists. So these are people who learned from what the Islamic mathematicians had done. One of the most important insights of the Islamic mathematicians was the significance of our Hindu-Arabic decimal system, in which you have 10 digits that can represent the different powers of 10, and so the power of 10 is determined by the place value in which you put the digit. And this Hindu-Arabic system of denoting numbers would be used throughout the Islamic world. And by the 12th century, Italian merchants who were working in North Africa would begin to pick this up. They would also begin to learn about the Islamic methods of doing algebra, doing geometry, and doing other mathematics. One of the most important Italian mathematicians of this time was Leonardo of Pisa. He sometimes wrote his name as Leonardo Pisano, and he also sometimes wrote his name referring to the family that he was from, the Bonacci family. He referred to himself as a son of Bonacci, or Fibonacci in Italian. And today he is best known by this particular name, simply Fibonacci. He spent much of his early life in Algeria. His father was actually an Italian diplomat in North Africa. And we know that Fibonacci spent a lot of time learning mathematics, not just common arithmetic, but also more advanced mathematics, algebra and geometry. And around the year 1200, he returned to Italy, to Pisa. He would live the rest of his life there, and he would work on mathematics, and he published some of the most important early works in mathematics that would appear in Western Europe. And so we find one of the first books, the Liber Abaci, literally the book of calculations, in which he explains for the Italian audience this strange method of representing numbers using the base 10 system, using the Hindu-Arabic numeral system. This is also the book where we find what is known as the Fibonacci sequence, the very famous sequence of integers that begins 1, 1, 2, 3, 5, 8, 13. And each of the numbers that we get in this sequence is the sum of the two previous numbers. So 5 and 8 is 13, 8 and 13 is 21, 13 and 21 is 34. So we get this sequence. Fibonacci was actually looking at this sequence in order to count the number of rabbits you would have after a certain number of generations. Although we call it the Fibonacci sequence, it actually is much older. It's a sequence that was known to Islamic mathematicians, to Indian mathematicians. You can even trace it back to the Greek mathematicians of the classical age. They certainly were aware of this particular sequence, and it's a fascinating sequence. There are all kinds of things you can do with it. One of the classic examples is looking at the seeds in a sunflower head. And if you follow one of the spirals, the number of seeds in a given spiral is always going to be a Fibonacci number. And you can actually follow the spirals around in two different directions, and the two numbers are going to be consecutive Fibonacci numbers. Now, in addition to writing his book on calculations, Fibonacci also wrote on geometry, he wrote on algebra, and he wrote on Diophantine equations. So these are equations from number theory in which you're only looking for integer solutions, things like the Pythagorean triples, where the square of one number, square of an integer, plus the square of another integer is equal to the square of an integer. And Italy, especially northern Italy, would begin to become an important center for the study of algebra. And most of the study of algebra actually was centered on the city of Bologna. Bologna was the site of the first of the great Western European universities. It was founded before the University of Paris, before Oxford or Cambridge. It was around 1088 that the university was first founded in Bologna. And one of the mathematicians who taught there in the 15th and early 16th century was Scipione del Ferro. And del Ferro was interested in the problem of finding a root of a cubic polynomial. So this is a polynomial of degree 3. And I need to say a little bit about finding the roots of a polynomial. You've got a polynomial equation. You're trying to find out where that's equal to 0. And in the last lecture, I talked about some of the Islamic methods, and before that, Chinese and even Indian methods for finding roots of polynomials. One approach is to try to find an approximation to the value that satisfies a given polynomial equation. In other words, trying to find an approximation to the root. Ideally, what we'd like to do is to find an exact value for that root, the exact number that satisfies it. And if we're working with a quadratic polynomial, a polynomial of degree 2, then it is possible to find the exact value using square roots and what's commonly referred to as the quadratic formula. That gives you an exact value for the root. And this is the question that del Ferro was pursuing. Is there a way of finding an exact value for a root of a cubic polynomial? Now, today when we think of cubic polynomials, it's degree 3, and usually we want to write down all 3 roots. But in fact, you only really need to be able to find one of those roots, because if you can find one root of a given polynomial, then you can divide that polynomial by the linear factor, by the factor of degree 1, x minus that root, and you're going to get a polynomial of one lower degree. So if I've got a polynomial of degree 3 and I can find one root for that polynomial, I can then translate that polynomial into a polynomial of one lower degree, a quadratic polynomial, and now there's standard methods for finding the roots of the quadratic. So the real problem is just to find one root of the cubic polynomial. Once you do that, you've simplified the problem down to finding the root of a quadratic polynomial or a polynomial of degree 2. Del Ferro succeeded in doing this. And he shared his discovery with two other people. One was a colleague by the name of Annibale Della Nave, and Della Nave is going to appear again later in this story. And another person that he shared the secret of how to find a root of a cubic equation with was Antonio Fiore. Now, finding this root of the cubic polynomial, of an arbitrary cubic polynomial, would turn out to be extremely important, because this is really the first time in the modern Western European tradition that mathematicians actually were able to go beyond what the ancient Greeks had accomplished. And so this was really showing, this now happening in the early 1500s, that European mathematicians of this time were actually able to go beyond what the ancients had managed to accomplish. Finding the root of a cubic polynomial was a very important watershed. It also was important for the individuals who were able to do that, because at this time, if you wanted to be a scientist or a mathematician, you needed to have a patron, you needed to have a sponsor. You really couldn't survive on your own. You could teach some math classes, but that didn't bring in very much money. And one of the ways to get a sponsor was to engage in competitions. And so one patron would take his mathematician, and another patron would take his mathematician, and the two mathematicians would have a competition. And whichever patron had a mathematician that was able to win, well, certainly that brought great glory to the given patron. And so mathematicians who knew how to find the roots of a cubic polynomial now suddenly had a great advantage in these competitions. And one of the important early competitions took place between Fiore and another mathematician by the name of Niccolò Fontana. Fontana is better known as Tartaglia the Stammerer, and he got his name because as a young man in Brescia, where he grew up, one day while he was quite young, the French corsairs came through the city. They were raiding the city, and Fontana was slashed with a saber, and he suffered quite a deep gash across his face. Apparently, it never healed properly, and so he had a speech impediment for the rest of his life. And from that, he developed the nickname the Stammerer, or Tartaglia. And Fontana, or Tartaglia, would turn out to be quite unfortunate throughout his entire lifetime. But he was a brilliant mathematician. And when he heard that Del Ferro had discovered how to find the roots of a cubic polynomial, or to find one root of a cubic polynomial, he began to explore this question for himself, and he discovered how to do it. And he then challenged Fiore to a competition. Now, Fiore had learned how to find the roots of a cubic polynomial, but Fiore was not a great mathematician. This was basically his entire bag of tricks. On the other hand, Tartaglia was quite accomplished. He had figured out how to find the roots of a cubic polynomial, but he also knew how to solve many other mathematical problems. And so when they held this competition, Tartaglia posed many different problems, not just finding roots of cubic polynomials, while Fiore only posed the question of finding roots of cubic polynomials. And Tartaglia went away from the competition with Fiore with a great deal of glory, because he was able to answer all of Fiore's questions, and Fiore was able to answer none of Tartaglia's. Another mathematician who then became interested in this question of the roots of a cubic polynomial was Gerolamo Cardano. Born in 1501, would die in 1576, certainly one of the greatest of the Italian algebraists of the 16th century. He was from Milan. He was the son of a very prominent law professor, scholar of law in Milan. Somewhat spoiled. He had quite a reputation as a gambler, and that tied into his mathematics. He actually did a lot of early work on probability. He also became known as a quite accomplished mathematician, but the one thing he was not able to do was to figure out how to find a root of an arbitrary cubic polynomial. And so he wrote to Tartaglia and asked Tartaglia to share the secret of how to find the root of a cubic polynomial. He invited Tartaglia to come to Milan. Tartaglia did so, thinking that Cardano might be able to find a patron for him. Despite his success in this competition against Fiore, Tartaglia had not been able to find himself a patron. And so he went to Milan hoping that Cardano could help him with this. Well, he went there and he shared the secret of how to find the root of a cubic polynomial with Cardano. Cardano, however, did not find a patron for him at the time. Tartaglia asked Cardano to keep this a secret because Tartaglia wanted to use this in order to arrange for patronage for himself. Cardano said, "Okay, but please publish it. I would like to be able to talk about this method for finding the root of a cubic polynomial." Tartaglia went home hoping to get this patronage, which never came. Cardano was waiting in Milan for Tartaglia to actually publish the result so that Cardano could then publish more about it himself. And so both were waiting for the other. Eventually, Cardano went to Bologna, and there he met Della Nave. Della Nave was that colleague of Del Ferro that I talked about earlier in this lecture. And Cardano learned from Della Nave that, in fact, this secret of how to find the root of a cubic polynomial was already known, had been known long before Tartaglia. Cardano, up to that point, had only known about Tartaglia's discovery of how to find the root of a cubic polynomial. And once Cardano realized that there were others who knew about this, he felt that he had been released from his promise. And so he went home and he now published his great work in algebra, the Ars Magna, literally the Great Art, in 1545. And in that book, despite his promise to Tartaglia, he explained the method for finding the root of a cubic polynomial, which won him the eternal enmity of Tartaglia. At the same time, there was another young potential mathematician growing up in Bologna, Lodovico Ferrari. Ferrari was born in 1522 and would die in 1565. Ferrari's father died when he was quite young, and he went to live with his uncle. And one of his uncle's sons, Ferrari's nephew, had traveled to Milan and gotten a job as a servant to Cardano. And apparently Ferrari's nephew didn't like being a servant for very long, and after a few months he simply left without giving Cardano any warning. Cardano was quite upset, and so he wrote to the young man's father and said, "You must send him back. I need him as a servant." The father, Ferrari's uncle, was reluctant to force his son to go back, so he took his nephew, the young Lodovico Ferrari, and said that he had to go back and serve as a servant to Cardano in his place. This actually turned out to be a great stroke of luck for Lodovico Ferrari, because he went to Cardano, and Cardano immediately recognized that this man had a great deal of mathematical talent. And so rather than being simply a servant to Cardano, Ferrari quickly became a secretary, and Cardano undertook to teach him the mathematics that he knew. And Ferrari was very accomplished in this, and very quickly went beyond what even had been done by Cardano. He was able to take a look at the way of finding the root of a cubic polynomial, an exact formula for the root of a cubic polynomial, and expand this idea so that he was able to find the exact value of the root of an arbitrary polynomial of degree 4. So he went from polynomials of degree 3 to degree 4. Shortly after that, an academic position with a patronage opened up in Brescia. And Ferrari decided to apply for this position. Tartaglia was still stewing. He was in Venice at this time, and he decided also to apply for this position in Brescia. And in order to decide who would get the position, a competition was arranged between Ferrari and Tartaglia. And Ferrari was such an accomplished mathematician that in the first day of this, and one can imagine what it must have been like, there would have been a stage set up in the plaza with the two mathematicians facing each other, and one would propose a problem and the other had to work it out in front of the crowd. And then if he did it successfully, he would then propose a problem to the other one, who then had to work it out in front of the crowd. And it must have been a great scene. But at the end of the first day, it was quite clear that Tartaglia was falling behind. There were a lot of Ferrari's posed problems that Tartaglia was unable to solve. But Ferrari was able to solve all of the problems that Tartaglia posed. And so Tartaglia left before the competition was over. At the end of the first day, he fled in disgrace. He had clearly lost the competition. Ferrari was exultant that he had succeeded. He was entitled to this position with patronage in Brescia, but his fame was such. He had bested Tartaglia. His fame was such that he was able to take any job, essentially, that he wanted in North Italy. And so he went back to Milan and got a job as the tax assessor for the city of Milan, a position that I'm sure was extremely lucrative. He would continue to do mathematics, but he quickly became a very wealthy man. Now, before I go on to the next mathematician I want to talk about, who is Bombelli, it's important to say a little bit about the method for finding the root of an arbitrary cubic polynomial. So I've got a polynomial equation of degree 3. So I've got some polynomial that involves x cubed, and I want to find an exact value for one of the roots. Now, it's always possible to translate the variable, to move the variable so that you can write this cubic equation in the form x cubed plus some number times x is equal to a constant number. As an example, we might take the cubic polynomial x cubed plus 6x is equal to 4. And we now take two numbers. We take that constant number 4, and we take the coefficient of the x. I had x cubed plus 6x equals 4. I take that 6. I divide it by 3. That gives me 2. And then I cube that number. I multiply 3 copies of that number together. 2 times 2 times 2 is 8. So my two key numbers for this particular cubic equation are 4 and 8. And the key to finding a root of this cubic equation is to find two numbers whose difference is the 4 and whose product is the 8. Now, this is an old problem. It goes right back to the Babylonians. You know the difference between two numbers. You know the product of two numbers. You want to find out what those two numbers are. And that's a problem that can be restated in terms of solving a quadratic polynomial. And we know how to find the exact value of the solution of a quadratic polynomial. In this particular case, the two numbers whose difference is 4 and whose product is 8 are 2 plus twice the square root of 3 and minus 2 plus twice the square root of 3. So if I take the difference of those, I get 4. If I take the product of those, I get 8. I take those two numbers that I have found, 2 plus twice the square root of 3 and minus 2 plus twice the square root of 3, and I take the difference of their cube roots, and that will give me a root of the original equation. Now, the next mathematician I want to look at is Raphael Bombelli. Bombelli was born in 1526 in Bologna. He actually worked as an engineer. He was not trained as a mathematician. He did not intend to be a mathematician. But Early on in his career, he was commissioned to go up to the Val di Chiani, so this is a high mountain valley that's north of Rome, and to drain the marshes there. Today, the Val di Chiani is a very fertile land, a very important agricultural area. But at the time that Bombelli went up there, it was all marshland. So he was sent as an engineer to drain those marshes. And he succeeded in doing it, but it wound up taking him 9 years to get these marshes drained. And the reason for it is in the middle of that 9-year period, there was a 5-year hiatus in which there was a dispute over who actually owned the land that was in that particular valley. So Bombelli was up there in the Val di Chiani, cooling his heels, waiting for word to come through to begin to proceed with the work once the dispute over who owned the land was over. And during that 5-year period, he was reading algebra. He was reading the work of Cardano, and he was very impressed with what Cardano had done, but he decided that he could do an even better job. And so he began to write his own book on algebra. But once the marshes at the Val di Chiani were drained, Bombelli had made his reputation as an engineer, and he was brought to Rome by the Pope for a couple of engineering projects that the Pope had in mind. The first of these was to restore the Santa Maria Bridge. This is one of the ancient bridges of Rome, spans the Tiber at a very important crossing point. And periodically it had been destroyed over the years by various floods. And after one of these floods, the Pope brought Bombelli in to try to restore the bridge. Ultimately, Bombelli was not successful, and I do have a picture of what the Santa Maria Bridge looks like today. As you can see, it's not very appropriate for trying to get across the Tiber. People finally abandoned any attempt to restore the Santa Maria Bridge in 1598, and today it's simply known as the Ponte Rotto, the broken bridge. Another one of the jobs that the Pope had for Bombelli was to try to drain the Pontine Marshes. This also Bombelli was not successful in, and actually the Pontine Marshes, which are a great coastal marshland south of Rome, they would not be drained until the 1920s. It would be under Mussolini that eventually these marshes would be drained. But while he was in Rome, Bombelli discovered Diophantus's Arithmetica. So this is the great work on number theory and Diophantine equations that Diophantus had written in the early centuries AD. And he began to translate this work and to see how to incorporate it into his own book on algebra. And so eventually Bombelli would produce a very, very important work in algebra that would go on to influence not just the Italian algebraists of the succeeding years, but also algebraists throughout all of Western Europe. But one of the most important insights that Bombelli had was the importance of being able to work with the square root of negative numbers. So let me take another cubic equation that I want to find the root for. I'm going to take x cubed minus 15x equals 4. And the two numbers that we're working with in this case are 4 and minus 15 divided by 3 and then cubed. So I want the difference between two numbers to be 4. And I want the product of two numbers to be minus 125. Now, that's a problem, because if I've got two numbers that are only 4 apart from each other, and the product of their magnitudes is 125, either these numbers both have to be positive or both have to be negative. I can't get a minus 125. So you can't find two real numbers whose difference is 4 and whose product is minus 125. But in fact, there is a root to this cubic polynomial. It's not too hard to see that 4 cubed minus 15 times 4 is 4. 4 is a solution. And so Bombelli wrestled with this question. The method of Cardano and Tartaglia and Del Ferro doesn't work in this case, but there is a solution. What's going on? It turns out that the key to this solution is to be able to work with the square roots of negative numbers. And Bombelli is the first person to start doing this. What he does is he shows that you get two solutions, one of which is the two numbers whose difference is 4 and whose product is minus 125. The numbers are 2 plus the square root of minus 121 and minus 2 plus the square root of minus 121. And if you take the cube roots of those numbers, you get 2 plus the square root of minus 1 and minus 2 plus the square root of minus 1. Well, 2 plus the square root of minus 1 minus 2 plus the square root of minus 1, take the difference, you get 4, you get the solution. So you get the solution, but on the way you need to work with these square roots of negative numbers. And so Bombelli is the first person to say, yes, we do need to work with the square roots of negative numbers. The square roots of negative numbers would later be called by Descartes imaginary numbers. That's a very unfortunate name. Descartes called them imaginary, and a lot of people seem to think that they don't exist because we call them imaginary. They are very important numbers. They're very real numbers in some sense, although we refer to the ordinary numbers as reals. As we're going to see several lectures hence, in the 18th century, these imaginary numbers become absolutely critical to proceeding with mathematics, to making advances in mathematics. The numbers that can be built out of real and imaginary numbers, the complex numbers, are really two-dimensional numbers. And I'll talk about these much more later. We've reached the end of the 16th century. Algebra at this point is pretty well understood. In the next lecture, we're going to be moving into the 17th century, the century that I said is the pivot for this entire series of lectures. We're going to spend 5 lectures on the 17th century. These developments in algebra undertaken by the Italian algebraists would lay the foundation for this. In the next lecture, we're going to go back to questions in astronomy. Astronomy led us into trigonometry, and in the next lecture, we're going to see some of the important ways in which astronomy would provide the motivation for the mathematics that would be developed during the 17th century. And in particular, we're going to focus on John Napier, a Scotsman, and his invention of the logarithm. In this lecture, we're going to move into the 17th century and look at the most important function to be discovered since the trigonometric functions, namely the logarithm and also the exponential function. Exponentials were certainly dealt with before the 17th century, but as a function, that really only begins in the 17th century. But before I start to look at logarithms and exponentials, I need to back up a bit into the middle of the 16th century and look at what was happening in astronomy, because that would directly influence what would then happen in the 17th century. 1543 is the year that Nicholas Copernicus published his groundbreaking work on the revolution of the heavenly spheres. Copernicus was a Roman Catholic monk in Poland, and he was trying to understand the motion of the planets. And in particular, he was very disturbed by this problem of retrograde motion, this apparent backward motion of the planets at certain times. And if you recall back when we looked at astronomy in ancient Greece, This was one of the problems that Archimedes raised, and a number of different Greek scientists, astronomers, looked at this problem. And one of them was Aristarchus, who suggested that what was happening was that the Earth was actually going around the sun, and that would explain this retrograde or backward motion of the planets. The problem with that explanation of Aristarchus was that we have absolutely no sense of a motion of the Earth. It appears that the Earth is stationary. And so that was quickly dropped in favor of a slightly later explanation that came from Apollonius of Perga, the same Apollonius who did the important work on conics. And it's Apollonius who came up with the idea of epicycles, that in fact the Earth is stationary at the center of the universe. And what is actually happening is that the planets are traveling around the Earth on little circles, whose centers then travel around the Earth. And this would become the foundation for what was known as Ptolemaic astronomy. Certainly there were many Greek astronomers before Ptolemy who established this system, but Ptolemy really showed how you could model the movement of the planets using these epicycles. And over the succeeding centuries, the system became more and more complicated because whatever system was in place never really matched what people were observing in the heavens. And so they tried the idea of equants. They tried putting epicycles on epicycles. They got very complicated models. And what Copernicus decided to do was to simplify this process, or try to simplify the process, by going back to the idea of Aristarchus and postulating that it was, in fact, the Earth that goes around the sun, rather than the sun that goes around the Earth. The problem with Copernicus's work is that he also assumed that everything went around the sun in a circle. And observations were sufficiently accurate by this time, the mid-1500s, that simply did not accurately predict where the planets should be. The planets weren't where they were supposed to be if, in fact, they were traveling in nice circles around the sun. And so a number of astronomers began to try to improve on this model and figure out what was really happening. Something else with Copernicus is that in his book on the revolution of the heavenly spheres, actually, he probably did believe that the Earth moves, but he simply puts it forward as a hypothesis, as a possible model. But succeeding astronomers began to suspect that maybe, in fact, the Earth is moving around the sun. But what was needed were much more accurate observations of the positions of the planets on which a better model could be built. And the person who undertook to find these observations was a Danish astronomer by the name of Tycho Brahe, born in 1546. He would die in 1601. He was a very wealthy nobleman. It's actually been estimated that at one point he personally owned 1% of all of the wealth in Denmark. And he set up an astronomical observatory on the island of Hven. It's just off the coast of Sweden, actually between what is now Sweden and what is now Denmark, although at that time what is now southern Sweden was part of Denmark. Brahe had studied astronomy in Copenhagen. He had then gone to Germany to continue his study of astronomy. While in Germany, he engaged in a duel where his nose was sliced off. And rather unfortunately, he went through the rest of his life with a tin nose, something that makes him very distinctive. We know that he also studied medicine and alchemy. He made two important observations in his observatory in Hven. The first, 1572, was a careful observation of a supernova. So a star suddenly becomes a brilliant light in the sky and then disappears. And Brahe observed this. And one of the things that this showed is that, in fact, the stars in the heavens are not eternal. They can appear out of nowhere. They can disappear. And so this began to undermine the Aristotelian view of the heavens. Something else that Brahe observed in 1577 was a comet. Now, if you really believe that the heavens are perfect, you can't have anything moving through the heavens. It was believed up until that point that comets were actually something that happened within the atmosphere of the Earth. And Brahe did very careful observations and measurements of the position of this comet, and he was able to show definitively that the comet, in fact, was well beyond the reach of the moon. It was well outside the atmosphere of the Earth, and so it really was moving through the heavenly rain. Brahe, you must remember, was working before the time of telescopes, and so all of the observations that he was making were being made simply by the naked eye with very accurate instruments to line things up, but without the aid of a telescope. Now, the best you can normally hope for in this case is to get an accuracy of about 2 minutes of arc. So 360 degrees is a full circle, and 1/60th of a degree is a minute. And actually, if there are two stars in the sky whose difference is less than 2 minutes of arc, it's very difficult to tell them apart. So that's normally about the best you can do with naked eye observations. Brahe actually was able to push that a little bit further. Looking back at his records, we now realize that sometimes he was able to get the position of the planets down to within half a minute of arc, very often within 1 minute of arc. But he had these incredibly accurate observations. In 1599, he was hired by the Holy Roman Emperor of the time, Rudolf II, whose capital was in Prague, to be the court astrologer. And as I mentioned in earlier lectures, there really at this time was no difference between a mathematician, an astronomer, and astrologer. So Brahe, as an accomplished astronomer, would also have been much sought after as an astrologer, trying to predict the position of the planets and interpret what that actually meant for what would go on Earth. And shortly after he became court astrologer, he hired a young assistant, Johannes Kepler. Kepler had been born in 1571. Shortly after Kepler became Brahe's assistant, Brahe died. And there was a story circulated at the time that the reason that he died was that he was at a banquet with the emperor, and he desperately needed to relieve himself, but being seated at table with the emperor, he could not simply get up and leave the table until the emperor was ready to get up and leave the table. And the story was that his bladder burst and he died of the infection. Well, about 50 years ago, Brahe's corpse was exhumed and examined, and I'm not sure how much of his bladder was left at that point, but they did an analysis of his hair and discovered that, in fact, he had died of mercury poisoning. Now, this raises all kinds of suspicions, because, in fact, Kepler benefited greatly from Brahe's death, and it has been suggested that perhaps Kepler had a hand in doing in Brahe. Kepler inherited Brahe's position as court astrologer to Rudolf II, and he also inherited all of Brahe's very valuable data. And it became Kepler's life work to take this meticulous data and try to find a model that would fit it. And Kepler eventually would succeed in doing this, but to do it, he needed to do very extensive calculations, very involved calculations. Eventually, he would come to the realization that the reason that Copernicus was off is that the orbits of the planets are not circles, they are actually ellipses. They're ellipses not with the sun at the center of the ellipse, but with the sun off at the focus of the ellipse. And so he realized that the data that Brahe had collected could be explained with this model. Kepler came up with other rules, other laws of celestial motion. He realized that the planets sweep out equal area in equal time, and practically what this means is that the planet speeds up as it comes in close to the sun, and then it slows down as it moves away from the sun. So it's not always traveling at the same speed. And another one of Kepler's laws is that the square of the time that it takes to complete an entire revolution is proportional to the cube of the average distance to the sun. Now, Kepler came up with many other laws. In many respects, he really was an astrologer and a mystic. He explained the relative distances of the planets in terms of Platonic solids, each one sitting inside another. He also talked about the way in which the crystalline spheres that the planets were embedded in would rub against each other. And he talked about the music of the spheres, and he actually describes the kinds of harmonies that the planets make as they travel around the sun. But I want to get back to his question of trying to work with building this model by doing these very involved calculations. With the kind of data that he had inherited from Brahe, Kepler needed to be able to do calculations that were accurate to 5 digits. And in fact, shortly after Kepler began doing his work on Brahe's data, the telescope was invented. Galileo would be the first person to actually begin to use the telescope to look at the stars, and this happened very early in the 1600s. Kepler then would begin to get even more accurate data. Very quickly, he needed not just to do 5-digit calculations, but 7-digit calculations. And certainly by 1630, the data that was available coming from the telescopes was sufficiently accurate that people needed to be able to do calculations that maintained 10 digits of accuracy. Now, doing multiple multiplications and divisions and evaluating trigonometric functions to 5 or 7 or 10 digits of accuracy is extremely difficult. And so a computational device was needed in order to make this easier to do. And that computational device would be invented by the Scotsman John Napier. Napier was born in 1550. He was a Scottish nobleman. He was the Laird of Merchiston in what today is now part of Edinburgh. And he had many interests. He was interested in theology. One of his famous works was published in 1593, and it was a diatribe against the Catholic Church called The Plain Discovery of the Whole Revelation of St. John, in which he talks about how the revelation of St. John is really describing the Pope as the Antichrist. But despite this great skepticism of the Catholic Church, he did travel to Italy in 1594. It's very possible that he actually met Galileo at that time. But he clearly came back from Italy with an interest in developing these computational tools for making it easier to do multiplications and divisions. And in 1614, he finally published his work, what he called Description of the Wonderful Canon of Logarithms. Now, the word logarithm is a word that was invented by Napier to describe what he had created. And there are various ways of understanding its etymology. You can actually see its root in the phrase ratio number, which is a reasonable explanation for what's going on with a logarithm. But the etymology that I really like is to take logarithm as being composed of 2 Greek words, logos and arithmos. And if you recall back when I was talking about Greek mathematics, I said that they viewed mathematics as 2 different areas. One was logos, or logical mathematical reasoning, and the other was arithmos, from which we get our word arithmetic, and this is calculation. And the beauty of the logarithm is that it applies this logical mathematical reasoning to the problem of calculation. And that's precisely what Napier was getting at, trying to simplify calculations. And the idea behind the logarithm is to exploit what happens when you're working with exponents. So let me give you a simple example. Let's say that I want to multiply 16 times 128. Well, if I know my powers of 2, I know that 16 is 2 to the 4th power, and I know that 128 is 2 to the 7th power. Now, one of the results that the Islamic mathematicians were certainly very well aware of and was now known in Western Europe is that if I want to multiply 2 to the 4th times 2 to the 7th, I can accomplish that by adding the exponents. 2 to the 4th times 2 to the 7th, that's 4 copies of 2, times another 7 copies of 2, I get 11 copies of 2. 4 plus 7 is 11. And if I know my powers of 2, I can simply read off a table. 2 to the 11th is 2048. Well, that's great if I'm trying to multiply 2 powers of 2. What if I want to multiply 19 times 33? Well, it is possible to write 19 as a power of 2. You can work with fractional powers of 2. 2 to the 1/2 power is the square root of 2. 2 to the 5/3 power is 2 to the 5th, and then take the cube root of that. So if I have any rational exponent that actually represents taking a power and then taking a root, that represents some number. And there actually is a power of 2 that gives us 19. It's going to be between 2 to the 4th, which is 16, and 2 to the 5th, which is 32. And the actual power of 2 that gives you 19 to 7-digit accuracy is 4.247928. In the same way, we can write 33 as a power of 2. And then we can multiply 19 times 33 by adding these 2 powers of 2. That gives us 2 to the 9.292322. And if I've got a table of powers of 2, I can see that that's approximately 627. Since 19 times 33 is an integer, I know that it's got to be exactly 627. Now, if I look at that exponential equation, 2 to the 4.247928 equals 19. What is happening there, if I start with a 19 and I want to know what that exponent is, what Napier did was to call the exponent the logarithm of 19. Now, the number that we're exponentiating, that 2, is called the base. So 2 is the base, 4.247928 is the logarithm of 19 for the base 2. And the problem then becomes, given an integer, find the exponent of 2 that's going to lead to that integer. In other words, find the logarithm base 2. And then if you know the logarithm, if you know the exponent, what is the number that comes out of that? And so this introduces the idea of the exponential function. We're interested not just in 2 squared and 2 cubed and the integer powers of 2 or the simple fractional powers of 2. We're interested in 2 raised to a power that could be any real number. We're now interested in the exponential as a function. Now, in order to be able to do the kinds of calculations that Napier needed to do, and that the astronomers, people like Kepler, needed to do, if we want 7-digit accuracy, then what we're going to need to be able to do is find tables of logarithms for all of the numbers in increments of 1 in 10 million. Now, I can simplify the problem slightly by just asking for the logarithms of the numbers between 1 and 10. If I know the logarithms of the numbers between 1 and 10, and I've got 2 numbers like 19 and 33, I can divide 19 by 10 and 33 by 10, and I'm taking the product of 1.9 times 3.3. And if I know that product, I take that answer and I just put the factors of 10 back in. So I'll take my answer and multiply it by 100. But there still is a problem of how to get the logarithms of the numbers from 1 to 10 down to the kind of accuracy that you need. And one of Napier's great insights is that if you know the logarithms for base 2, you can use them to find the logarithms for base 3 or any other base you want to use. That there is always going to be a simple conversion factor, so that if I calculate the logarithms for base 2, I can use them to find logarithms for base 3, or base 5, or base 10, or whatever base I might want to use. Now, a base that actually makes sense if you're going to do 7-digit accuracy is the base 1.0000001. So that's 1 plus 1 over 10 million. If I can find the logarithms for that base, and the powers of that base are fairly easy to calculate, if I want to multiply a number by 1.0000001, I just take that number, and that same number with a decimal point moved over 7 places, and add those two together. If I want to take those powers, that will give me the 7-digit accuracy that I need. But in order to get the logarithms for all the numbers from 1 to 10, I'm going to need 23 million powers of 1.0000001. Now, that's an impossible task, and Napier realized that he couldn't do those 23 million calculations. But his insight that once you know the logarithms for one base, there will always be a simple conversion factor that enables you to find the logarithms for any other base, actually enabled him to find these 23 million values very easily. What he actually did was to first find the powers of 1.01 that go from 1 up to 10. You only need 230 powers in order to accomplish that. And then what he did was to interpolate between those. So he then took the powers of 1.0005, 20 powers of that, enabled him to get numbers between 1 and 1.01, between 1.01 and 1.02, and so on. And then he looked at the first 50 powers of 1 plus 1 over 100,000, and that enabled him to interpolate between the values that he already had. And then he looked at the first 100 powers of 1 plus 1 over 10 million, and that enabled him to interpolate beyond the remaining powers. So with just a few hundred calculations, he was actually able to set up tables that would enable somebody to find logarithms to the base 1.00001 for all numbers between 1 and 10 to the desired 7-digit accuracy. But he also realized that since it was so easy to change these bases back and forth, there was no reason to stick with the base 1.0000001. He could choose any base he wanted. And so the question that he next grappled with is what base to use. And what he did was to consider two lines with points moving along each line. And on the first line, we've got the point that we want to take the logarithm of. So we're going to take the logarithm of a real number, and that real number is traveling along this first line. And on the second line, we look at the image of that point under the logarithm. So I've got a point like 3. On the second line, the position is going to be at the logarithm of 3. When the first point gets to 5, the point on the second line is moved up to the logarithm of 5. Get up to 13, it's moved up to the logarithm of 13. The point on the first line travels at a uniform speed. How fast does the point on the second line move? Well, what Napier realized is that the point on the second line moves at a speed that is inversely proportional to the distance that the point on the first line is moved. In other words, if the first point has moved to position x, the speed of the point on the second line is going to be some constant divided by x. The value of that constant is going to depend on the base that I am using for the logarithm. And what Napier decided was to choose the base that would give him a speed where that constant of proportionality was exactly equal to 1. Now, for those who know a little bit about calculus, you may have realized at this point that that's exactly equivalent to finding the slope of the derivative of the logarithm function, and that the slope of the derivative of the logarithmic function is inversely proportional to the value at which you're evaluating it, and that it is this particular logarithm that Napier chose that is what today we call the natural logarithm. Napier never actually worked out what that base needs to be, but it was later observed that it's a number between 2 and 3. It's about 2.71. It's a number that would later be referred to by the letter e, and e now is known as the base of the natural logarithm. It is the base of Napier's logarithm. The actual name natural logarithm would be invented later on in the 1600s. While Napier used this particular base, 2.71, Henry Briggs down in London got a hold of Napier's work on logarithms and recognized that a lot of the calculations would be much easier if instead of using this strange number 2.71, Napier would actually go back and use the base 10. If you're actually taking powers of numbers, a base 10 makes it much easier to work with. And so Briggs went up to Edinburgh in 1615, and he convinced Napier, instead of working out his table of values with 2.71 as the base, to use 10 as the base. Briggs would then go on to develop his own tables of logarithms, and in 1628, Briggs would actually publish a table of logarithms that was accurate to 10-digit accuracy. But Napier's logarithm, this 2.71 base, would wind up having a very important role to play in the calculus. And in the mid-17th century, two Belgian Jesuits, Gregorius St. Vincent and Alfonso Antonio de Sarasa, would consider the problem of finding the area underneath the curve of a hyperbola. So that's a curve that's simply the reciprocal of the variable, so the graph of y equals 1 over x. And what they were able to show is that if you look at the area underneath this curve, starting at x equals 1, going up to some value, say t, the area underneath the hyperbola from 1 to t is actually given by Napier's logarithm of t. It's given by this natural logarithm of t. And so we get both the exponential function and the logarithmic function coming in, and they would be very important concepts as mathematicians then went on to develop the calculus. I'll talk about that more in later lectures. But for the next lecture, I want to go back to the beginning of the 1600s and take a look at another one of the important influences of astronomy, and that is on the work of Galileo and the beginning of the understanding of the mathematics of motion. In my very first lecture, I talked about the 17th century as a pivot point, and I also talked about the 5 strands that would come together in the 17th century: algebra, geometry, astronomy or astrology, mechanics, and the mathematics of motion. And the first figure in which we really see these 5 strands coming together is the great scientist Galileo Galilei, Born in 1564, he would die in 1642. And he's a controversial figure insofar as knowing what it was that he really accomplished. There's a quote that I really love from E.J. Dijksterhuis. Dijksterhuis was one of the great historians of science in the 20th century. And he wrote about Galileo, "The whole history of science perhaps cannot point to a single figure about whom opinions differ so widely as about Galileo. No one indeed is prepared to challenge his scientific greatness, but on the question of what precisely his contribution was and wherein his greatness essentially lay, there seems to be no unanimity at all." And in fact, as we look at what Galileo accomplished, we see that virtually everything that he did we can find foreshadowed in the work of earlier scientists, and often not merely foreshadowed, but often quite fully worked out. And many of the important contributions that he made, he never got quite right. It would fall to later scientists in order to complete them. But for myself, where I see Galileo's greatness is that he knew the right questions to ask. He knew what was important, and he had a good sense of where to look for the solutions. Most particularly, he realized that if we wanted to understand the motions of the planets, if we wanted to understand celestial mechanics, we really needed to look at mathematical modeling. And it's this very important emphasis on the mathematics that really sets Galileo apart from others. He didn't work out the techniques, but he showed us how to approach the problems. And his work then would lead on into the eventual development of the calculus. Galileo was really trained as an algebraist, as a mathematician. He got his first job in 1585 in Florence. He would then hold a succession of positions in Siena, in Vallombrosa, in Pisa, and in 1592 he was appointed to a position in Padua, and this is where he would have been in 1594 when John Napier visited Italy, and we know that Napier probably got to Padua, which makes it very likely that the two of them actually met each other. In 1610, Galileo would return to Pisa. And there was a very important book that he published in 1610 called The Starry Messenger. Some years earlier, Galileo had gotten a hold of one of the first telescopes. This originally had been built in the Netherlands, in the lowlands of Belgium and Holland. And what Galileo did was to use it not just in order to see objects that are far away on the earth, but actually to look at the heavens, and to look at the moon, and to look at the planets, and to observe what was out there, and to observe the first moons of other planets that were known to exist, thus showing that not everything went around the Earth, because there were moons that go around the other planets. And to see things like the mountains on the moon, just thus showing that the moon was not ethereal and perfect, that the moon, in fact, had imperfections on it. And The Starry Messenger of 1610 was a popular book that he wrote, explaining what he understood about the heavens and the arguments for the fact that it is the Earth that travels around the sun rather than the sun that travels around the Earth. And this was made quite explicit in a book published in 1616, Letter to the Grand Duchess, in which he lays out this point of view quite clearly. And this was the first time that he was pulled before the Inquisition in Rome, and he was warned at this point that he should not state that he knew categorically that the Earth traveled around the sun. It was fine for him to put that out as a possible basis for a model, But he was not allowed to say that this, in fact, is what was happening. Because there are passages in the Old Testament, most especially in the Psalms, that talk about the earth being on a firm foundation and the earth never moving. And so the Catholic Church believed that it was important not to state that, in fact, the earth could move. But Galileo was convinced that, in fact, the earth moved, and he realized that if he was going to support that point of view, he had to be able to explain how it was possible for the earth to move and for us not to be aware of its motion. And so he began trying to model gravity and inertia and all of the physics that would go behind explaining how we could be on a moving earth without being aware of its motion. And the great book that he wrote that explains his physical understanding of the universe would finally appear in 1632, called The Dialogue Concerning the Two Chief Systems of the World. And he was very careful, or he thought he was being very careful, not to put this out, the idea that the earth is moving around the sun, as something that he actually believed. He wrote the book with three protagonists who were debating this issue of whether the earth goes around the sun or it is the sun that goes around the earth. His three protagonists were Salviati, Sagredo, and Simplicio, one of whom was an intelligent layman, one of whom was a person who believed that in fact it is the earth that goes around the sun, and one who argued that in fact the earth is stationary and the sun goes around the earth. The person who held to the position that it is the earth that is stationary was given the name Simplicio, which perhaps suggests that Galileo's sympathies were not with him, and he's somewhat portrayed as the simpleton of the group. And certainly the Inquisition was very much aware of the fact that while this book claimed to be impartial, there was a very clear argument in favor of the earth traveling around the sun. And so for this reason, Galileo was called before the Inquisition in Rome. And many of us know that this story, how he recanted. He agreed that it must be the earth that is stationary. And he was forbidden from publishing this work, The Dialogue Concerning the Two Chief Systems of the World. And he was restrained, restricted to house arrest at his home in Arcetri for the rest of his life. But I want to look at the mathematics that he did, and especially the mathematics that appears in the dialogue. One of the things that Galileo realized is that the key to understanding what is happening, why we don't sense the motion of the earth, has got to be gravity. And to understand gravity, we must go back to the Aristotelian viewpoint of what gravity is and what Galileo was changing about our understanding of gravity. To Aristotle and the later scientists, philosophers, gravity, gravitas, was a property inherent in certain bodies. It's a tendency of certain objects to move toward the center of the universe. And if the earth is at the center of the universe, that's because it has more gravity than anything else. And if you drop an object, if I take a book and let go of it and it falls, that's because the book has gravity. It is trying to get to the center of the universe. As opposed to gravity, an object can have levity, which is a tendency to move away from the center of the earth. So fire rises because it has levity. Now, one of the problems that you encounter as you try to explain what's happening in terms of gravity and levity is the problem of what happens when you throw an object. If I take a ball and I throw it, as long as the ball is in my hand, because it's in contact with my hand, it can move away from the center of the earth. But as soon as it leaves my hand, it continues moving away from the center of the earth. I can throw it up in the air and it continues moving away from the earth. why doesn't it immediately start moving toward the center of the universe? And the explanation that eventually would be found is the theory of impetus. The idea that as I'm moving this object, it begins to accumulate an impetus, a tendency to keep moving in a given direction. And so, to the medieval philosophers, they were able to explain this motion of a thrown object as something that acquires a certain impetus from the hand, and they expected that this impetus would gradually dissipate as the object traveled through the air, until finally the impetus ran out and the object would then fall to the ground. And early explanations of the motion of cannonballs used this idea. People drew illustrations of the motions of cannonballs that showed a cannonball being fired straight out of the cannon, traveling in a straight line until it ran out of impetus, and then falling vertically down to the ground, and hopefully it was above the target at the moment that it began falling. But it was pretty clear that this is not really the way in which a cannonball travels. A cannonball travels along an arc. And so trying to explain that arc and what is going on with this gravity, with this tendency to move toward the center of the Earth, was one of the important problems, not just for Galileo, but also for the scientists of the 16th century. Now, as Galileo tested the ideas behind gravity, one of the ideas that he tested is this idea that if you've got a heavy object, it's going to fall faster than a lighter object. And there is a common story told that Galileo went up to a tall tower, and perhaps the Leaning Tower of Pisa, and took two balls of unequal weight and dropped them and observed that they hit the ground at the same time. There actually is absolutely no evidence that Galileo ever conducted this experiment, but we do know somebody who did. The Belgian and then later Dutch scientist Simon Stevin, who lived 1548 to 1620. It is known that in 1586 he went up to the top of a church tower and actually performed this experiment of dropping two balls and observing that even though they have very unequal weights, they both hit the ground essentially at the same time. Stephen is an important figure for a number of reasons. There are a number of things that Galileo did that were prefigured in Stephen, and I'll come back to him a little later this lecture. But I just want to mention a very influential book that he wrote in 1585 called La Tiende, which advocates for the adoption of decimal fractions. If you recall, when I was talking about the Islamic mathematicians, I said that they adopted the idea of decimal fractions, so tenths and hundredths and thousandths, using the decimal system. They also continued to use the system that had been inherited from the Babylonians, that used sixtieths and sixtieths of sixtieths, as we get now in an hour is divided into 60 minutes and a minute is divided into 60 seconds. And what happened in the Islamic world and in the early Italian world was two systems that existed side by side. For most of the merchants, they found tenths and hundredths, decimal fractions, to be very easy to work with. In scientific work, especially astronomical work, but also more general scientific work, they would use sixtieths and sixtieths of sixtieths. And it was Simon Stevin who argued that you really want to use the decimal fractions, tenths, hundredths, thousandths, and so on. And he wrote this little book to argue for this point. And we happen to know that Thomas Jefferson had an English translation of Simon Stevin's book. And that Jefferson was so impressed by this argument that when the new United States government set up its own money, so the dollar, one of the questions that came up is, how should we subdivide the dollar? The British system, of course, was to divide a pound into 240 pence. Rather than dividing a dollar into 240 pennies, Jefferson took this work of Simon Stevin and argued that we should divide the dollar up into 100 pennies. that we should work with a decimal system for our dollar. And so Simon Stevin had a direct influence on American currency. Simon Stevin also wrote very influential books on arithmetic and on algebra. There is another experiment, this time a thought experiment, that Galileo is credited with doing on falling objects, again with whether two objects of different weights should hit at the same time or whether the heavier object should hit first. And that involves the question, what if I take two balls and I connect them by some kind of a bar? Now suddenly they weigh at least twice as much. They should fall twice as fast. But what if that's a very thin bar? Is that still one object? What if instead of being a bar, it's simply a piece of string that connects the two balls? Does that now make them one object? What if it's just the lightest gossamer thread that connects the two balls? Does that now make them one object? And obviously, once you get a very thin connection, you need to think of them as two objects. This whole question raises the realization that, in fact, the rate at which something falls cannot be dependent on its weight. And that was something that is often credited to Galileo. In fact, that goes back also into the 16th century to Giovanni Benedetti, who also studied this question of falling objects. Galileo looked at this question of falling objects, and one of the questions that was still out there, that was still undecided, is whether the velocity, which increases as an object falls, whether that velocity is increasing as a function of time or as a function of distance. Now, actually, you can express the velocity either as a function of time or as a function of distance. The real question is it easier to express it as a function of distance or a function of time? And the scientists up until the early 1600s had debated this, and we see in Galileo's own writings that he himself went back and forth on this, taking different points of view, and eventually coming to the conclusion that you've got to look at the velocity as increasing at the same rate over each interval of time. And in fact, we do know that Galileo conducted experiments with balls rolling down inclined planes that showed that in each unit of time, the ball picks up the same increase in velocity. So velocity is most easily expressed as a function of time. And this would be a very important insight. That now raises the question, if you've got an object that is falling, such as a ball falling under the influence of gravity, we let go of that ball, its velocity is increasing, so for each unit of time, the velocity increases by the same amount. How far does the ball fall over a given period of time? And Galileo did something very important here that would be a precursor to calculus, to integration. And that was to represent the velocity at each piece of time by a small line. So we would take the velocity as initially 0, and then a short line that would represent the velocity a short time later, and then a slightly longer line that would represent the velocity slightly later, and a slightly longer line that would represent the velocity later. And you put all of these lines together, and you get a triangle. And what Galileo realized was that the distance that the object would travel is precisely the area of this triangle. It can be represented by the area of this triangle. And the area of the triangle is the base, which is the time that is elapsed, times half of the height. So you take the final velocity and take half of that, so that the distance traveled under uniform acceleration, the velocity changes by the same amount in each unit of time. The total distance traveled is the amount of time it takes multiplied by half of the final velocity. And this idea of representing the velocity as little vertical lines would really be the key leading into the development of analytic geometry that I will be talking about in the next lecture. Something else that Galileo did that would be extremely important is the idea of the vector decomposition of velocities. So I'm going to take a ball and I'm going to throw it. And what Galileo did was to take the velocity of the ball and break it down into two parts, a horizontal component and a vertical component. And what Galileo assumed is that the horizontal component is not going to change. It's certainly not going to change very much. But the vertical component of the velocity is going to change. We can treat the vertical component of the velocity as if we're working with a falling object. So what we can do is to take this ball that is being thrown and decompose the motion into a horizontal motion at a constant velocity, plus a vertical motion that initially is going up and then is coming back down. And the vertical component is decreasing by exactly the same amount in each unit of time. And by doing this kind of decomposition of the velocities, the horizontal component does not change. The vertical component decreases by the same amount in each unit of time. Galileo was able to show that the path is going to have to be a parabola. And this is the first time we get the description of the trajectory of a thrown object or the trajectory of a cannonball being shown to be modeled by a parabola. Now, this idea of decomposing a velocity into two orthogonal components, two pieces that are at right angles to each other, had some precursors in ideas of Simon Stevin. Now, Stevin was not decomposing velocities. What Stevin did was to consider decomposing forces. And one of his important works was Elements of the Art of Weighing. And one of the things that he looked at there was the problem of an object that is sitting on an inclined plane. So I've got a slanted plane, and I've got an object sitting on it, and I've got the force of gravity that is pulling this object down. We assume that there's no friction on this surface. And the question is, how much force do we need to apply in order to keep that object stationary on the plane? Now, the actual force that is acting on this object is a force that is straight down. But the object would have to move parallel to the surface of this inclined plane. And what Simon Stevin realized is you could figure out the amount of force that was needed to counteract the tendency of the object to slide by taking that vertical force and decomposing that into two pieces. One force that ran parallel to the plane and another force that was at right angles to the plane. And you simply construct a rectangle so that the vertical force due to gravity becomes the diagonal of a rectangle. And the side of the rectangle that is parallel to the plane, that's the component of the force that is pushing this object down the plane. That's the force that is needed in order to keep the object stationary. So this idea of taking a force and decomposing it is something that we get from Simon Stevin. Galileo took Stephen's idea, and he then applied it to a decomposition of velocities, which turned out to be a very useful way of understanding trajectories. Something else that Galileo looked at was the question of inertia. And as Galileo realized, inertia really would be the key to understanding why we don't have this sense of moving on, or of being on a moving Earth, of moving around the sun at such incredible speeds. Now, inertia initially was very closely connected to this idea of impetus, this belief that inertia is something that is a tendency for bodies to remain at rest. And to get something going, to keep it going, you've got to overcome inertia. Galileo is the first scientist to really realize that inertia is a tendency to keep going the way you have been going. And so if you're in motion, you're going to tend to stay in motion unless there's a force that acts on you. If you are stationary, you're going to tend to remain stationary unless there is a force that is acting on you. But Galileo didn't quite get inertia correct. He was trying to explain why we're able to stand on an Earth that's spinning at such an incredible speed without any sense that we are spinning on this Earth. And he tried to explain this in terms of inertia. He believed in a circular inertia, that if you're moving in a circular pattern, you're going to tend to stay in a circular motion. And that's why we don't sense this motion of the Earth, that we have this circular inertia that is tending to take us around the Earth. And also that we have this circular inertia that is moving us around the sun, and we're not aware of that motion. Well, he was wrong. As would later be discovered, there is no such thing as a circular inertia. There is only an inertia in straight lines. It's been suggested that one of the reasons that Galileo was not able to realize this idea of a tendency to keep moving in a straight line at the same velocity forever is because that really assumes that space goes on forever. And Galileo was not prepared to accept space that was infinite. To him, he still believed in a universe that was enclosed within a sphere. And in fact, circles were extremely important to his understanding of the workings of the universe. Galileo was someone who never accepted Kepler's law that in fact the planets moved in ellipses. Galileo always held to his belief that somehow everything really was moving in circles. But as I said at the beginning of the lecture, and I want to come back to now, Galileo's real insight, his real contribution, was the realization that if you want to understand the world around us, you need to use mathematics. You need to look at mathematical modeling. And I'd like to close with a quote from Galileo that really says this very clearly and would really set the stage for the mathematics that would follow in the 17th century. He wrote, "Philosophy is written in this grand book, the universe, which stands continually open to our gaze. But the book cannot be understood unless one first learns to comprehend the language and read the characters in which it is written. It is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures without which it is humanly impossible to understand a single word of it. Without these, one is wandering in a dark labyrinth. The key to understanding the universe is to know the language of mathematics." And Galileo then would set the stage for this. In our next lecture, we will continue with Fermat and Descartes, taking Galileo's idea of representing velocity as a sequence of vertical lines and turning that into analytic geometry, and so setting the stage for the development of calculus. In this lecture, we're going to look at Pierre de Fermat and also René Descartes. Fermat really is instrumental in the development of analytic geometry and the origins of calculus. And this will be the first time that I talk a little bit about Fermat's last theorem. Fermat was, by profession, a lawyer. His mathematics was simply an avocation. Fermat had been born in 1601. He would die in 1665. Born near Toulouse, he first went to Bordeaux, and there he actually studied mathematics, studied with some of the disciples of Viette, a French algebraist from the 1500s who was no longer alive at that time, but people who had studied with Viette were around, and Fermat learned a lot of his mathematics at that time. From Bordeaux, he then went on to Orléans, where he got a law degree, and then returned to Toulouse. He initially got a job as counselor to Parliament, and it was in this capacity as a counselor that he was able to add the DE to his name, and so he became Pierre de Fermat. He fairly quickly rose through the ranks as a lawyer in service to the Parliament and to the government in Toulouse. By 1638, he was counselor for the Upper House of Parliament, and by 1652, he was working for the Criminal Court and would eventually attain one of the highest positions there. In fact, his rise through the law profession was so meteoric that a number of people have postulated that it may have been his good luck that the plague came through Toulouse so frequently, that his superiors probably were dying off, which is why he was able to rise through the ranks. He himself at one time did actually contract the plague, and the rumor went out for a while that he had actually died of the plague, although fortunately for us, he did survive. As I said, Fermat looked at mathematics as an avocation. He actually published very little in his lifetime, and we might not even know about Pierre de Fermat if it had not been for his son. It was his son who would collect his manuscripts after his father's death and then see that they got published and that his name was more widely known. The first mathematics that Pierre de Fermat did came out of work that he had begun in the 1620s while he was in Bordeaux. He had come across a description of a lost book from Apollonius. So this is Apollonius of Perga, the author of the Conics. And one of the books that he wrote was called Plane Loci, or its two-dimensional curves. That book is lost to us. But a later Greek mathematician by the name of Pappus had written about this particular book of Apollonius and described many of the results that Apollonius had proven in his book. And so Fermat took a translation into Latin of this description of the lost book of Apollonius, and he sought to try to prove these results on geometry. And they were extremely difficult to prove. But in order to find a proof, what Fermat did was to invent an entirely new way of approaching geometric problems, what today we call analytic geometry. What he did was to take a geometric figure and reinterpret it algebraically. Usually the way we think of that today is to take an algebraic expression and look at it geometrically when we graph an algebraic expression. And so we put a horizontal axis and we put a vertical axis. We've got our two variables, the x and the y. And for each pair of values, a value for x and a value for y that correspond to a point that satisfies an algebraic equation, we take a look at the x value and the y value and we plot that point. And as you plot all of the points on what today is called a Cartesian coordinate axis, you get a curve traced out. Now you can actually look at this both ways. You can start with an algebraic expression and turn it into a geometric curve. You can also start with a geometric curve and turn it into an algebraic expression. And this is exactly what Fermat did. He took the geometric statements that Apollonius had made, he translated them into algebraic statements, and then he used this very advanced work on algebra that had been done in the preceding centuries in order to find simple solutions and simple proofs to these geometric problems. Now, when Fermat did his coordinate axes, he didn't do them quite the way we would do them today. He did not actually have a vertical axis. He had the horizontal axis on which one of the variables would be represented, and then he simply marked off the distance to the other variable, very much along the lines of what Galileo did. But remember that Galileo actually drew little vertical lines. One of Fermat's inventions was not to draw those little vertical lines, but simply to mark the point above the horizontal axis. But he didn't actually put in the vertical axis. And actually, as he found the distance from the horizontal axis, he didn't always move vertically. Sometimes he moved off at an angle. The important thing is that you're always moving off at exactly the same angle. But it provides a method for translating this algebraic expression into geometric, or geometric back into algebraic. It's an idea that Fermat came up with. Descartes would also come up with the same idea at the same time. Fermat had started on this work in the 1620s. It would be 1637 before he was ready to publish it. And he published it in that year as the book Introduction to Plane and Solid Loci. And exactly that same year, by one of the great coincidences that often happens in mathematics, René Descartes independently came up with exactly the same idea for translating between geometric objects and algebraic expressions. René Descartes published his great work, Geometry, contained in a more comprehensive work called Discourse on the Method for Rightly Directing One's Reason and Searching for Truth in the Sciences. And one of the things that you cannot accuse Descartes of is being overly humble. He believed that he had found the right way for answering any scientific question that would be out there. Now, in fact, Descartes' explanation of how to pass back and forth between geometric and algebraic expressions would become much more popular than Fermat's for a couple of reasons. One, Descartes was just much better known. Also, Descartes was very good at coming up with efficient algebraic notation. And the notation that we use today is really Descartes' algebraic notation. Fermat was using an algebraic notation that he had learned from Viet's disciples. It's not as efficient, it's not as easy to work with. A lot of people looked at Fermat's work and they couldn't understand what he was really doing, or they had trouble reading it. And that is why today, when we talk about a coordinate plane, we talk about it as a Cartesian plane, named after Descartes, rather than a Fermatian plane, named after Pierre de Fermat. Although in reality, both of them discovered the same idea and published this idea in exactly the same year. Now, there is an important difference between how Descartes and Fermat looked at this problem of moving between geometry and algebra. Descartes, like Fermat, started with this idea of taking a geometric object, interpreting it algebraically, and then being able to come to geometric conclusions by studying the algebra. That is how Fermat began this, but Fermat fairly quickly realized that he could move in the other direction, and that would be very powerful. He could take an algebraic expression, say the equation that describes a quadratic polynomial, a polynomial of degree 2, and he could then graph that algebraic expression and work with a parabola instead of the algebraic expression. And when you take an algebraic expression and you look at it geometrically, very often you can see things in the geometry that are not immediately apparent when you're looking at the algebra. And two examples of this are, you can think about the area underneath the geometric object. So I've got a parabola, perhaps a parabola that is opening downward. And one can ask, what is the area between the horizontal axis and this particular parabola? The other thing that you can look at is, where does this algebraic expression hit its largest value? Where does it reach its smallest value, say within some range of values? If you look at it geometrically, the highest value is simply going to be where that curve peaks. And the lowest value is going to be where that curve has its lowest valley. And that ability to take an algebraic expression and translate it into something geometric would very directly lead into the development of much of calculus. This is something, unfortunately, that Descartes missed. I want to say just a little bit more about Descartes. I mentioned before that he is the person who invented the term imaginary number for the square root of a negative number. Again, a very, very unfortunate term, because these are numbers that truly exist, even though Descartes called them imaginary. This is also a time in the 17th century when people were still not sure about whether to accept negative numbers as legitimate numbers. Now, I've talked about the introduction of negative numbers. The Chinese were the first to work with them. They didn't accept them as legitimate solutions, but they realized that they were important as intermediate steps. And the Indian mathematicians eventually would adopt them not just as intermediate steps, but actually as legitimate answers. The Islamic mathematicians were very much divided on whether or not to allow negative numbers. They were certainly very useful. On the other hand, they were very much embedded in the Greek tradition and the Babylonian tradition that looked at numbers as describing something, and ideally numbers were describing lengths in some way. You can't talk about a negative length, and so it never really seemed to make sense to talk about negative numbers. And when we get into Western Europe in the 15th, 16th, and 17th centuries, there was a very real ongoing debate about whether or not to accept negative numbers as legitimate answers. Descartes was one of the last to really speak out against accepting negative numbers. He would talk about a negative root of a polynomial, a negative solution to a polynomial equation, as a false root, and a positive solution as a true root. Fortunately, that's a terminology that we have long since lost. And certainly by the middle of the 17th century and well into the late 17th century, people were now accepting negative numbers as legitimate numbers that really could be answers to problems that were out there. One of the other things that Descartes did that really set science back quite a bit was his Principles of Philosophy, published in 1644. His idea was to put out principles on which you could base all of your knowledge of the universe. So he was looking at this problem that Aristotle had laid out foundations for understanding the world around us, and the Aristotelian foundations were crumbling. Descartes decided to replace those with modern foundations that would hold up. And so this is where we get such phrases as cogito ergo sum, I think, therefore I am. And his work consists of 4 major volumes: the Principles of Human Knowledge, the Principles of Material Things, of the Visible World, and the Earth. And one of the things that Descartes stated quite forcefully in this particular collection was that there can be no action without an actor, no action at a distance. If something is moving, it's because something else is moving it. And so he explained the motion of the planets by postulating an ether that pervaded all of the universe, and it was actually the swirling ether that was moving the planets in their courses. And he explained the fact that we don't sense motion because we are embedded in this ether. We are moving with the ether, and since we're moving with this ether, we don't sense this motion. Now, I said that would be one of the great disasters of the mid-17th century, and that's because when Newton published his Principia, he was looking at gravity. Gravity is something that acts at a distance, and Newton was unable to explain how it was possible for gravity to act at a distance without any intermediary. And a lot of people criticize Newton, in fact, refuse to accept his great work on celestial mechanics, precisely because he could not come up with a Cartesian-type mechanism in order to explain how gravity was able to act. I said that Fermat published very little. Even though he published very little, he was an active correspondent in mathematics. And most of his correspondence was undertaken with a Catholic priest in Paris by the name of Father Marin Mersenne, a very important figure during the 1600s. This is a time before scientific journals. And so if you wanted to find out what something else was doing, you had to learn it by letter. And there were a few key people, and Father Mersenne was one of the most important of these, who would correspond with the scientists of that time. He would hear what different people were doing, what they had discovered, and then he would send out letters to all of his acquaintances describing this. He was a great friend of Descartes. He was a good friend of Christian Huygens, who I will talk about in the next lecture, and he also corresponded regularly with Fermat. Mersenne, incidentally, was also a great supporter of Galileo, despite the fact that he was a Catholic priest. In secret, he managed to smuggle out a copy of Galileo's Dialogue, this work that had been banned by the Inquisition. It was Mersenne who managed to get a copy of this to the Netherlands and to see that it got published. Mersenne is known to have had over 78 correspondents during his life, including not just Descartes and Huygens and Fermat, but also Gassendi, Roberval, Pell, Torricelli, Hobbes, and both Etienne and Blaise Pascal, all of the great scientists of his time. In 1636, Fermat tackles the problem of finding the area underneath a curve that is described by an algebraic expression. So this is, in essence, what would come to be understood as the integral calculus. Given an algebraic expression, consider its curve, the curve that represents that expression, and look at the area underneath it. And it would be Fermat who would be the first person who would actually discover how to find the area underneath this curve for an arbitrary algebraic expression, coming up with what today we think of as the roots for integrating, as the means of integrating polynomials. He used precisely the method of exhaustion that goes back to Eudoxus of Cnidus, and that had been used then by Euclid and Archimedes and Ibn al-Haytham and many mathematicians since then. And Fermat showed how to use this idea in order to find areas under curves. He was not the only person. One of the other correspondents of Mersenne in the very same year of 1636, Gilles de Roberval, also found exactly the same formula for the area under a curve that corresponds to an arbitrary polynomial. Fermat then went on and considered the problem of, given an algebraic expression, how do we find where it reaches its maximum, its greatest value, or its minimum, its least value? And in 1639, he would discover how to do this. And the idea was to take the algebraic expression, represent it as a curve, and then look at the line that is tangent to the curve at each point. If we consider the line that touches the curve at just a single point, if I've got an expression that is increasing, that slope is going to be positive. If I've got an expression that is decreasing, that slope is going to be negative. if I've got an expression that is at its highest value or at its very lowest value, then that tangent line is going to be horizontal. Its slope is going to be 0. Fermat did not stop there. He then looked at how to determine the slope of the tangent line at a single point. And what he did then was to consider 2 points that are very close to the point in question on the curve that we're looking at. And it's possible to actually construct the equation of the straight line that goes through those 2 points. And the slope of the line that goes through those 2 points is going to be the rise over the run. It's the change in the y value divided by the change in the x value. And Fermat's brilliant insight was that you could take this change in the x value to be smaller and smaller and smaller. As the change in the x value gets smaller, the change in the y value gets smaller. And what happens is that this ratio of 2 numbers, both the numerator and denominator, are getting closer to 0, but this ratio is going to approach some number that is the slope of the line that is precisely tangent at that particular point. When we want to find the maximum value or the minimum value, we do precisely this procedure, but we're looking for those points where the slope of the tangent line is exactly equal to 0. Now, the fact that the slope of the tangent line is 0 does not guarantee that we have either a maximum value or a minimum value. The function might increase, level off at a kind of step, and then start increasing again. But in general, for most algebraic expressions, you're going to have very few places where the function actually has a horizontal tangent line. And so that greatly limits the number of places where you have to look for the greatest value or the least value. In fact, restricts it so that you can then simply look at the value of the function at the different candidates and pick that value of the function at which you get the largest value or the smallest value. Fermat extended this idea to actually find ways of determining this slope of the tangent line, what today we call the derivative of the function. Fermat found rules for doing this for any polynomial, for arbitrary, not only integer powers of an unknown, but also for arbitrary rational powers of an unknown. So if I've got something that is representing, say, a curve that's representing the square root of x, or the cube root of x, or x to the 5/3 power, Fermat showed how to find the slope of the tangent line for an expression such as that. I want to spend the rest of this lecture looking at Fermat's work in number theory, because that would be extremely important. Fermat read Diophantus's Arithmetica, and one of the things that he discovered there was the Pythagorean triples. Something else that he discovered in the work of Diophantus was perfect numbers. A perfect number is one which, if you take the sum of its proper divisors, gets you back to that number. So in the case of 6, the sum of its proper divisors, 1, 2, and 3, is 6 again. If I take the proper divisors of 28, they are 1, 2, 4, 7, and 14. If I add those numbers up, I get back to 28. Perfect numbers were important to the Greeks. They continue to be important. And in fact, one of my favorite quotes comes from St. Augustine of Hippo. In The City of God, he muses on why it took God exactly 6 days to complete the creation. And he says in that, it is recorded that all God's works were completed in 6 days because 6 is a perfect number. Well, there were 4 perfect numbers that were known to the ancient Greeks, 628, 496, and 8128. And Fermat was interested in this problem of going beyond that. And one of the keys to finding a perfect number, as Fermat realized, was to find a prime that is 1 less than a power of 2. So if I look at 6, that's 2 times 3. 3 is 1 less than a power of 2. If I look at 28, that is 4 times 7. 7 is 1 less than a power of 2. And the even perfect numbers, we actually don't know if there are any odd perfect numbers or not, but the even perfect numbers all have to be of this form. It's going to be a power of 2 times a prime that is 1 less than a power of 2. And Fermat did very important work in understanding when a number that is 1 less than a power of 2 can be a prime. First of all, the exponent has to be a prime. 2 to the 8th minus 1 cannot possibly be prime. 2 to the 9th minus 1 cannot possibly be prime. 2 to the 11th minus 1 might be a prime. In fact, it's not. 2 to the 11th minus 1 is equal to 23 times 89. But something interesting is happening there. If I look at 23 and 89, I was using the exponent 11. And both 23 and 89 are 1 more than a multiple of 11. There's something very deep going on here that Fermat realized, that if I take a prime, take 2 to that prime power and subtract 1, the only numbers that can divide into that are numbers that are 1 more than a multiple of that prime exponent. This would come to be known as Fermat's Little theorem, and it would come to play a very important role in number theory, and in fact the RSA public key crypto system that I'll talk about in the very last lecture has its foundation in this observation of Fermat. This problem of when is 1 less than a power of 2 equal to a prime is one that would continue to interest mathematicians. And in fact, the very largest known prime today is of this form. It is called a Mersenne prime in honor of Father Merin Mersenne. And the largest prime known at the moment that I am speaking, and this changes about once a year, but currently the largest known prime is the 44th prime that is 1 less than a power of 2. It is 2 to the 32,582,657 minus 1. It's an enormous number. It's got almost 10 million digits in it, so I'm not going to be able to show you that number. But in general, the largest known prime has usually been one of these Mersenne primes, a number that is 1 less than a power of 2. Fermat also was interested in the problem of Pythagorean triples. So integers like 3, 4, 5, where 3 squared plus 4 squared equals 5 squared, or 5, 12, 13, 5 squared plus 12 squared equals 13 squared. And that led him to think about, what about using higher powers? Can I find 3 positive integers so that the cube of the first plus the cube of the second is equal to the cube of the third? Or use 4th powers. The 4th power of the first plus the 4th power of the second is equal to the 4th power of the third. Well, he was reading Diophantus, his Arithmetica at this time, and he was writing his notes in the margin. And this copy of Diophantus with the marginal notes is something that Fermat's son would publish with all of these marginal notes. And this is how we come to know of what today is called Fermat's last theorem. And Fermat wrote in the margin, thinking about doing Pythagorean triples but for higher powers, it is impossible for a cube to be written as a sum of 2 cubes, or a 4th power to be written as a sum of 2 4th powers, or in general for any number which is a power greater than the second to be written as a sum of 2 like powers. I have a truly marvelous demonstration which this margin is too narrow to contain. Well, almost certainly he did not have a proof of this result, which came to be known as Fermat's last theorem, called Fermat's last theorem because over the years, people would prove all of the other results that Fermat had stated without proof, or show that they were wrong. This was the last of his assertions that needed to be settled, and it would not be finally settled until the very end of the 20th century. But that's a topic for a later lecture. For the next lecture, we're going to turn to Isaac Newton and the full development of calculus.